Welcome to jFocus. Please don't leave any empty seats. Welcome to jFocus. Please don't leave any empty seats in the room. Thank you.
Good morning. Please stand up and move to the center of east section as all seats are sold out. So please stand and make sure there are no empty seats between you and your neighbor. Thank you very much.
Matthias, where are you? What are you doing?
Hi, Helena. My spaceship start sequence will not compile. I'm stuck here on planet MPE.
But you're supposed to be here in Stockholm to kick off the 14th Intergalactic Developer Conference, jfokus. Help me, Matthias, you're my only hope. What is wrong with your code?
I don't know. It worked on my computer, but when I ran it remote, I felt a great disturbance in the source, as if hundreds of testers suddenly cried out in error and were suddenly silenced. I fear something terrible has happened.
But our ally is the source, and a powerful ally it is. Someone from the dark side ruined it. I think they have done a commit and run.
That would explain why all the integration tests are red. I even get the blue screen of death. The source needs to be compiled and rebuilt. I'm stuck on the dark side of merge hell.
Calm down. Just resolve all conflicts and choose the right side of the source. Hurry up, will ya? We haven't got all day. There are 1,800 developers here waiting for us. Mostly humans, I believe. Many locals, but also guests from places far, far away, like Japan, Serbia, United States, and the Moon of Oak. When will you be back? We have to inform everybody about food and other practicalities.
Food? I know nothing about food. That's all handled by Count Duke. Let's check with him. Welcome, almighty Count Duke, the last descendant from the planet of Oak. What do we get for lunch? Thank you, Count Duke. Helena, if delegates have questions, who should they talk to?
They should install the jfokus app on their personal communicator. And there is a ground crew of jfokus volunteers in grey t-shirts to help them whenever they are in need. Hurry up, get back to Earth and join me. Use the source, Matthias.
All right, I'll give it a try.
No, try not. Do or do not. There is no try.
Or catch.
Let's welcome all developers to the 14th major version of jfokus. Delegates, stay on the good side of the source and be gentle. With each other, with the venue, and with the Wi-Fi.
May the source be with you.
Ladies and gentlemen, please welcome Daniel Banks. May the source be with you.
Good morning, everyone. Give me just 1 second. Oops, there I go, and I dropped my mouse. Great way to start. Okay. Alrighty. So, at this point, you are probably wondering why Matthias asked a digital television meteorologist to come and talk to you, right? Valid question. You want to know why? I'm in your pocket right now. Interesting looks on your faces. I didn't even have to say it all creepy or anything, like I'm in your pocket. But seriously, take out your phones and open up the Weather Channel app for me, okay? Open up your Weather Channel app, and you're gonna come to this. So that's gonna be a look at your home screen, okay? And you're gonna see the current forecast up there. Took a screenshot of that last week. It's only about 5 degrees cooler this week, but at least we don't have the rain, right? But where you're gonna find me and my crew is under the video section where that bottom arrow is pointing, okay? All right, so within the app, you're gonna see multiple playlists up there at the top. You can select whichever one you want. They're categorized under different things. We can create up to 8, we generally keep it at 4. But the order can be rearranged any time, not just on which playlist 1, 2, 3, 4, but the order in which the playlist is stacked. And we have analytics people that test this all day long. They'll try out different things. They might move slot 1 down to slot 5 up to slot 2, and so forth. And then they'll also try out different headlines just to see what people are the most interested in. And of course, the things that end up being the top performers are the ones that you generally see at the top of the playlist. It doesn't even necessarily have to be the most recent video either, just the video that seems to be performing well and capturing the audience's interest a lot. All right, so pop quiz time. You guys ready? Because there's a prize involved. All right. What is the #1 use of smartphones? Anybody want to take a crack? Besides pictures. I should have put pictures up there too. Nope. Shopping. What's #2? Close. What do I do for a living? Okay, very good. All right, I'm gonna give you the umbrella, okay? You're gonna get a Weather Channel umbrella, this gentleman right here, okay? So come up afterwards and get a Weather Channel umbrella, all right? All right, so news and weather top the list. And then music and streaming video. There are those cat videos you were talking about. And digital wallets, and of course the space for, of course, hailing rides, Uber, and also Lyft continues to grow. So this was compiled by Deloitte, pretty recent study. And what's interesting to me about this particular study is, a lot of people have been wondering, why is television viewership declining? Nobody in television is doing anything wrong, but people have gotten sick of all of the ads. And Deloitte found in a study that if you go past 16 minutes worth of ads, that's it. 20, they're gone. 8 minutes is where most people say that they're comfortable. So with television, of course, a lot of times you have these placed commercials that actually goes through a department called the traffic department in local news stations. And so, of course, if they don't sell ads, that TV station's not going to make money. But we all know that the viewership, of course, is really high on digital, but that's also where the advertisers have been going. So in part, because in the digital space, we can also offer non-ads. Even our app, we offer a premium subscribership just for people who maybe want to opt to not have ads and also get some additional services. So more and more companies are giving people that option. If you don't want the ads, here's a way to opt out. Some of them, you just have to click a button. Some of them, you do have to pay a little bit of money to get that. So this is where I'm from. I am a Georgia peach from Atlanta, Georgia. And this is a look at our building. So this is where I work. And why did it go away? Oh. All right, so this is a drone shot. There it goes. My coworker, Jim Robinson, shot this, and it's such a beautiful building. We overlook the interstate from the penthouse, so I get to see how bad traffic is every single day. And trust me, in Atlanta, there is some very, very bad traffic. But it's a gorgeous building. If you're ever in Atlanta, please send me a tweet. I'd love to give you a tour of the studio. Seriously, it's a really cool space. It's a small studio, but it's actually really, really, really versatile. And we crawl all over it like monkeys to get pretty much any different angles that we want to. Okay, all right. So I want to talk to you about a few things. For starters, I want to introduce you to my team. This is my team. I love these people. They're amazing. I've been with the Weather Channel since 2006, very long time. I've worked in 3 different departments, and now I'm currently in the digital department, which is my favorite department, and I'm not just saying that because they pay me. This is such an incredible group of people. So we only have 42 people, and I say we're small but mighty. On my shift, I make anywhere between 10 and 12 videos a day. So my face is on that app 50 to 60 times per week. And that doesn't even count all the text videos that our editors are producing. We've got writers on the team. So we were purchased by IBM in 2016. IBM initially they were after the data. I don't know if they knew what they were in store for when they acquired a TV part of it too. But they were very happy because within our team, they've been able to have some things happen that they didn't expect. We have a team group up in New York that primarily produces documentaries. So IBM won an Emmy for the first time. So they were really excited about that. They were also really excited to find out that our viewership is quite high. Our average daily views in 2019, 5.4 million. Sometimes much higher, sometimes a little lower. Again, that's just the average. The biggest day of video attempts, however, in 2019 was September the 2nd, 47.2 million views in a single day. Okay, quiz. Does anybody know what was happening on that day? Anybody want to take a guess? Hurricane, yes. Yeah, hurricane. It wasn't Harvey, though. It was Dorian. So on September 1st, as you take a look at this timeline, that was the day that Dorian reached peak intensity as a Category 5 with 185 mile per hour winds. I just felt sick to my stomach when I saw that happen. And we knew once it started turning that it was likely going to go into the Bahamas. We were hoping maybe it might not do that. There's always a chance that the forecast models might, not see something, even though they're getting better. And that's what I'm here to talk to you about today, is tech improvements in weather. But on September 2nd, pictures tell the story in a way, words do not. As you can tell, I still have a hard time talking about it. It's really tough. But we cover a lot of different topics: hurricanes, tornadoes, winter storms, wildfires. Anybody here from Australia? Anybody? No, I was just gonna say my heart is with you. Oh my gosh. Earthquakes, heat waves, volcanic eruptions, extreme drought, flash flooding, eco-climate, viral trending, celestial events. Sometimes I cover all of that in just a single week. So, I mean, it's like throw a dart at the wall. That's what I'm going to cover today. The tone of how a story is delivered is key in my business. I always try to tell people when they're first starting out in this business, if you see something interesting on radar and satellite, it's really easy to kind of geek out over these incredible satellite images. But the last thing you want to do is go on the air and be like, oh my gosh, look at this storm. This is absolutely amazing. Oh my God! Because that storm could be doing damage and possibly killing people. So you have to be very, very cognizant of your tone. In the field, I think this goes without saying. However, I have seen it not be done. You have to be respectful. You are meeting the most wonderful people, sometimes on the worst day of their lives. Covering aftermath, it's so hard. And let me tell you, since I became a mom, I've got a 6-year-old and a 2-year-old, it becomes a lot harder for me to go out and do aftermath stories. Mother Nature does not choose sides. Mother Nature does not care if you are rich or if you're poor, or if you are 8 months old or 80 years old. It can still happen. Here's a look at an EF4 I covered back in Lee County, Alabama.
We're here in Lee County, Alabama, one of the locations that took a huge hit from Sunday's storms. Now, look around and you can see from the ground, you see a lot of scenes like this, twisted metal, trees, but when you go up into the sky and get this bird's eye view, this is when it really takes your breath away, the scope of the damage. And again, this is just one location out of many that was hard hit.
23 people died that day. Actually I was out the day after. This is from the day after, but 23 people died the day before. I interviewed a 20-year-old young man who saw a dead body for the first time. That type of innocence should not be lost, And that was hard for him. And I told him, you don't have to do this. You don't have to do this. He said, no. We have to tell people what happened here. A lot of people find it cathartic to talk about it and tell their story and let people around the world know what's happened in their area. I mean, nobody wants their community put on the map because of a disaster. But, it is a way to to reach folks, and some people, you know, they do want to talk about it. I'm very respectful, very, very respectful of people. If you tell me, I can't, I'm sorry, I can't, I'm just gonna give you a hug and walk away, okay? So I take weather really, really seriously, but not everything that we report is bad weather. We talk about newly published scientific studies. That's always really fun. Animal stories, we call it crazimals, because who doesn't love seeing a panda playing around in the snow, right? We also do some human interest stories, which I love, and I have some pictures of this one that I was just so inspired by. So there's an artist named Shane Grammer, and you should look at his work. So the guy basically, he paints sets during the day or during the week for his day job at some of the theme parks in California. But on the side, he's a graffiti artist. And when the fires happened in Paradise, California, afterwards, he went in and painted on the burnt down relics within the area. So you see that used to be a chimney on the top one. He called that Beauty Among the Ashes. The one on the bottom is called Tomorrow's Dream, and basically he took like plastic wrapped and, you know, stretched it between 20 feet between two trees, and then did that with spray paint. And you see that face is overlooking so much acreage that was burned down behind him. It just never occurred to me that that could be used as a canvas. And I think that that's why I was so mesmerized and struck by it. So he really gave back to the community that was hurting so badly. I mean, they needed it. And a lot of people were just so grateful. And he did it on his own time. He did it on his own time. Weather has a lot of sides. We just talked about the scary, devastating, and deadly sides, but it's also breathtakingly beautiful. And then there's my personal favorite kind of weather, which is weather phenomena. I love the strange and unusual, and it kind of makes me think of that quote from Beetlejuice. You guys seen Beetlejuice? I myself am strange and unusual, said Lydia Dietz. Anyway, take a look at this video. You might recognize the place.
You are not going to want to take your eyes off of these clouds. They are so beautiful, drool-worthy gorgeous, but they do have a dirty secret, which we're going to talk about in just a sec. Now, the technical term for them is nacreous or polar stratospheric clouds, but that doesn't exactly roll off the tongue, though, does it? The slang name, however, is very fitting, mother of pearl clouds. And they can be seen in the polar regions of the world and form much higher than most clouds. And it must be incredibly cold. I mean, really cold. The temperature in the stratosphere has to be minus 108 degrees Fahrenheit. And when that happens, any moisture that's up there, well, it turns into ice crystals. And then the sun's rays will bounce off of these ice crystals as the sun is either rising or setting. Now, that beautiful rainbow effect, which is the result that we're all seeing in this video, is called cloud iridescence. And sometimes these are mistaken for the northern lights, but nope, they are two very different things and they are not related. As for them having that dirty secret, well, these clouds contribute to the breakdown of the ozone layer, where they're basically triggering a chemical reaction. Now, to be fair, they are not the biggest threat to the ozone. Human activity is a far bigger problem.
All right, so that video was taken about 600 miles north of here. So if anybody wants to go on a nacreous cloud hunt after this, please let me know, but we're gonna have to travel very, very far away. So I love stuff like that. And guys, if you see something cool and you wanna share it, I've got that email address. If you wanna snap a picture of it, I can give it to you. I'll be over at the IBM booth afterwards too. But we love submissions and we get some really, really cool stuff because everybody is a photographer now. Yes, we partner with Storm Chasers, but the entire world is our photographer. Have you heard of the term UGC? Yeah, user-generated content. Yep. So we rely on UGC. We work with some offices that we can buy stuff from. Newsflare, Viral Hog. I don't know if you've heard of those companies. But whenever they get weather phenomena, I'm like, I want to do that story. Please, 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 give me that story. Give me that story. Because I love it. I love clouds so much. I don't know if we have any Game of Thrones fans in the room, but there was a guy that I worked with named Wisdom Udo, and he used to call me Mother of Clouds. Because we would always talk about Game of Thrones in the break room. But I just love weather phenomena. These pictures are from Weather Underground. If you're looking for a cool gift idea, You can download these pictures for free and then just get them like printed out. I actually decorated our makeup room at work with these, and I actually have copies in my living room too, just because I think they're gorgeous. There's actually 16 kinds. All right, now let's talk about weather phenomena I'm probably never gonna report on, and I'm okay with that. Sharknado, anyone? Yeah, when that happens, I'm definitely running somewhere. But, you know, weather people do like to have fun, too. I love that the Seattle Weather Office just a few weeks ago put, you know, in the weather that keeps vampires happy category. And, of course, that was an ode to Forks, where the series Twilight took place. All right, now the main point. I know I took a little bit longer to get to this than I expected, but I'm just having such a great time up here, so forgive me. JFocus is just awesome. All right, let's talk about the link. We actually have more in common than you think. Digital media broadcaster, coders, and developers. All right, so here is a look at a flow chart that I designed myself. So I built this, and with the help of a couple of folks from my office, Danella Cohen and Todd Eaton, got to give them a shout out. Now, Todd Eaton is our head of DevOps, super nice guy. And I asked him, I was like, can you provide me like a good picture of engineers? And I had picked this one, but he suggested this instead. Heavy metal engineers, woo! All right, so I hope you guys can follow this from left to right. I know it's a little bit of a busy graphic. This is probably the most populated graphic that I have. But there's me with my on-camera crew. There's actually 5 of us. Kate was not feeling well that day, I believe, but that's one of our very rare group pictures where we all get to be together, because usually we're overlapping shifts. Dominica works the morning shift. She's the gal in the yellow dress. There's me in the green. There's Ari, and then there's Heather, and then we have Miss Kate, who generally does our eco pieces. That is her passion, eco and climate. So we feed into the editorial side, and then we go into video production, which of course then goes into the CMS, content management system. I know you guys are familiar with Drupal, Calliope, but it all feeds back around to DevOps and journalists and analysis. And in terms of us, you know, you notice this bubble on the right, storytelling for us, but for DevOps, it's technology, speed, consistency across all platforms and devices, which equals customer satisfaction. Todd Eaton, who I was just telling you about, just did a lecture on need for speed, about how they improved the speed of the website. Many of you here have probably been asked, I need you to make this website run faster. I need you to make this app run faster, because if people see things that are taking too long to load, whoosh, they are gone. They are absolutely gone. So online media is growing and here to stay, and especially in the digital space. And I want to tell you just a really quick story. So back in 2009, when I first started doing digital media, and this was initially just back in our old Weather Channel building. I think I forgot to mention that IBM did not buy the TV side. They just bought, well, pretty much everything else, including us in the digital space. But in 2009, pre-IBM purchase, we were actually asked to start doing mobile and web products. And there was a makeup artist who actually refused to do my makeup, because she's like, digital, nobody's gonna see that. And while it was quite mean, she actually did me a favor, because I had to learn how to do my own makeup. So I had to do my own makeup. Nowadays, I don't have the luxury of a makeup artist. But, you know, my mom's the type of person who I said, honey, you gotta make lemonade out of lemons sometime. And that's what I did. But, you know, right now we're pretty specialized in what we do. It used to be that people would come out of journalism school. They needed to know how to not just write editorial or broadcast, they also needed to know how to code. That's not required anymore. So we're really specialized. And so now, as we just talked about in the flowchart, we work independently, but we still have to understand each other's roles and, of course, how we support one another. You know, we're able to reach people on their phones and their laptops. That has changed video broadcast of today. We talked about where the advertising dollars are going. But here's what we know at this point from our analytics. And we have this just wonderful young lady named Melissa, who I adore. And she studies analytics, and she finds a lot of interesting things. So we know that people want a broad variety of topics. They generally want it under a minute. 55 seconds is generally the sweet spot. And if they want more statistics, we do give them that option. But she's also been able to find some interesting things, like if I turn my back to the camera to start pointing at the map, drop-off. We can actually track the drop-off rate. So within a minute story, we can find out how many people dropped off at 35 seconds, 45 seconds, or who made it to the end. So we do track the completion rates. But as I mentioned, there are some people that are just hungry for statistics. I mean, it's like, do you remember that movie Short Circuit? Data, 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 data. You know, some people just love that. And that's where these guys come in. And I have to brag on them. I love these people so much. This is Weather.com's content meteorologist. I lovingly call them the stat rats. Okay, I have so much respect for these guys. They pull up just some of the statistics from years past, and it's like, oh, you want to know what was happening on January 3rd, 1902? I'll get that for you. So we all work in part with each other. Here's what I'm going to say to you. You know, when we first started doing the digital stuff, we were kind of just trying to figure out what worked, and we were trying all sorts of different stuff. You gotta be willing to experiment. You gotta be willing to make mistakes. I love this quote by Dr. Martin Luther King Jr. Faith is taking the first step, even when you don't see the whole staircase. And I mean, really, how often do we see the whole staircase? Not that often. I try new stuff. I fall flat on my face all the time. I tried to do a video about Maverick Waves a couple weeks ago, and I was like, oh gosh, this could have been done better. And so we have a meeting now every other week where we talk about videos, and I offered myself up as a sacrificial lamb, which is hard to do, especially amongst your peers. And I said, look, I feel like I could have done this video better. And, you know, everybody started, you know, analyzing it. And I take that feedback because I know that Maverick Waves are going to come along again. So I want to be able to do it better the next time around. All right, speaking of doing things better, let's talk technology at its best. Ready for another umbrella game? Anybody? So I work for IBM, also known as the land of acronyms. And we, of course, have our own acronyms in the weather world. But one of the newer ones that we're really excited to talk about is GRAPH. Does anybody want to take a crack at what it stands for? You guys are tough. I don't see any hand raising. All right, I'll just go ahead and tell you. It's Global High Resolution Atmospheric Forecasting Center. You were so close, so close. But before I talk about GRAPH, I want to back up to a little bit before now. So think about it. You know, we've been saying this for years. We have seen advancements in medicine. We've seen advancements in how we communicate. We live on our phones. We've seen advancements in home security. Everybody's got a Ring doorbell now, and online security, and just everything. But we just needed to see more in the weather field. Big weather tech needed a serious upgrade. We've seen some great advancements. So NOAA launched GOES 16 back in November of 2016, and that offered greater resolution, also faster. Oh, I'm sorry, there's a typo there. Faster, 5 times faster, not faster, than before. And then it actually got its new GOES East position, and we were able to see severe storms, wildfires, hurricanes, all of this updated information in real time 24/7. I think this really shows it to you, though. This is a side-by-side comparison. GOES 16 on the left, GOES 13 on the right. I mean, it is incredible. And this was actually taken at the same time, on the same day, by both of those satellites. So it really is amazing. So that was incredible. It happened at a crucial time. 2017 was a year of horrible hurricanes. We had Harvey, Irma, Maria, and that data from GOES 16 let us better predict the rain that Harvey would produce. Harvey is a hurricane that rained its guts out over Texas in particular. A lot of Louisiana got hit very, very hard with rain. Top rainfall total, 60 inches in Nederland, Texas. Over just a very short day span, 60 inches, okay? Like, I'm 5'2". That's basically the equivalent of me, but it doesn't all just, you know, stack up. It just goes everywhere. So the flooding was really, really bad. Just want to show you this quick image. This just still amazes me. I mean, look at that thing. It's just massive, just massive. Another one that kind of made my stomach hurt, for sure. But going back to GRAPH, you know, NOAA's on this mission. IBM partnering with NCAR, National Center for Atmospheric Research. They're on this mission that everybody deserves access to accurate and reliable weather information. There are so many people around the world, oh my gosh, we have no idea how lucky we are. We have no idea. There are so many people that they either have really poor access or no access at all, even worse. So this has obviously got to change if we're going to protect life and property. Weather continues to be so impactful. I mean, every year I just feel like I'm talking about an increased number of billion-dollar disasters across the globe. 2018, India had the worst flood in 100 years. So this is about just helping people, families, farmers, power outages, safety, just in general for everybody. And this particular model, which by the way, is completely free, okay? I'm not trying to sell anything here. It's completely free. You can pull it up and you will see that amazing resolution in your phone, which I'll show you the comparison to. So it's got 5-minute output versus 1 hour, and it updates every hour versus every 6 to 12 hours. It's using the Power 9 GPU accelerated supercomputer, which is really, really cool. And I want to show you this. So this is what we generally have right now, 10 kilometers. You take it down to 3 kilometers. Now, if you notice up there, look at all those gaps. You see all those gaps. And now, with graph, this kind of gets knit. It's kind of like knitting together mesh, okay? And where we, especially you see at the top, where we thought, people might just be getting some pockets of light rain before, now, if you kind of look at the top and you go over to 3 kilometers, you see that they're absolutely getting hammered. That is some serious rain coming down, probably some hail. So this is huge. This is made possible by first of its kind weather model. It is the first weather model to run on a GPU accelerated supercomputer. To me, one of the most amazing things about it is that it runs 5 to 6 times faster, but it's actually less expensive. Yeah, so it's amazing. But again, this is something that people don't have to pay for. People can access it right now, okay? I want to show you this video really quick. I think it's going to explain things to you a little bit better.
The raw power of weather is easy to see. But look closer. This isn't just weather, it's weather data. Data that feeds the forecast, that generates the insights, that power the world around us. Weather insights help put food on the table, keep the lights on, get us home safely. Yet hundreds of millions of people lack access to a reliable forecast. Until now. The Weather Company, an IBM business, has developed global high-resolution atmospheric forecasting. Driven by IBM Power 9 supercomputing, IBM Graph maps weather data more frequently and at 3 times higher resolution to help generate the world's most accurate forecast, driving better decisions for parents, pilots, governments, everywhere on Earth. Helping farmers in Kenya grow more food with less water. Turning media companies in Australia into public safety companies. Turning power companies in India into outage prediction companies. We believe in weather for all, so that wherever you go, whatever you do, weather looks, sounds, feels transformative. The Weather Company and IBM, we power better decisions, so you can power a better world.
Yeah. I'd be excited about this regardless of whether or not I worked for IBM. I mean, it is just so exciting. So this is all being done by a global network of weather data. I love that the computers are named Dais, named for an ancient god of the daytime sky. But this is far from over. This project is very much ongoing. There are more and more sensors being added to airplanes that are going to be able to get us data over places that we haven't been able to see it before, deserts, tropical rainforest, all sorts of amazing things. And eventually everybody's going to be working towards possibly, and of course this will have to involve permission, something to experiment with is a possibility of seeing people if they will say yes to letting us use their phones to get barometric pressure readings. And barometric pressure is huge. There's actually a new study that just came out the other week from Colorado State University. Dr. Phil Klotzbach, very well known in studying hurricanes. He's actually suggesting to change the Saffir-Simpson scale, which is the hurricane rating system, from sustained wind speeds to pressure. So that's a really new, interesting study. But I want to talk to you about some other stuff. Okay, so I love comics. I know a lot of you probably love comics too. Spider-Man. I have a little crush. My husband knows, it's okay. But that's me with Spidey at Universal Studios. I love that line, with great power comes great responsibility. And I do believe that coders and developers, you're a new breed of hero. Like, you probably never thought of yourself as a first responder, but now you are. Your weapon of choice, it's a keyboard. I'm telling you, look, as a broadcaster, I really don't take myself that seriously. It's not like I'm curing cancer. I'm not. But there are people and supercomputers out there that are sure as heck trying. My skill set is storytelling, and I'm really proud to report on that stuff that everybody in this room is contributing to. Here's how you can contribute even more if you want. Again, I will say this over and over to you in the next couple of days. You just have no idea how special you are. I don't know if you get told that enough, but you really are. And there's this initiative called Code in Response that IBM partnered up with the David Clark Foundation, calling on the world's 24 million developers to use open source technology to help communities in need. And so this is about bringing open source solutions across the world to everybody, okay? This is not checkbook philanthropy. Again, crafting solutions that work on the local level, that have the ability to scale and help any community anywhere. This is my last video for you. This is a documentary which is currently available, streaming on Amazon and Apple. The whole thing is about, I want to say an hour and 15 minutes or so, but here's a look at the trailer.
Planet's going through a time of change. It's been a horrific year. It's scary.
When the earthquake happened, I could just hear people screaming. I felt how an animal would feel when we destroy its home.
So it's up 18 inches in the house. That's my lower level right there.
All signs are pointing towards the old phrase that this is the new normal.
The howling of the wind is very scary. I just started crying, like, when is this going to stop?
Last year was record-breaking in the acreages that were burned, and we already surpassed that this year.
There are natural challenges and disasters that we perhaps can't change. Somebody needs to say, let's do this different, let's do this better.
Empathy is a very key part of creation, because only when you listen, you can respond.
How grandly are we willing to act?
Code is a form of poetry, but trying to solve a problem.
This is a call to action.
How can technology I build today affect people around the world generations from now? Mobile app that would give you access to data in an offline mode.
Goosebumps every time I see it. Every time I see it. All right. let's talk about past winners, because this is a fairly new initiative. 2018, it was Project OWL, which stands for Organization, Whereabouts, and Logistics. And that little thing that you see buried in the sand is called a duck device. And so they have papa ducks and mama ducks that are basically trying to talk to each other. And the first place that they went to was Puerto Rico, and they've actually since started having students help with them to deploy and install these devices. After Hurricane Maria, nobody could get communication out. There's a very well-known band out there. Have any of you guys heard of Zach Brown Band? Zach Brown Band? Yeah, they're awesome. The drummer, Danny De Los Reyes, he lives in the Atlanta area, and I was able to interview him. And Danny is from Puerto Rico, and his mom still lives there, and Mama Matilda, and he couldn't reach her. I mean, this is literally a rock star with more disposable income than certainly I have, and he wasn't able to get to her for 3 days. And I remember interviewing him and him talking about that and choking up. And of course, when a grown man starts crying, I'm going to start crying too. But nobody wants to see that happen again. People should not have to be writing chalk on their roofs saying, "Help me, this is what I need, send this." They need to be able to communicate. And these duck devices are this very interesting network. There's more information about Project OWL out there. It's really cool. It's really cool. I don't know how the judges choose the winners. There are so many submissions to this, and they're all amazing. This was the 2019 winner, Prometeo. And this team was made up of a firefighter, a nurse, and 3 IT professionals. And what they wanted to do was build a device that would basically strap to a firefighter's arm, and you see it in the picture below, and it looks at the firefighter's health and safety in real time. I have so much respect for firefighters too. I mean, they put their lives on the line every single day. It is absolutely incredible what they do. So, who's going to be the winner in 2020? It could be you. It could be in this very room. If you win, you better tweet me and tell me, because I'm going to Venmo you money and buy you dinner. I will be so excited for you. Seriously, if it's one of you, you better tell me, or I'm coming after you. I'm kidding. So in just a few weeks, the 2020 Call for Code Challenge is going to be released. Last year, the submission window opened up in March. But again, that's something really exciting that we are very much looking forward to. In closing, we're all connected by weather, even if you dress like this guy. I really hope one of you is going to be dressed like this at the dinner later tonight. That'd be awesome. Thank you guys so much for having me. This has been a blast. I'm so excited for you. I hope this has pumped you up a little bit about JFocus 2020. Matthias and his team have worked so hard to bring you guys all sorts of new and interesting information. Please stop by and see me at the IBM booth and talk to me. If you have ideas, if you just want to say hi, talk to me about metal music or Game of Thrones or whatever, please come over. Again, that's a look at our video submissions. If you see something cool, don't put yourself in harm's way. Please do not. It's not worth it. Not worth it. But if you see something cool like those mother of pearl clouds, send it to us and we'll feature you. We always give our people credit in the upper right-hand corner. Thanks again, guys. It's been a pleasure.
Thank you, Danielle. It's fantastic. It's fascinating to hear you share your information and your experience about the weather. Thank you very much.
Thank you for having me.
But I'm not supposed to be here. I'm looking for Matthias. Have you seen him?
We have to find him. I mean, I have to give him his forecast for JFocus. I mean, partly geeky with 100% chance of awesomeness.
That's good. That's good. Where are you, Matthias? Where are you? He's gone. Maybe he crashed.
I hope not.
Burned. Or maybe he...
I'm coming.
There you are.
Oh,
Matthias.
yay.
Thank you very much.
Thank goodness.
There he is, Matthias, finally. Thank you.
Thank you so much.
So why don't we give another round of applause for Daniel Banks, and then Matthias will introduce.
Very kind.
Come with me.
Hi guys, welcome. Let's just continue with the show immediately. So our next speaker is a developer I met about 15 years ago, and he said, I'm going to write a new database engine. And I was like, there are a few. How will that work? But he made it. He really did. So, and he was here 10 years ago, and now he is back. Welcome on stage, Emil Eifrim.
All right. Good morning, Stockholm. Really? All right, let's try this. God morgon, Stockholm. All right. So let's try this. How many in here speak Swedish? Raise your hand. Probably 80, 90, 85%. How many in here do not speak Swedish? 5%. I feel like I'm going to go into a different, like a Venn diagram talk here. It's like Swedish, not Swedish, should be 100% kind of a thing. That's actually not what I'm going to be talking about. Today, I'm going to be talking about something different. I'm going to be talking about this. Nice couple of fellas over there. So my name is, well, for the 80% Emil Eifrim, and for the 5% Emil Eifrim. I'm the CEO and founder of a company called Neo4j, which was started here in Sweden. We have our engineering HQ in Malmö, which is where we got started, and our headquarters in Silicon Valley, which is where I moved about 8-9 years ago, something like that. And I'm going to talk to you about the Panama Papers and how we got embedded in what ended up being one of the biggest news stories of 2016. Even though 2016 was an interesting year because we ended up with both Trump and Brexit. But prior to all that, the Panama Papers happened. And we are a small technology company, so it's kind of odd for us to get embedded and ultimately become very essential to a story like this. And so I'll share a little bit about the kind of behind the scenes from that story. Before that, though, I only have one ground rule for all my talks. It was the same 10 years ago when I spoke at jfokus for the first time back in 2010. It's the same today, which is I do not want your undivided attention. You all have phones, laptops. Apparently the Wi-Fi supposedly works here. Let's try it out. Tweet about this. Let me know if I'm doing well, if I'm doing poorly. The only thing that I ask of you is that you use the jfocus hashtag and the Neo4j hashtag, because we monitor at least the Neo4j hashtag religiously. So that's it. The Panama Papers. the biggest news story of 2016, at least for the first half of 2016. And just to give you a little bit of a reminder, because this was a while ago, this story, like many stories, like some of the stories we heard this morning, of course, starts with a few heroes. And there are several heroes in this story. I'm going to start calling out 3. The first 2 are 2 journalists, both of them confusingly named Obermeier, last name, at a local newspaper in Munich, in München, Germany, called Süddeutsche Zeitung. Süddeutsche Zeitung, a very high-quality newspaper with a great investigative journalism team. And both of the Obermeiers were in this journalism team. And the third hero is an anonymous whistleblower. That's the one that you saw in the video, called John Doe. Still, 4 years later, we have no idea who it is. He or she is only known as John Doe. And this John Doe contacted the Süddeutsche Zeitung, these 2 journalists, and reached out to them and said basically what you saw in that video, which is, I work at a law firm. I don't know if he said that he worked at the law firm, but he said he had access to information from a particular law firm in the Panama called Mossack Fonseca. And he said, I have all of their internal data dating back to their year of origin, 1977, all the way up until 2016. Are you interested in this? And they said, yes, of course. And they asked him, why are you doing this? Because I want to expose what these guys are doing. And so they took this data, ended up being 2.6 terabytes of data that they got from John Doe. And then they said, okay, how are we going to analyze this? They realized that they couldn't do this alone, or rather, this was a global story. This was not a local Munich story, a local Germany story. So in order for this to have the most impact, they should really collaborate with journalists all over the world. So they reached out to this organization called the ICIJ, the International Consortium of Investigative Journalists, which is based in DC. It's a small team who's locally employed by them, about 15 people at the time. But they work with hundreds of journalists from all over the world. And the goal is to make more efficient cross-border investigations. And what may not be intuitive and obvious to all of us is that journalism is actually fairly competitive. So if you get an interesting lead for a story, you're very unlikely to share that with your friends at some other newspaper. And why? Because they're actually your competitors, right? You want to leak that, you want to get that story out earlier than they want to. So it's very counterintuitive and very countercultural for the Obermeiers to actually do this. But they ended up doing it. They reached out to the ICIJ. They took a look at that data and said, this is an amazingly interesting data set. We need to try to look at this from a global perspective. And so why was this interesting? Well, it turns out that Mossack Fonseca, as a law firm, they were specialized in what's called offshore tax havens. And so what that means is that these are jurisdictions, these are countries where you don't have a lot of visibility into them and where there's typically low or no taxes, right? So they were used for offshore tax planning. And offshore tax planning can be used for legal tax planning purposes. It's perfectly fine to do that. But it can also be used for illegal tax evasion, right? So if you have a lot of money that you got in some way, and you want to hide that from the authorities, you stick it into an account, you set up an entity in Panama or the Bahamas or the BVI, the British Virgin Islands, something like this, and you use a law firm like Mossack Fonseca to do that. So the ICIJ started looking at this data, and ultimately they ended up concluding a number of really interesting things. So here's a chronology. In the early 2015, John Doe reached out to the Süddeutsche Zeitung. They contacted the ICIJ. They started digging into the data and activating their broad network, their graph of journalists from all over the world, and they started investigating this. And then in April of 2016, the news leaked. The news were published. This is Edward Snowden tweeting about it, the biggest leak in the history of data journalism in April of 2016. So let's take a little bit of a peek under the hood of what is actually going on here from a technology perspective. So first of all, this was a massive data set, right? 2.6 terabytes. Just to give you some context of 2.6 terabytes from a journalistic perspective, here are some other famous journalistic leaks. And you see their sizes, and then you see the Panama Papers data dump. And in our world, we think of terabytes, and that's like, my phone can probably do a terabyte these days, right? Or at least the next version of my phone, right? Because terabytes sounds like, actually we do that all the time, even petabytes type scale. But if you think about it, the data sets that you've used of that size, they're almost always, I would guess that they're actually always going to be either machine generated or generated as a side effect of some fairly rudimentary activity by a large volume of people. So think clickstream data, for example, for the latter, or sensor data as an example of the former, right? This data was a bunch of emails dating back to, I guess, not 1977, right, but whatever, 80s, early 90s. They were forms that people had filled out by hand. They were passport scans and things like that, right? So very manual, human-generated data that all built up all the way up to 2.6 terabytes. So a massive data set, right? And then the question is, okay, so how do you make sense of all of that, right? So this is what the team looked like. They ended up activating almost 400 journalists worldwide, 80 countries. This was a truly global operation, right? Working for over 100 media organizations and tons of local folks here in Sweden, in the US, globally all over the world. Supporting all of that was a team of 3 developers and 3 data journalists, right? A really, really tiny team that ended up supporting hundreds of journalists looking through all of this information, right? And an almost impossible task. So the question then is, how were they able to pull this off? Well, because they were so tiny, the only way they could pull it off was by using a lot of off-the-shelf technologies, right? And what was interesting, one of the many things that is interesting with the Panama Papers story, but in particular from a technology perspective, is that this leak technically could have happened 10 years earlier in 2006. If that would have happened in 2006, none of the stories would ever have been published, because the technology was not available to a tiny team of 3, 5, 6, 12 people. You needed to be at Facebook scale or at Google scale or something like that to be able to work with that type of data. But it happened in 2016, and they were able to pull together a number of very interesting open source components to make this happen. At a very high level, this is what they wanted to accomplish from an architecture perspective. They had the raw files, again, emails, passport scans, government forms. I don't know if you noticed in the chart before, they had something that they call database formats, which is basically CSV dumps of the database that was internal to the law firm. So they had all that, and they wanted to take that data, and they wanted to somehow being able to look into it and try to find out if there are stories here, newsworthy stories worthy of writing about. So with the stuff that was already in metadata, so think emails where you have a from and a to and a subject, it was actually pretty easy to pull that out, as you can imagine. You extracted the metadata, you stored that in a database. Obviously for things like PDFs, passport scans, things like that, you had to run it through some kind of OCR process to get the raw data, the raw text, which you then would enter into the database. And then ultimately, once you have it all in some kind of a database, you can start looking into this and make it, from the developer's perspective, make it available to their journalists, right? So that's at a high level. So they did that, pulled together a number of open source tools for ETLs, for OCRing, and so on and so forth. And then they put it into this database, which obviously, that's where we came into it. But the first thing they did, actually, when they had that data, is that they just put it into a simple Lucene index, right? So the first thing they wanted to achieve was, hey, let me just search this data, right? So they put together this, or actually they reused this open source tool called Blacklight, which is typically used by libraries, like by the ABM market, so libraries and museums and folks like that. They modified that a little bit, but think of this just as a UX on top of Lucene, or in this case on top of Solar. Fairly easy, but all of a sudden you could search across this entire data set, right, in free text, which is actually really powerful. But what they learned pretty quickly was that they searched for kind of an interesting name, maybe a politician in their home country or something like that, and they ended up getting thousands, tens of thousands of hits, right? For those of you, I guess Matthias said that we first met 50 years ago, which isn't quite true. But for those of you who were around, in the early days of the internet, there was a search engine called AltaVista. Who here remembers AltaVista? Wow. All right. Who here does not remember AltaVista? Oh my! Oh, that was like 50%. Man. Okay, we need to. I'm gonna do the Venn diagram keynote tutorial next year at JFocus. So with AltaVista, which is one of the most popular search engines in the early days of the internet, it became popular because it was super fast and it was very powerful and all that good stuff. But after a while, the AltaVista effect kicked in, as it became known, which was that no matter what you searched for, you got thousands of hits, right? And initially, you would think that's a good thing, except there were thousands of hits, and like you couldn't find any relevant information, right? And that's ultimately what Google came around and figured out how to solve. And how did Google do this? Well, Google had exactly the same approach to web search as AltaVista did. Let's crawl the entire web. Let's download that into our data center. Let's search. So if there's a web page that says JFocus, and I search for JFocus, if in the text it says JFocus, I search for JFocus, I'm going to serve up that page, right? But what Google realized was that, hey, you know what? Let's do that. But in order to serve out the best search results, we're going to rank them, and rank them based on what? Based on how these documents are connected, right? So they chose a graph algorithm called eigenvector centrality that they made some tweaks to and they named it PageRank after Larry Page, one of the two inventors. That was the key innovation that allowed Google to filter through these thousands or tens of thousands or millions, actually, of search hits on the web and filter out and rank the top 10 ones. And we all know that if you're on the first page of Google versus the second or third or fourth, it's a huge difference, right? Because Google just made that so awesome, so awesomely relevant by using this connected data view of that information that there's no reason usually to even go beyond page 1, right? So the ICIJ team had a similar revelation where they said that, we have too many hits here, but we should start looking at this in a different way. So taking a step back, where are we now? So we've had they've gotten all this information, right? And they've been able to, through a series of advanced steps, extract it into 11.5 million documents, right? And they want to try to make sense of that. If we take a step away from technology for a moment and just think about investigative journalism. Investigative journalism is actually about finding patterns, right? You try to find unintuitive patterns or patterns that some people try to find, right? So let me talk to you a little bit about patterns. Here's an example of a pattern. You have a person. That person has an account in a bank, right? That is your pattern, right there. Yes. You nodded. Exactly. It's my pattern. It's everyone in here. Like, it's not a particularly interesting pattern. Even though you are particularly super interesting. This is a different pattern. We build on that same thing. Let's say that this person lives at an address over here. Another person is living at that address. That person is an officer in a company, and that company has a bank account in a known offshore tax haven. That is probably not true for you. It's not true for me either. But all of a sudden, this is a much more interesting pattern, right? And what if we could start finding those kinds of patterns in this massive data set, right? So In the graph world, obviously I grew up in graph databases. I tend to take a graph view of the world. It was my heart beat a little bit extra when Daniel talked about graph multiple times in the previous talk, although it was a different graph, but still, just the term made me really happy. In the graph world, we call these concepts the round circles here, then we call them nodes, right? And they're the nouns in your domain, so to speak, right? We call the arrows between them the connections, we call them relationships. And with key value properties on both nodes and on relationships, those are the fundamental building blocks, the primitives of graph databases. With that, you can model everything. Right? And what's really powerful is if you can take this model and you can put it into a data infrastructure that can scale not just to whatever 7 nodes here, but it can handle all the 11.5 million nodes or billions of nodes, in fact. That can create some really interesting opportunity to finding stories at a global scale. So, switching gears a little bit, the question is, what does this look like in practice? And I now realize that my computer has gotten suspended. I'm now going to go into a live demo. And the really good news is that even though my computer just got suspended, we all know that live demos always work. So I'm super confident nothing is going to break. All right, cool. Yes, I believe we can, you can see it. All right, let's launch into my screen, please. Sweet. All right. That looks great. We are off to a great start. All right, let's see if this works. It's still looking for Wi-Fi over here. I may have to do like an improvised song and dance version of this demo. Is that okay? So, all right, so I have the Panama Papers data here, and I'm going to search for an officer. Woo, I get data back. So officer is what in the Panama Papers data. It's basically what they call human beings, right? You're an officer of a company, for example, right? And so here's an example of a bunch of officers in here. You can zoom in, and all of a sudden you start seeing names. I don't know how visible this is for you, but you see some names here. It says the bearer on many of them, which is actually an artifact of the data. It is an old term for a type of shareholder that physically is carrying a token that means you're an owner of a company. And whoever is carrying that token is the actual owner of it, right? So you're not registered as a human being on it. There's no records anywhere. It's just whoever holds that physical piece. So that is what the bearer means. So this is data that is now put into Neo4j that ended up coming out of that 2.6 terabytes, the 11.5 million documents. And we can just search it right here, right? So we can take this interglobal construction thing, and we can look at some interesting stuff. We can say, for example, how are these two connected? Let's see if they are. Let's see if there's a shortest path between them. Yes. All right, sweet. So now all of a sudden, I don't know if this is visible on the big screen, we can see that these two random people that I chose, CN Limited and Intergalactic, are connected to each other through several intermediaries and law firms, and so somehow they belong to the same companies, right? That's the kind of stuff. Imagine that if you got back that list of 1,000 or 10,000 hits from the Alta Vista-like search, and you wanted to find something like this, it is probably doable. It just would take forever, right? And with this at their fingertips, the journalists were able to all of a sudden find all kinds of interesting things. So let's take an example of that. Let's see if I can clear this. Let's see here, Sigmundur. All right. Sigmundur David Gunnlaugsson. Sounds very Scandinavian, doesn't it? Does anyone recognize that name? All right, who is this? All right, shout louder. You can do it. Yes, the now former Prime Minister of Iceland. He was the Prime Minister of Iceland when the Panama Papers broke. So what ended up happening was that Sigmundur was the Prime Minister of Iceland. It turned out that he had been the shareholder of a company called Wintris. But if you look at the shareholder of data, this is very, very hard for you to make out probably. But you can see here that it says end date of that relationship. The relationship between Sigmundur and Wintris has an end date in December 2009, which is around the time, maybe it was exactly the year, when he became the prime minister or an active politician or something like that. So he had actually sold his shares then. So maybe that was fine, but it turns out that he also had a registered address here, Lukastig or something or another. And if you look at that, all of a sudden we see, wait, there's someone else who's living at that address, Anna Paulsdottir. And if we look at her, wait, all of a sudden, she is registered to Wintris as well. And she has two shareholder relationships. And then we can click on them and we see that this one started in 2007. And this one started exactly when Sigmundur's relationship ended. And so this tipped off the journalist that something fishy was going on here. Oh, because it turns out, I should have probably pointed that out. If you look at Wintris, oh, yeah, they had a bank account in the Panama, in an offshore tax haven. This was something that he had not disclosed. And he had tried to sell it to who subsequently turned out to be his wife for $1 or whatever, euro or an Icelandic krona. I don't know, for some low amount, on exactly the same date. So this was exposed in the Panama Papers. They were confronted actually by SVT, the Swedish public television, who was there together with some local journalists, and he ended up ultimately resigning over this fact. So, an interesting way to look at this data. Now, speaking of interesting, I picked on you before, so I'm not going to pick on you anymore. But let's see here. Front row is really dangerous. What's your name? All right. Okay, I'm not going to do that. Does anyone have a neighbor they want me to type in or something like that? Wow, that's probably not a good idea. I run an American company now, so I know what kind of liability that would. Donald Trump, that's an interesting one. Well, is this being recorded? Catch me afterwards. We'll talk afterwards. But we can look in Stockholm, right? So here are some of the addresses in Stockholm, right? We can zoom in, Magnevägen, Drottninggatan. We can start looking at what's going on at Drottninggatan. Oh, someone is actually registered here, whoever that is, right? And then we can, what did you say? Did you say Trump? I don't know what Trump Trading Limited is, but it sounds interesting, so we can find that. All right, let's see if this dude over here is related to this Trump thing over there. So we can find, is there a path between them? Shortest path? It turns out it is. Oh, there you go. So I'm going to zoom rapidly out of this right now and not go any further. But this is the kind of stuff it's that easy to do that when you put the data in a powerful database that can do things like finding patterns in data, right? And this is all public data. It's available. It exists off of the ICIJ website. Okay, good, yeah. Can you switch back to the presentation? It exists off of the ICIJ website, right? And actually off of the Neo4j website too. And I'll give you some links towards the end. Let's see how we're doing on time. I got carried away there with the whole Trump thing. So a few more minutes. Cool, so what this ended up being, again, was like this massive worldwide story, broke all over the world, that was the impact. They actually ended up winning the Pulitzer Prize, the ICIJ did, in 2017 for the Panama Papers story. It was an amazing moment. But probably most importantly was that it exposed a bunch of people who had money stuck away in ways that they had not publicly disclosed, right? Several of them were politicians, several of them were big, and important business leaders. One of the first things that happened when the Panama Papers broke was that the Neo4j engineer started looking for me in there. But luckily enough, I wasn't in there. So, all right, so that's fine, but what does this mean to you? So, I think to me, what's interesting about this story from a developer perspective, from a technology perspective, is what we alluded to before, which is that 10 years ago, this story would not have been possible, right? Because these three developers, these three data journalists, the only way they could make this happen was by using this really rich ecosystem of open source technologies and compute and storage off of these public cloud platforms, right, that are commoditized today. And with just that power at their fingertips, a few developers could impact something as huge as this. So that is my urge to all of you here. That is how easy it is. If these three people, these six people, could make this happen at a global scale, you can probably make something like that happen locally for you, for your company, or maybe even for public society. It used to be that this technology was only the property of these big web firms, right? Only at Google scale or at Twitter scale or at Facebook scale were you able to do this, but that is no longer true. The Panama Papers is available on Neo4j's site. We have a bunch of open source stuff. We have an open source community edition of our database. You can go and you can launch what we call a sandbox, which is purely just a tab in your web browser. And you can go there, you sign up with your social ID, and in a minute, you have a Neo4j instance running. You launch the sandbox, and bam, you have the Panama Papers right there. And you can start looking up your neighbor, or see if they're connected to Trump, or whatever it is that you want to do. There's a bunch of other sandboxes too, if you want to look at more typical graph database use cases like recommendation engines, or customer 360, or fraud detection. It's pre-populated with data sets to allow you to do that. So finally, I want to call, since this is a local conference, I don't usually give talks in Sweden anymore, but it's been fantastic to be here. We are always hiring. We are 300 people right now at Neo4j. We want to be 500 by the end of the year. We are hiring as many qualified developers as we possibly can. So if you think this is interesting, go to neo4j.com/jobs. We also have a booth here at the conference. We'll be here for the entire day. I'm going to be there for most of today, but colleagues will be here throughout the conference. Come up, talk to us, and most importantly, have a fantastic conference. Thank you, everyone.
You have to be on stage for this. Oh, they are already leaving. That's good. So I just want to say thank you.
Yes.
So for how long are you staying around?
At least for all of today, possibly tomorrow. Yes.
And will you be here for the party tonight as well?
Of course. If you show up in a Jedi costume, who's not going to be there?
This is a setup. What costume will you wear?
I'm always in all black.
So that should be Kylo Ren.
Kylo Ren.
Kylo Ren.
Yeah,
perfect.
Kylo Ren.
Okay, it's a fika break. Thank you. We'll be back soon. Thank you.
Awesome. Thanks, everyone.
there be like a time indicator on this screen? I mean, I have my laptop, of course, but...
Not with that. I was sitting there.
Okay.
And I have this.
Ready?
Ready if you are.
Vi är klara. Well, ladies and gentlemen, it's time for our next talk. I call myself a full stack developer, but here is a man that's trying to convince you backend developers to come over to the dark side. Matt Rabel.
So my boss thinks that I just came here to go skiing, so I do have to start off with a selfie to, prove to him that I was working. So let's pretend like you're all having a good time. Ready? 1, 2, 3. All right. So welcome. Today we'll be talking about a number of different items: JavaScript, TypeScript, build tools, JavaScript frameworks, CSS, front-end performance, and progressive web apps. But first, my name is Matt Rabel. I'm a hick from the sticks. I grew up in the backwoods of Montana with no electricity, no running water, and I had to walk 1.5 miles to the bus stop every day. And it felt like it was uphill both ways, but luckily I had Finnish ancestors, and so we had a sauna before a cabin, and we got to ski in the winter. So I learned how to ski Nordic style very well as a child. And I live in Denver, Colorado with my beautiful wife Trish and 2 awesome kids, Abby and Jack. I also have a middle child. His name is Hefe. I bought him off eBay in 2004 and spent 12 years restoring him. If you follow my blog, starting in about 2004, 2005, you might have seen the pictures. I always thought he was going to be done in 6 months. And man, I'm really good at hope because I always thought he was going to be done. I also have an expensive obsession with other Volkswagens. I have a VW Syncro there. His name is Stout and Hefe, so I like beer. I work for a company called Okta. My dad calls it Okra. Interesting story about Okta. When I was last at JFocus in 2017, on my way here, I had worked for a company called Stormpath, and I found out that Okta was buying us. I negotiated my current job in the lobby of the hotel right over there. So very special place for me here. We do authentication in the cloud, OAuth 2, SAML, OpenID Connect. But enough about me, let's learn a little more about you. How many people consider themselves back-end developers? I would say that's 95% of the room. How many people are doing Java? Same, 95%. Any .NET developers? We've got 3. Anyone doing Python? Got about 5. Node developers? Okay, that's about 10. Who writes code for UIs? Okay, so that's maybe 1/3 of the room. Who likes JavaScript? Okay, that's 40% of the room, and that's way better than it used to be 5 years ago. At a Java conference, you ask how many people like JavaScript, like no hands go up. So it's getting better. Who likes TypeScript? Okay, so about the same as JavaScript. All right. Who uses Angular? Okay, 1/3 of the room. Who uses React? Even less. Surprising. What about Vue? Any Vue developers? Okay, that's about a handful. Okay. So my web developer journey, I actually started doing web development before Netscape 1.0 even came out. So this was way back in like 1994. My dad turned me on to what's called a Slipknot browser, and it didn't even render images, right? You would type in, HTML, and it would, put up a nice page, but it didn't have support for images. I remember seeing the first image rendered in a commercial on TV and being like, wow, that's so cool. That Netscape thing looks pretty awesome. And then I got into Java in the late 90s, and then in the early 2000s, I got into struts. I'm sure many of you might have got into struts as well. Bad habit. I broke it quickly after a couple of years and got into Spring MVC, which I liked a lot. But then in the mid-2000s, I got back into JavaScript, and there was kind of a JavaScript renaissance at the time with jQuery. And so I stayed in the front end a little while, worked for LinkedIn for a while, which was a fun gig. But most of my career, I was independent. And I only became a developer advocate, like I said, in the lobby over there a few years ago. And now I get paid to, go around and speak at conferences and write example code and only test in Chrome. So it's really a great web developer journey. So I ask people, what is modern front-end web development? And a lot of times people think it's maybe mobile development. It might be HTML. Used to be HTML5, right? We don't have HTML6 yet. But it's mostly HTML, CSS, and JavaScript. But a lot of times it's also the frameworks. And so the web frameworks over the years, there's been a lot, right? And it started in the late 90s and blossomed in the early 2000s. And they used to make fun of us in Java for having so many web frameworks. And then JavaScript came along, and now we make fun of them. But the interesting thing is in Java, we came out with this great web framework in the mid-2000s that was going to solve everything. JSF. It started at the same time that jQuery came out, and Ajax came out, and Flex came out, and Spring came out. They all came out around the same time in 2004. So bad timing. But at the same time, you'll see there was still a lot of love for JSF in 2017. This is from a study that Rebel Labs did. But really, the JavaScript explosion or renaissance or frameworks really changed a lot. So this was back 2007, 8, 9. AngularJS was very popular in 2010. And I think this is a great depiction, this blog post about what it feels like to learn JavaScript. And this is as recent as 2016. And it can be very overwhelming. This is a blog post about this guy like going through all the build tools he has to learn, the frameworks he has to learn, whether he has to use hooks with React and all that kind of stuff. And what I want to take you back to is when you were first learning Java. When I first learned Java, it was the late 90s, early 2000s. And you know what I learned? I learned like servlets and JSPs and JDBC. If you were learning JavaScript today, that would be like learning the basic syntax, promises, and maybe how to write a UI. You wouldn't try to learn everything. You wouldn't try to learn the build tools. You wouldn't try to learn all that stuff. And I remember back when I was learning Java, I wasn't really overwhelmed. Right? I didn't see all the options and be like, I have to learn everything. And I think that's what people often see when they look at JavaScript. And so what I'm here today to teach you is the tools and techniques that you'll need for front-end development. And I want you to be excited like you were when you first learned Java, in the sense of not overwhelmed by all the options, but just focusing on the core things that you need to learn to be productive. And learning is really the ultimate skill. It's not knowing Angular, or React, or Struts, or Spring MVC, or Wicket, or any of the frameworks. It's really the ability to learn that's one of the greatest skills you can have as a programmer today. And how do you learn? Well, you got to be curious. So curiosity is the key. Are y'all curious? All right. Let's do some learning. So I'm going to start with ES6, ES7, and TypeScript. ES3 going back was actually released in 1999. And if you're a web developer back in the 90s, that was with IE6. And people look at IE6 and they're like, holy cow, what a terrible browser. But back in 1999, it was the coolest thing on earth. It was really a breath of fresh air, and it was great. But the problem was Microsoft didn't innovate for 10 more years. And ES5 wasn't actually released until 2009. And so ES6 is kind of a breath of fresh air for JavaScript, has modules and classes. It's also known as ECMAScript 2015, and it was released in June 2015, so that's been 5 years now. ES7, technically ECMAScript 2016, released in June 2016, and all it really had is an exponential operator and array prototype includes. So not a whole lot of innovation there. ES8 added async and await, which are kind of new features to the language, make it very easy if you're used to working with chained promises. It gets you away from that, makes things much easier. So with ECMAScript 5, all browsers have good support for it. ES6 classes, most of them. IE doesn't, but it's not supported anymore anyway, so who cares? But really, for Java developers and people that like strongly typed languages, TypeScript is where it's at. So it's got optional static typing, depending on how you define your linting files. You can, add certain types, or you don't have to. But this is just an example. You can install TypeScript using npm install. And this is a simple JavaScript function here. The only difference between it and normal JavaScript is you have that person defined as a string. And then you can run TSC, the TypeScript compiler, on that file and actually, compile it. Little known, you can actually use a TypeScript compiler on regular JavaScript files too. But it's more just about functions, it's more about classes. And this is not really so much a TypeScript example as it is an ES6 example. So this is a perfectly valid ES6 class. You can see it's export class bus. And the constructor there, you don't have overloaded constructors like you do in Java. You basically just have optional arguments. So that's what the what do you call it, Elvis operator there is, the cute little question mark colon. And then if you're using TypeScript, you actually don't even need that to set that local variable. It actually happens for you. So all you need is have that variable in the constructor, and it'll create a local private variable for you. And then the get and set is kind of like Java getters and setters, but the difference is you don't actually have a method name, get name, set name. You just call person.name, or in this case, bus.name equals. That calls the setter, and if you just print it out, then that calls the getter. And then you can do string interpolation on all that. So, pretty full-featured language. And again, most of this is actually JavaScript, not TypeScript. And I don't have the sound plugged in, so you won't be able to hear this, but there's actually an animated GIF here, and you can see if you just add TS check in Visual Studio Code, it'll actually, or VS Code, it'll do TypeScript syntax checking on your regular JavaScript file, so that can be very useful. But before you can write any code in TypeScript or ES6, you probably need a tool to make your code work in older browsers that support ES5, just in case you do have to support IE11. Not all of us are developer advocates, right? We have to work with real clients and real applications. So Node is a way to do that. And when I first was introduced to Node, I always thought it was like a back-end way of doing things. But turns out it's for front-end development a lot nowadays because you need to transpile or code or compile your TypeScript into JavaScript. So easiest way is just get it from nodejs.org. If you actually work on multiple Node applications that require different versions, then you can use MVM to switch between those. It works pretty well. But again, you probably only need this if you're doing like back-end development with Express or other Node frameworks, because on the front end, typically what I found is the latest version of Node will work with most front-end frameworks. So the front-end build tools, old school was Gulp. If you like Ant, you'll love Gulp. New school was System.js, and actually I just recently learned that System.js is around and used by a fair amount of folks. But it was the original build system used by Angular when they switched from AngularJS to Angular. And it actually had a whole bunch of code that was needed for it before they hid it behind like Angular CLI. So now what's hip is Webpack to this day, I believe, unless there's a new one that came along while I was, doing this talk. But if you want to do web dependencies, the old way used to be Bower. And what Bower would do is similar to Maven. It would just pull down the raw JavaScript files and put them in your project, but really nothing more than that. The new school is NPM, and Yarn is still kind of hip. Yarn basically took over from what NPM was doing and said, hey, we're going to add caching. And people were like, wow, that's cool. It's so much better and faster. So now they both do caching, and basically you do npm install or yarn add, and that's how you add new dependencies to your project. You'll notice from this slide that if you actually want to have a hip JavaScript build tool, you got to have a cool logo. So keep that in mind if you decide to write your own one. Something that's kind of come and still popular, but maybe not as popular as a couple years ago, is Yeoman. And this was a tool for generating web apps and having like basic testing infrastructure built in, the ability to start your app and make changes to it and it reload really quickly, helps you kickstart new projects. And what's happened since Yeoman was very popular is that a lot of the projects have actually created their own CLI. Even on the most popular Yeoman generator, jhipster, we've kind of hid it behind the scenes, so you just type jhipster instead of yo, jhipster. And the cool thing about the command yo, like when it was used for jhipster, you're like, yo, create me an app, right? Like it's a cool command name. I'm kind of sad to see it go. How many people have heard of browser sync? Okay, not too many. So this is worth the cost of admission, at least, for this talk. And I didn't plug in the sound, so I don't know if we'll get the sound on this one. But this is a demo here where it shows that if you modify HTML, CSS, or JavaScript in a file and you have browser sync running, this is, not only Firefox here, but we also have iOS Simulator, and we also have Safari. It'll reload all those browsers. And it'll even make it so if you scroll in one browser, it scrolls all those browsers. So if you have to do web development and support a number of different browsers, it's a very easy tool to use. One thing I've seen that's interesting, though, is if you're using Chrome, for instance, or even Firefox or Safari, and you have multiple tabs open, it will manipulate all those tabs. So beware of that. Just by default, that's kind of how it works. But it's a great tool to basically test in all kinds of different browsers. And you can use Gulp to do it. So the reason I show this example is because it's only a handful of lines of code, and you just point at where your directory is that has your files, and then you use Gulp watch. You watch for changes in those files, and then you tell browser sync to reload when any of those happen. So this also can lead to lack of testing on your front-end applications, just to warn you, because the change will happen so fast that you're like, wow, why bother write tests, right? I can see it working. And so that's something that happens to JavaScript developers. There was a study a few years ago that found that 75% of JavaScript developers did not write tests. And so it can be a dangerous habit to get into, but if you have 100 pages, then you're going to want tests for those. So Webpack is a modern bundler for modern JavaScript web applications. What Webpack does is it recursively builds a dependency graph for every module your application needs, and then packages all those modules into smaller number of bundles, often only one, and then loads by the browser. So it's very configurable, and it has 4 main concepts: entry, output, loaders, and plugins. So if we were to look at an example of how we might write code and bundle it with Webpack, you might start with just a regular JavaScript function in a bar.js file, and then you'll import that into another file, or app.js file. And then your webpack config.js, this is just a standard name, just like build.xml or pom.xml. You would point to that entry point, and then it can basically calculate from that entry point all the different files you need to import and produce one bundle.js. And then you import that into your index.html, and you have your single page application that can be loaded once. If you want a more advanced example, this shows how to use Babel to take something like React and make that into JS and have the ability to know how React works. And there's all kinds of different configurations. So very configurable. I recommend going to webpack.academy. Yes, that is a valid URL if you want to learn more about Webpack. But the coolest thing about Webpack is it's like Java back in the day, where you can go to sword fighting in the hallway as you wait for your TypeScript to compile. Because I actually wait longer for my TypeScript to compile these days than my Java code. So maybe Webpack and the JavaScript ecosystem will get faster one day, but right now there's a lot more compilation that goes on the front end. So I like to talk about leading JavaScript frameworks in 2020. In my opinion, these are the ones that are the leading ones: Angular, React, and Vue. And guess what? Hasn't changed in 4 years. And so even though it seems like there's a lot of turmoil and a lot of new frameworks coming out in the JavaScript framework space, it hasn't really. It's really stabilized a lot. So I base a lot of what I'm saying here on this article from Eric Elliott. So he writes an article at the end of every year about what JavaScript frameworks you should learn and some of the findings that he has. So this is from late 2016, the last time I spoke at jfokus. It says top JavaScript frameworks and topics to learn. He says React, Redux, Angular, and RxJS. And what he says in there is also Angular and React dominate. Nothing else even comes close. And so then we fast forward to 2017, a year later, and he says first, software ate the world, the web ate software, and JavaScript ate the web. In 2018, React is eating JavaScript. So 2018, 2 years ago, the year of React, won the popularity battle. And then 2019, he basically says React keep a firm grip on its lead in 2018. And then for 2020, I really like this guy, right? He's talking about these JavaScript frameworks, what you should learn and everything like that. He goes a little off the deep end here. He starts talking about top JavaScript frameworks and topics to learn in 2020 and the new decade. So he's got like AI and blockchain in this one. So, the JavaScript frameworks part I like, and AI and obviously interesting. Blockchain, not so sold on that yet, but I'm just writing JavaScript apps. I'm not really trying to change the world. So he said React dominated in 2019 and will probably dominate in 2020. So it may be cool to learn Svelte or Vue. He does mention this in the article. But if your goal is to get a job, you'll have better odds if you learn React first. So I like to crunch the numbers. In this section, I call pretty graphs. So take what you will from it. It doesn't really mean much, except that they're pretty graphs. So hotframeworks.com is actually a thing. You can go out there and find it. Each framework is scored by 2 separate measures, and they are simply averaged. So the 2 measures are GitHub score, based on the number of stars, and then Stack Overflow score, based on the number of questions. So you can see here, ASP.NET had a certain dropping off there in Q2 2019. Not sure why, but the leading one on this one is React. And a better view of it is actually this screen shows the top 10 So according to GitHub stars and Stack Overflow scores, here's the top 10 frameworks. But I also like to look at jobs. So how many people are hiring in Sweden for Vue, React, and Angular? Most people are hiring for React. If we look at the US, the ratio is a little different. You can see that y'all like React a little bit more than we do. But Angular is still very popular, and Vue they're hiring for. Stack Overflow tags. Most people have problems with Angular. GitHub stars, most developers like Vue. And so I think this is an accurate measurement of kind of developer satisfaction, because chances are managers or manager types aren't on GitHub, but developers are. And so this is also inspired by, there was a contest on Twitter going on at one point between React and Vue on who could get the most stars. So I think it is a little gamified, but it is interesting. And I threw Svelte in there. The only reason I threw Svelte in there is because it's one of the new frameworks that's on the scene in the last year. And it's basically a radical new approach to building user interfaces. And this is from their website. That's why it says radical. Whereas traditional frameworks like React and Vue do the bulk of their work in the browser, Svelte shifts that work into a compile step that happens when you build your app. So if you're familiar with a Jamstack, or the ability to do like static sites with React, it's kind of that flavor. But I like to look at GitHub star growth. So this is a great site for that, star history t9t.io. You can see that Vue and React had that contest there in 2018. And, great growth for all the projects. Like if this was your open source project, you'd be super pumped about your star growth. And then if you add Svelte in there, it's kind of making a blip, but really not much. But you're here to learn about what you want to do as a front-end developer. So I like to show a little hello world example with each one. You can see with Angular, it starts pretty simple, right? You have an import of a component, and then they have what they call decorators. In Java, we call them annotations. And this was supposed to be part of ES7. They actually took it out of ES7, but you can get it with TypeScript. So that's one of the big reasons that Angular chose TypeScript as a first-class citizen. And then you just have your export class. It's an ES6 class. You have your local variable, and then you have your HTML that talks to that selector. So it looks simple enough, but then you have to have a module that imports that app component, and then you have to have a main.ts that imports that module and bootstraps it. So what happened was there was a get started tutorial for Angular 2 when it came out, right? Now you have to call it just Angular. And I think Angular 9 might actually be released today. So it's been on the horizon for a while. There was this Angular 9 blockers list on GitHub, and I went and looked at it right before this, and there's 0. So could happen today. But anyway, they created Angular CLI because the get starting guide for Angular 2, I remember, was like 10 pages. And you basically go and copy and paste 10 files and then be like, this is hello world, this is terrible. So they came out with Angular CLI, and how Angular CLI works is you install it and then you do ng new and whatever name of your app. And you can see it generates a number of files for you, and then if you run ng serve, your app is up and running and you can develop on it, and it'll automatically reload with browser sync, or not browser sync in particular, but some mechanism to make sure everything's updated in real time. So it's great, works really nice. And then if you want to do mobile development, there's Ionic, and there's a great book, Ionic, I read a couple years ago, and what I was fascinated by was I was a pretty good Angular developer at the time, and I finished that book in an hour, because if you know Angular, you pretty much know Ionic. Now Ionic 4 has added support for Vue and React, so it's a little different, but chances are if you know React or you know Vue, you know Ionic, because it's a very thin layer on top of the standard framework belowhand. So if you want to learn more about Angular, I recommend this book. It's one of the best books that has testing. So if you're ever looking for a JavaScript book about a framework, I'd recommend look for a chapter on testing, because that's not often covered, and typically these frameworks have really good support for testing. So the funny thing is the URL there, ngbook/2. It was the ngbook 2, and then it was the ngbook 4, and now it's the complete book on Angular. They took the version off the front. Instead of saying Angular 8, it's just Angular, right? So it's updated for Angular 8 right now. It's a great book. Highly recommend it. And if you want to do authentication with Angular, that's my company's specialty. I write blog posts. Here's a blog post on it. And just to let you know, all these slides will be available. I'll give you a link at the end where you can download the PDF, and then everything in the slides are actually clickable. So moving from Angular to React, React is quite a bit different. And when it first came out, it was actually had a very bad reaction in 2014 because what they did that was different was they were putting XML in their JavaScript, and a lot of people, especially Java developers, were like, hey, we were putting HTML in our servlets a while ago, and that wasn't a good thing, and that was really painful. So it actually took developers a fair bit of time to actually embrace React and like that they were putting XML or HTML in their code. So you can see here, here's just a simple div, and then we have React DOM render into that div, and it's not like a quoted string or whatever, it's just a first-class citizen that is HTML, and that's how you define all components in React. And so the best video I found about learning React, I like to tell people this just because this is about an hour video from Eric Vicente, and it goes through with him showing you with a GitHub repository how to develop an app. And it takes you about 45 minutes, and you can totally follow along the whole time, and by the end of it, you're like, wow, I feel like I actually know React and how it works. So if you're brand new to React, highly recommend this video. But one of the interesting things about it is if you're familiar with the old way of doing things, and that's kind of the jQuery way, which I certainly learned for a long time and it worked well, is that's called imperative code. So you're adding elements, you're modifying elements, you're moving elements, and you're removing elements, right? This is an example of, in Facebook, if you actually have more than 99 notifications, it says 99 plus, and there's a little fire icon. Has anyone had that? Yeah, me neither, right? You got to have a lot of notifications, or maybe you didn't check it for a year or whatever. So managing the transitions of whether it has that fire, whether it has the number, and all that different things is very verbose. You're managing, transitions in state, and especially with Facebook, I don't know if you've watched, they have, the time changes on when it was posted. So there's all these little elements on the page that have their state changing, and it's very difficult to do in an imperative framework. Versus declarative code, this is the same thing, but it defines the UI you want. And it returns HTML, or what they call JSX, directly. And the cool thing about React is it actually diffs the HTML of the components and only adds what it needs. So similar to Git, for instance, instead of sending the full log of what changed to GitHub, it actually just sends a diff of what changed. So in this example, the first time it might just return that div class name equals Bell when there's no count. But when there is a count greater than 99, it already has that class name equals Bell, so it just sends that span. And so that's why it can be so fast, is because it's just doing virtual DOM and diffing. So similar to Angular CLI, create React app exists to create a new app, and it's very popular. So there's a new tool with NPM 5.2 called NPX. So instead of having to NPM install something and then invoke the command line for that, you can do NPX and it does everything. So NPX create React app will actually create a new React app for you. And then you can run yarn start or NPM start and you're up and running with React. So authentication with React is very easy. I've written schematics with it. You might think that schematics is a thing for Angular, but schematics are just a way to automate adding information to a project. So someone like me who does a lot of demos, I've written an Angular schematic, a React schematic, and a Vue schematic that adds authentication to one of those apps. Moving on to Vue. Hello World with Vue is what most people that are familiar with AngularJS will like. So what happened in 2014 when Angular announced Angular 2, it was almost like Tapestry 3 to Tapestry 4, Tapestry 4 to Tapestry 5. They did it twice, where they didn't have backwards compatibility. And Struts did it, right? Struts 1 to Struts 2, like very bad thing to break backwards compatibility, but Angular did it, and they're one of the few that pulled it off. But at the same time, 2014, 2015, a lot of people went to other frameworks. A lot of people went to React, and a ton of people went to Vue just because it is basically like raw JavaScript. There wasn't like a compilation step. You didn't need to learn TypeScript. And so you can see here, Vue is very simple. You just instantiate a new Vue object. You tell it the element to tie it to, in this case, the app. And then there's data and there's methods that you can read. So you don't have data.message in the HTML, but you have message, and then it can read that directly. So very simple to learn. If you spend an hour taking a tutorial, you'll learn it pretty quickly. And then you can use TypeScript with Vue as well. And I even watched several videos on egghead.io that really make it simple. But here you can see use v-on and then click, and that's how you do a lot of the attributes on a Vue application. And then you can see how it calls that click button. You can pass in an event, and it all works pretty nicely. And of course, they have a CLI too. The difference, I think, is they actually make it easy for people that aren't really command line folks. So they have this Vue UI. So if you use Vue UI, it'll actually pop a browser, and you can go in and make the choices for your app and then generate it that way. So if you're familiar with start.spring.io, it's kind of like that, but for Vue. And they also prompt you for all the different options. So with Create React App and Angular, Angular only has a couple of prompts. React doesn't have any. And this one actually prompts you if you want to use TypeScript, if you want to have a router, if you want PWA support, if you want a linter. Of course, no one ever checks testing, but it's an option. And then, you can run it the same way. And I write blog posts. So server-side support. If you want server-side support in any of these languages, it's now built in to Angular, so Angular Universal. Mobile.twitter.com is a good example of React on the server. And then Nux.js is a framework for doing Vue on the server. And what I found in my personal experience is if you're going to do any server-side rendering of these frameworks, you're probably going to want to use Node. You can do it in like .NET, you can do it in Java, but chances are their first-class support is going to be in Node, and if you just do it that way, you'll probably save yourself a fair amount of headaches. So I did find a couple articles about how to do it in Java. This is server-side support with Spring Boot. There's this Spring Boot Angular renderer project that's out there, but it does tend to break between like Angular releases. So one thing I looked into at one point was Graal. Graal has support for multiple runtimes, and I was trying to have Graal basically run my Spring Boot app and my Node app, right, server-side. And it's just one of those things that sounds good, but in general, you don't really find a lot of people in the wild doing server-side rendering unless it's someone like Twitter. So now we've learned a little bit about the frameworks. We've seen the build tools. Now let's take a look at style sheets. Who likes CSS? Hey, we got more hands than I expected. There's about 10 people. So this is one of the unique things that I tell people. They say, tell us, Matt, what's something that people don't know about you? And I'm like, I like CSS. And they're like, oh, so strange. And part of the reason is because I started doing CSS in the 90s. And at that point, you had to learn like what worked in IE and what worked in Netscape and then what worked in Chrome and what worked in Firefox. And so there's been a long journey, and that's pride that I have, and I've learned all the quirks. But really nowadays it's much easier. This is just a basic primer that if you have an ID, use a hash, right, to tie to it. If you have a class, then use a dot to indicate that class. If you have a first child, for instance, this case, it's a double first where you use the greater than sign. And then the first P, and then you say first, so it's double double. And that's called a pseudo selector, the colon first there. And then to do the image plus span, that's actually a sibling selector. So you can say if this image is on the same level as a span, then do it that way. The one thing that CSS doesn't allow you to do is go up the tree. It'll allow you to go down the tree, but not up the tree. So once you know the selectors, like everything else is pretty much manipulation. Now that we have the browser web console and all the tools there, it's very easy to manipulate CSS and make it look like you want. So I do that all the time for expense reports, right? Oh, wait, this is recorded. Sass is one of the best ways to do CSS, and it's called Syntactically Awesome Style Sheets. You can see the link at the corner there, sass-lang.com. And what it allows you to do is variables in your CSS, and then you can nest it, and you can make it much cleaner and more like a programming language. And variables are actually a part of CSS. They're coming in newer versions, and so that's not something you need Sass for, but still, a lot of people do like Sass for their applications. So the reason that CSS has really become easy is because there's a thing called CSS frameworks, just like JavaScript frameworks. So some of the most popular ones, I love Skeleton. It's dead simple. Ha. Right? Pure CSS is from Yahoo. There's Bootstrap, which you've probably heard of. There's Foundation, And also material design, which is more of an overarching, like how you do design from Google, and it's both web and iOS and Android. And then Tailwind CSS is kind of a newcomer in the last year, and that's instead of pre-designed components, Tailwind provides low-level utility classes that let you build completely custom designs without ever leading HTML. It basically means that you're going to have 10 classes on your HTML element to get it to look like you want. But hey, you got full control. So for me, Bootstrap was kind of what JSF wanted to be. And it's because it was components, right? When they came out with JSF and when they came out with Flex, they were like, we have web components. And the ability of you plop something on a page and you have this data table that you can sort and filter and do all these kind of things with. And Flex certainly had it, and JSF kind of had it. And you know, there was a lot of third-party vendors that created them, but Bootstrap made it so anyone could do it on any table. So just adding, you know, a couple CSS classes all of a sudden made you have good-looking buttons. I mean, before we had Bootstrap, no one colored their buttons. Now everyone colors their buttons, so revolutionary there. But also grid, right? So if you wanted to do a grid and you didn't want to use table layout, you know, Bootstrap gave you a way to do that. Small tip for you, if you're using Bootstrap Grid, you should definitely look into CSS Grid. It's a way of doing grids in CSS, and you don't have to really have as many nested components and divs and all that kind of stuff. Works very nicely. So I like pretty graphs. If you look at the stars on GitHub for these various frameworks, Bootstrap blows them away, right? And it's a very respectable number for most of their stats. I mean, most of them are above JHipster, which is a project that I work on. But still, you know, Bootstrap is the far and away winner. It was one of the most popular projects on GitHub when it first came out back in 2012. And you can see it's still very popular today. Also on this chart is Material UI, which is the React version of material design. And Angular material is also very popular. So those are all doing very well. Bootstrap and material are still kind of the main ones. If you want to customize it, Tailwind is certainly making some traction. One of the interesting things for me was as an independent consultant, I was an independent consultant for 19 years. Having front-end experience and back-end experience, I was often brought in as a Java developer to help them optimize their website. And they basically said, hey, you know, we don't know if it's the database queries or we need more caching or whatever, but it takes 5 pages or 5 seconds to render a page. Can you help us and tell us what's wrong? After I did just a couple days of testing, what I would often find was it was merely front-end optimization. And it hardly had anything to do with their back-end most of the times. So this became a specialty of mine, front-end performance optimization, reducing HTTP requests, you know, gzipping HTML. Browsers have supported that since Netscape 4, since 1996, where you can gzip the text content on the server and make sure the client renders it with far futures expires headers. You should have your expires headers like a year in the future. And you know, that really makes things faster. And a lot of this stuff can just happen on the server level. You don't really need to do it in code. But I had a lot of experience in the mid, 2015, 2016 timeframe where I could just make websites 2 to 3 times faster without ever touching the code. And a lot of it's just server configuration. But the interesting thing is HTTP2 kind of changes a lot of that. So they used to say, make your JavaScript bundles into one file. But there's been a lot of studies by the Chrome team that they actually prefer, especially with HTTP2, multiple files. Because it's much easier for them to detect if there's a change, in a 20 kilobit file than it is in a 1.5 megabit file. So with HTTP2, if you can use that, do. And it's much faster. It's binary instead of textual. And it uses fully multiplex, so it can send multiple requests down the pipe instead of having just one bundle, and works a lot with header compression and allows servers to do server push as well. And so if you have a slow site or you need to optimize your current site, check out this front-end performance checklist. You can see the table of contents there that shows all the different steps. HTTP2 is part of that. Testing and monitoring is part of that, which is very important. And then it has a checklist that you can download in Word or Apple Pages or whatever, where you can actually go in and make sure you're doing that. So written by Vitaly Friedman. There's also Chrome developer tools, which is very useful if you're a web developer. You should definitely follow these two folks because they often talk about Chrome developer tools and what it can do and how it can profile your app and how you can do debugging and how you can really optimize the use of Chrome developer tools. There's a number of framework tools and plugins for Chrome. How many people use Angular Aguary? That's none. How many people use React developer tools? There's a handful. And Vue dev tools? Got a couple. That's my experience as well. I've never used the Angular one. So I use like the console and debug there. But as far as actually installing these and using them, what I've seen is the React one is very popular. So if you aren't using the React one, you might want to check that out. The other two aren't that popular. But one of the more interesting things is, to me, progressive web apps. So progressive web apps are basically require that it's from a secure origin, it loads while offline, and it references a web app manifest. So the web app manifest is just a JSON document that gives instructions on what icons to use and what the start page is and kind of how the app looks. The loading while offline, there's a feature of modern browsers. It's called a service worker, and how a service worker works is it's kind of like a proxy that can monitor your network request and do caching and stuff like that. So it gives you the ability to basically cache more things in your browser. So as a web developer, it really gives you one of the worst experiences ever because you're caching everything in your browser, and when you're developing all day, that's the last thing you want, right? So what I see a lot of people doing with service workers is not using it in development, but using it in production. So it can be difficult to get used to, but just be aware that if you're using PWAs, you're developing a PWA, you might have to go into Chrome every once in a while and delete your app or turn off the service worker just so it's not caching everything. So this all started in 2016 with a talk from Alex Russell at the Chrome Developer Summit. And he basically said, we failed on mobile. And what he found was he was citing a DoubleClick report that said 53% of websites are abandoned if a mobile site takes longer than 3 seconds to load. And that same report said that the average mobile site takes 19 seconds to load. And I think in 2020, we're up to like 24 seconds. So it hasn't really gotten better. And the reason for a lot of that is our laptops are filthy liars. Like, we're often developing on a high-speed network with nice, fancy laptops, and we really don't experience what our end users are experiencing. And it kind of depends on where you are. If you're a developed country, if you're in the US or you're in Sweden and you have high-speed internet, you really don't see it. But if you're a company like Facebook or Google and you're trying to reach India or Africa and really get into those countries that has lower bandwidth, then you see it a lot where people just aren't installing your app because their phones don't have the room for it, and they're using web browsers, and if it takes longer than 10 seconds, they just abandon the site. And so what they recommend is basically fighting back with the purple pattern, getting kind of a lower quality phone, unlocked Android phone that only cost a couple $100, and using that to test, right? So when people say mobile first development, that actually means that you're using your mobile phone to test first. So if you're developing mobile apps, especially browser-based ones, make sure you have a low quality device to test with. Use Chrome developer tools to see that inspect the network connection and to trace it. Lighthouse is a great tool to actually see if your web app is performant and if it's a progressive web app. And then DevTools, the network and CPU throttling. That's what Lighthouse does. It throttles your CPU, it throttles your network and says, okay, will this work good on 3G? So the purple pattern is just pushing those critical resources for the initial route. That's kind of the app shell. And then rendering the initial route, and then pre-caching the remaining routes with that service worker, and then lazy loading everything else on demand. So if you're doing Webpack bundling of your front-end framework and you're putting everything into one file, you're probably doing it wrong. Because HTTP2, you should be able to split it into a number of different files, and if you're doing progressive web apps, you want to lazy load everything. So that's certainly a way to make things faster. So I asked people, as I've done this presentation before, what things am I missing? What would you like to see? And one request was web components. So they're a part of the browser, so you shouldn't need things like jQuery or Bootstrap. But Bootstrap is more of a CSS. So a lot of web components can be used without writing code, simply by adding an import statement to an HTML page. So you might have heard of Polymer. If you search for Polymer and try to include it in any of these pretty graphs that I've shown, it barely registers. Like, it was a framework to make web components easier, but not a lot of developers really adopted it. But it is out there. But there's also Stencil.js. So the Ionic folks created Stencil.js, which allows you to author web components. And the components that you create kind of look like TypeScript Angular components. And then there's also webcomponents.org that has hundreds of web components out there. So if you need to embed like a Google map or something like that, or a YouTube video, there is web components for you that you can use, and they're all out there and they work pretty good. And what I've seen personally is web components really work well for someone like Ionic that's trying to support multiple frameworks. So if you're a tools developer or a library developer, might work for you. End developers, maybe not so much. But Ionic uses web components for Ionic now, and they have it for Vue, React, and then Angular, and then they have just thin layers of Angular, React, and Vue on top of that. So, most of their stuff is done in web components. Another thing that people asked about was just directory structures. So if you're using a CLI, you can see there that Angular has a lot of files, and so does Vue, and React not so much. But I don't know why people are interested in that, but I put it in there. And then since I work for a security company, got to mention OWASP. Make sure you know about injection, broken authentication, session management. Try not to make unsecure applications. Your lack of security is disturbing. Micro front ends. I'm doing a talk on this tomorrow if you're interested. We have microservices on the back end, but what I've found is a lot of people are still creating monolithic front ends for their microservice back end. So micro front ends is kind of a reaction to that and saying, hey, we can actually have separated front ends that tie to each of these back ends. So I'll be talking about that tomorrow. And this is becoming more and more popular, largely because same reason that microservices became popular in 2014, there was a blog post on Martin Fowler's blog. So this was written by Cam Jackson, and it's very popular. A lot of people like it. And there's a framework for that. So singlespa.js.org is a framework that you can run Angular, Vue, and React all in the same application. I don't know why you'd want to do that, but it's kind of like microservices, where the reason for microservices is you have 1,000 developers and you want to all be able to deploy to production, and you don't want to actually work all on the same team. So I think single SPA is almost a way to that, where maybe you have a legacy jQuery or Angular application and you want to switch to React, but you don't want to rewrite the whole thing. So you could just write parts of it and kind of introduce new frameworks slowly. Like I said, I work on the JHipster project. So JHipster is an application generator, generates a Spring Boot backend, Angular, React, or Vue front end, supports microservices. I'm doing a talk on it tonight at 6:30 in C1 for the J Forum meetup. So if you're interested in JHipster or microservices, come to that. I did a YouTube video and tutorial on it, and microservices, that's what I'll be talking about tonight. And I like it so much, I wrote a book on it. So fun story about this, I wrote this for InfoQ, the InfoQ mini book. You can go there and download it for free. They thought it would be the most expensive book ever because I wanted to write an ASCII doc and then actually be able to produce all the artifacts myself. And so what they thought they would have to do is I would send them a PDF, they would take it, put it into Adobe InDesign, and then spit out, the different formats. And it turned out to be their cheapest book ever, because with ASCII Doctor, I could actually produce a MOBI, an EPUB, PDF, as well as a print version, and they don't have to touch it at all. So I'm in full control of the actual book. So that's pretty cool. And there's actually a template out there if you wanted to use it to write your own book and self-publish. And I wrote a cool 21 points app that tracks my health, kind of like Spring Boot has Actuator to track its health. Works pretty nice. So what you learned today, you learned a bit about ES6, how it's classes and modules more than just functions. Learned a bit about TypeScript. Node and MVM, Angular, React, and Vue are still the leading web frameworks. So I think if you choose one of them, it's like choosing between a Ferrari, a Lamborghini, and a Bugatti. Like, you're not going to be sad. It'll probably work pretty well for you. If you're a Java developer, a lot of people find Angular very familiar because it has separation of concerns. It has components and services and tests, just like we do in Java. CSS and Sass. If you don't like CSS, use a framework, might make it a little easier, and then figure out how to delete the stuff that you're not using because that can become a problem. Front-end performance optimization is very performant and important, and progressive web apps are kind of a way that you don't have to do mobile apps, and there's a lot of companies that are embracing them and doing them really nicely. So try. Like, don't be scared of the front end. Be curious. And UI development is awesome because you can see the results immediately. I mean, it's so cool to be in a demo. You get all the credit, right? The back-end guys get no credit. So that's always fun. So don't be afraid to try new things. Learn JavaScript or TypeScript. Try one of these frameworks and form your own opinions. And more than anything, it's a great time to be a programmer. There's so many different options out there and so many front-end frameworks. So be curious. We do a ton of tutorials on our blog on Spring Boot, Angular, Ionic, React, Vue, progressive web apps, and all that. We're also on the Twitters. And if you have any questions, feel free to reach out to me on my website or on Twitter. My DMs are wide open. I've already uploaded this presentation to SpeakerDeck there. My code often resides on Okta Developer. And may the auth be with you. And I have some stickers up here if anyone wants stickers.
Well, welcome back, ladies and gentlemen. Hope you all had a nice lunch. It's time to kick off the afternoon, and
Mark Reinhold. Wow, that's a promotion. Awesome. So, just waiting for the slides to come. There we go. Hello, everybody. Did you have a good lunch? Anybody feeling a bit tired, getting a bit food coma-y? No? No, excellent. Well, thank you very much for choosing this session. There are some awesome sessions in competition with me today. I did feel the pressure today when I saw the program, but thank you for coming to this. My name is Mark West, and I'm going to be talking about deep learning with you today. And I was actually here last year. I held a talk called Practical-ish Introduction to Data Science, which was actually the first part of this talk. But don't worry, if you didn't come last year, you haven't missed anything. You'll be able to follow this one fine. So, who the devil am I? Well, I'm an Englishman, but I live in Oslo. I speak fluent Norwegian, but I speak really bad Swedish, so which is why I'm speaking English today. And I'm actually a Java developer and architect by trade, but the last couple of years I've been building up a team of data scientists at my employer, which is Bouvet in Oslo. And I'm also the leader of JavaBin. This is why I'm wearing this strange T-shirt. It's a Norwegian Java user group. We just opened our call for papers for Java Zone, so if you want to submit a talk, you're welcome to do so at the Java Zone website. But anyway, enough of that. What am I going to be talking about today? Well, my talk is split into 3 sections. I'm going to start with giving you a background of deep learning, some basic stuff just to help you get started with understanding how deep learning and artificial neural networks work. And then we're going to take that understanding and we're going to apply it to a very popular neural network architecture called convolutional neural networks, which are very good for handling pictures. And then finally, we'll talk about recurrent neural networks, which are another type of neural network architecture, which are really good for handling sequential data such as text. And if you like my slides, actually, I'm going to put them onto Twitter afterwards. So you can take pictures if you want to, but if you want the better copy, if you follow me on Twitter, I'll be putting them out under the jfokus hashtag later on. So let's get started with deep learning. What the heck is deep learning? Well, I think this slide pretty much sums it up. Deep learning is basically biologically inspired machine learning, with multi-layered artificial neural networks. So on the left-hand side of this slide, you see a brain spinning around. And what we understand about how the brain works is that it's comprised of billions of cells that are connected to each other in hierarchical structures. And these cells all talk to each other through neurochemical or electrochemical means. And these kind of neural activations across the brain, they're what make us what we are. They give us the ability to think, reason, to do everything that we do. So what happened is computer science took this idea of how the brain works and they applied it and they built neural networks, which are basically small computational units that are connected to each other, which can tell the difference between a cat and a dog, amongst other things. So if we look at this picture here is a representation of a neural network, of what I call a vanilla neural network or a multi-layer perceptron. And all these orange circles in the picture here, they're the computational nodes that are taking in information and doing some kind of computation on that information and then passing it out to the next set of nodes. And this is a feed-forward architecture, so the data is moving from left to right through the network. And it's also densely connected. It means all the nodes are connected to each other. And finally, the connections are weighted. And I'm going to talk about how weighted connections allows neural networks to learn in just a second. So if we look at a neural network, a standard artificial neural network has 3 types of layer. The first is the input layer. So this is where you define what kind of shape or what kind of inputs you want going into your neural network. So imagine that you have like a picture which is 10 by 10 pixels, and it's a black and white picture. You would have one value for each pixel. 10 by 10 would be 100 values. So your input layer would have 100 nodes in it, each taking an individual value. And the input layer does nothing more than that. It just defines a contract for accepting information. Then you have the hidden layer. Now, the hidden layer is called because it's not exposed to the outside world. And this is where the kind of magic's happening, because in the hidden layer, we are actually identifying features from the input, and we're correlating them to a desired output. So this is kind of a supervised learning approach. And then we have the output layer where we give the result of the neural network. And that also has to have some kind of contracts that people using the network can understand. So, for example, if you have a neural network which is just going to give you a value, hot dog or not a hot dog, then you might just want to have one node in your output layer giving you a value between, for example, 0 and 1. But if you're trying to find 10 different types of animal in pictures, then you might want to have 10 nodes in your output layer, each representing the probability that an animal of that type has been found. So when we get to deep learning, deep artificial neural networks, these are basically neural networks with more than one hidden layer. And that doesn't mean that the deeper a network is, the more smart it is, because these hidden layers do different things, as we'll see later on. So if we zoom into a specific node in our neural network, what is that actually doing? I said earlier on, they're computational units taking in values and pushing out another value. Well, what's happening is you have an artificial neural network, and an artificial neural network is taking in lots of values. They could be taking in literally hundreds of thousands of values from previous nodes in the network. And those weights that are, those inputs that are coming in all have a weight assigned to them. And the weight is a way of amplifying or dampening a specific input. And this is what allows a neural network to learn, because you adjust these weights up and down to prioritize some inputs over others. All of these weighted inputs come into our node and are added together. This is a sum of weighted inputs. And then what we do is we take that sum of weighted inputs and we pass it through an activation function. And the activation function basically converts the sum of weighted inputs into an output, which is then propagated onto the next layer of nodes in the network. So it's really quite simple, these nodes. They're basically taking an input, and if a threshold is exceeded, they'll push out an output. But these activation functions, there's a lot of mathematics going on here. And I just want to point out that I'm not going to talk about calculus today. I'm not going to go into mathematics at all. I'm going to try and give you layman's explanations of how these things work. So these activation functions are basically a mathematical operation that will convert an input value into an output value. And there's different types of activation functions out there. There's lots of different types. And I'm going to just talk about 3 of them, give you an example to show you how your choice of activation function can actually affect the network's behavior. And I've drawn a little box here, so I'm going to try and map the input that would be coming into the activation function to the output that's coming out of the activation function. So if we take a simple sigmoid activation function, this basically converts our input range into an output range of 0 to 1. Okay? And as you can see, it's nonlinear. This is one of the things with activation functions. They're trying to introduce nonlinearity into the neural network. So a sigmoid activation function, whatever you give into it, it will give you a value between 0 and 1. And that's really good if you want a true or false kind of result from your node. Another type of activation function is the hyperbolic tangent. And this is the same as a sigmoid activation function. It's also nonlinear. But what this does, it gives you a value between a -1 and +1, with the centering over the 0. And that can be relevant in other types of use cases. Then you have another type of activation function, the rectified linear unit. And all that does, it's an if-then-else statement, which says if the input value is less than 0, round it up to 0. Otherwise, just output the value as it is. So you see these different activation functions have different behaviors. And kind of applying them to specific use cases is kind of it's not really in the kind of context of this talk, but I'm just trying to give you an idea that your choice of activation function can affect how your network acts. So when you train a neural network, how do you train it? What you do is you show it loads of information. So if I wanted the network to be able to tell me, is there a cow in this picture? I would show it lots of pictures of cows, loads of pictures of cows. And what would happen initially, the network probably wouldn't be able to work very well because it's basically a blank canvas. So in this case, I'm showing my network a picture of a cow and it's saying, yeah, I think there's a 0.15 chance that this is a cow. So in other words, it's saying it's not a cow. Fine. But you keep showing it pictures of cows. And then after a certain amount of pictures, you calculate the loss. And that is the difference between what the network predicted and what your expectations was. So in this case, imagine that I was expecting a value of 1. This is definitely a cow, and I'm getting 0.15. Then I have a very simple mathematical function. I just calculate the difference between the predicted value and the expected value, and I get the loss. And the loss is how wrong the network is, basically. The bigger the loss, the more wrong the network is. So I take that loss, and what I do is I optimize the weights in the connections in my network so that next time the network sees the same input, it will get a lower loss. So I'm adjusting my weights to reduce the loss. And basically, I update the weights backwards through the network via a process called backpropagation to reduce the loss and make sure the network performs better next time it sees the same data. So adjusting weights to reduce loss seems like a pretty simple thing, especially when I kind of show it in a nice two-dimensional plot like this. But what you have to remember is that the network doesn't know which way it should adjust the networks to get the lowest loss value. It doesn't know which weight value will give the lowest loss. It doesn't have this picture. It's like a blindfolded person on the top of a hill, and they're told, okay, find your way to the bottom of the hill. Now, how do you do that? You do it one step at a time, right? You try and find the next step downhill and try and find your way downhill like this. And each of these green arrows is a step. And you can actually tune the size of the step the network takes when it's doing gradient descent. You can actually say, right, okay, I want you to take big steps. But the danger of taking big steps is they can actually take you into a local minimum, where you want to get into a global minimum. You want to find the weight value, which gives us the lowest loss. So that's the challenge of gradient descent. There's no map. You're trying to avoid local minima. You're tuning the learning rate, that the big steps that the gradient descent algorithm takes. So now I've just given you a very, very quick summary of how artificial neural networks and deep learning works. So just to recap, an artificial neural network is a set of interconnected nodes, and these nodes are all organized into 3 types of layers: the input layer, the hidden layer, and the output layer. And you can have lots of hidden layers in, for example, a deep learning solution. And you change or you amplify or dampen the values coming into the network by using weights. And those weights are then tuned by gradient descent to optimize how the network predicts. Okay, so now we all understand what neural networks are. We can start talking about some of the more commonly used neural network architectures out there. Convolutional neural networks have really taken off in the last few years, and that's because they're really effective and really efficient, especially for image processing. But convolutional neural networks have a very broad use case, actually. But in the talk today, I'm going to be focusing on pictures. And we need to remind ourselves how computers actually perceive images, because computers or neural networks don't see a picture, they see numbers. Okay, this is very important to remember neural networks. Neural networks see numbers. They're just mathematical machines. So in this picture here, which is a picture of a Nike ankle boot, we have a 28 by 28 pixel picture of an ankle boot. And each of those pixels has one value in it. And that value, the lower the value is, the lighter the pixel is rendered in this picture. The higher the value is, the darker the pixel is rendered. And that's how computers see images, basically as a grid of pixel values. And it becomes even more complicated when you start dealing with color images, because that picture I just showed you was grayscale. There's 1 value per pixel. But in color images, there's 3 values per pixel. You have your red, green, and blue saturation per pixel. So that means you have 3 times as much data going into your network as you would do with a grayscale image. So you can see that the amount of data going into a neural network when you're processing pictures, it quickly escalates. Here's a picture of my parakeet at home. And imagine this picture is 640 by 640 pixels, and it's color, so it has 3 channels. So the amount of data in this picture is actually 1.2 million data points. Right? Now, you're going to feed those into a neural network. You're going to need 1.2 million nodes in your input layer, right? And imagine you have a hidden layer with 1,000 nodes. Well, imagine how many connections you will have to have in a densely connected traditional neural network, like the one I showed you in the first part of this talk. You're going to need something like 1.3 billion, sound like Dr. Evil now, 1.3 billion connections between your input layer and your hidden layer. And that's a lot of connections. You have to calculate weighted values for all of those connections. So training takes a long time. Running a network takes a long time. It started to get very inefficient. And the bigger the pictures get, the worse traditional multi-layer perceptrons will perform. So this is a problem. This has been a problem and a bit of a showstopper in the neural network world until everybody started shouting about convolutional neural networks, because convolutional networks take a different approach. In a convolutional neural network, you have a pre-processing stage where basically you use convolutional filters to extract the features in your images. And that's going to become clear as I speak. Now, these convolutional filters, they're basically filters that you slide backwards and forwards across the image to bring out, for example, vertical edges or horizontal edges. And they're basically reusable. So it's normal to use, for example, a filter of 3 by 3 pixels, which just slides backwards and forwards across the pixel. So they're reusable, and they're weights. You actually learn the convolutional filters when you train the network. So if you have a convolutional network with blank filters, it will learn which features it needs to identify to actually solve your problem. And a convolutional neural network can have lots of filters. You can have like 32, 64, 128, 256, depending on how complex your images are and the use case you're trying to solve. So how do you apply these convolutional filters to a picture? Well, here we have a filter which is really good at finding lines, vertical lines. And this filter is something you actually specify when you define the convolutional hidden layer. And this is 3 by 3 pixels, and it has a stride of 1 by 1, which means it moves 1 pixel at a time. And we're going to apply this filter to an image, which is a simple 6 by 6 pixel image of a black square. And what's going to come out of this process is something called a feature map. And feature maps are very, very important in convolutional neural networks because they're what the network are going to use to find out what it's looking at. So what happens is you take your filter and you start it off in the top left-hand corner. And what happens is you multiply every pixel by the filter value overlaying it. And then you add the results together. And that's what goes into your feature map in that top left-hand corner. And then your filter moves 1 step to the right, does the same thing again. 1 step to the right, does the same again. 1 step to the right, does the same again. Now, we see now our filter has come to the edge of the image, which is why the feature map is actually going to be smaller than the original image, because the filter can only move 4 steps across before it gets to the end of the image. Now the filter moves down the next line and does the same thing again. And it just carries on doing it, and then you end up with this feature map we have on the right-hand side of the screen. And I'll see if I can, that's the feature map. So this is a filtered version of the original image, which shows us that it's found a line on the left-hand side of the original image. But we're not finished with the feature map yet. We're going to push it through an activation function. And we're using the rectified linear unit activation function, which strips out all of our minus values. So we now end up with a new feature map where we only have this line on the left-hand side of the feature map, saying, OK, I found the line on the left-hand side of the original image. But we're still not finished, because what we want to do now is we want to do something called dimensionality reduction. And basically, the dimensionality reduction is reducing the amount of inputs. By reducing the amount of inputs, we reduce the amount of nodes we need in the network. We actually make the network more efficient. So we're going to do something called pooling. And pooling comes in lots of flavors. And I'm just going to quickly show you how it works. So we have a pool. We define how big the pool is and how far it moves across the image. So this one has a size of 2 by 2 pixels and a stride of 2 by 2. We're going to apply it to the feature map we just generated. And the result is going to be a new feature map. And there's 3 different types of pooling, which I'm going to show you here. Max pooling, where we take the maximum number per pool. Average pooling, where we just average. And then sum pooling, where we just add all the numbers together. So our pool starts in the top left-hand corner, just like the convolutional filter, does its mathematics, moves 2 to the right because it has a stride of 2 by 2, 2 down, and then 2 to the right. And now we have our feature maps on this side, which are still maintaining the fact that they've found something, they've found a line on the left-hand side of the original image. But the amount of data we're pushing into the rest of the network is a lot smaller. Okay, this is what convolutional neural networks are all about. They're about reducing and reducing and reducing, but not reducing so much that you lose the important information the network needs to make its predictions. So just to recap, we started with our image. We pushed the convolutional filter over it, and we got the value with all of the minus values in it, or the feature map with all the minus values in it. We stripped those values out by using activation function. And then finally, we used pooling to reduce the size of the feature map. And this is just one example of one feature map. Now, in real life, what you would do is you would have lots of convolutional filters all producing their own feature map. And those would then be sent on into a dense traditional neural network to make the prediction. But the benefit here is we've done the feature identification already. And the dense neural network itself is a lot smaller. It doesn't have to be as big as it was with a multi-layer perceptron. And also, it's a lot more effective. So let's just quickly look at a real-life use case. Have any of you heard of fashion MNIST? Yay, Zalando for the win. Zalando made this data set, which is basically 70,000 pictures of clothing. And each picture is 28 by 28 grayscale pixels. And that means there's one value per pixel. And they're distributed across 10 different classes. So you have 7,000 pictures of shoes, 7,000 pictures of t-shirts, 7,000 pictures of coats, all that kind of good stuff. And what I did, I trained a neural network, a convolutional neural network that can identify which class one of these pictures can belong to. And this is quite simple. My code, I'm not going to go through code today because I don't think it's very interesting. I think how things work is more interesting. But if you like code, you can go to my GitHub, and I'll put this link out at the end of the talk. You can go to my GitHub, and I've created a simple Jupyter notebook, which you can run in Google Colab. So you just click on the link, and it opens it up in the browser. So you don't have to use your own computer's processing to run this stuff. And I've created a neural network using TensorFlow and Keras, which basically, and it will show you step by step how you build a neural network like this to do this kind of image processing. So the convolutional neural network I built to solve fashion MNIST is pretty simple. We have an input and an output layer, and we have 5 hidden layers. That means it must be really, really smart, right? Because it's got loads of hidden layers. It's deep. But that's not really the case, actually. This is pretty simple. What you'll find now is that a lot of these hidden layers are just actually transformation. They're not doing any learning. But anyway, if we step through the layers and explain what they're all doing. We start with our input layer, which is taking our data, which is 28 by 28 pixels, 1 value per pixel, coming into our input layer. And that's just pushed on to the convolutional layer. The convolutional layer is where we have our filters. They're our filters that are going to learn which features it needs to find, the network needs to find to solve the problem, which is identifying what item of clothing it's looking at. So in this case, the convolutional layer is going to generate 32 convolutional features. Convolutional filters, sorry, each of which will generate a feature map. Then I have my max pooling layer, which is doing the pooling to reduce the size of the input. And then I'm done with the feature extraction. Now I'm going to do some housekeeping. The first thing I'm going to do is a dropout layer. And what this does, it mirrors the max pooling layer, the output of the max pooling layer. But what it does, it randomly deactivates 25% of the nodes in my network. Now, why would I damage my network? Why would I make it harder for my network to learn? Well, because I want to fight overfitting. I don't want my network to memorize the training data. I want it to generalize. I want it to find different solutions to the problem. So by damaging 25% of the nodes in my network at training, I'm actually going to make my network more generic and hopefully more powerful. The next step is another housekeeping step, because at this point, I still have my data in 3 dimensions. I have 20, I think at this point I have 26 by 26 pixels by 32 feature maps. But dense layers don't like 3-dimensional data. They want it in 1 dimension. So I have a flattened layer here, which just takes my 3D data and just turns it into a list of values, which goes into my dense layer, which has, I think, 128 nodes, which is going to then correlate the feature maps that it's seeing, the lines, and try and work out what it's looking at. And then we have a final dense layer of 10 nodes, which is going to tell me, okay, which items of clothing did I find in these pictures? Pretty simple once you go through the code, at least. Now, just to give you an idea what the convolutional layer is actually producing, this is after I've done the training. So imagine I'm putting in a picture of a handbag, and it's going into my convolutional layer. My convolutional layer has learnt 32 filters, and those 32 filters will generate these feature maps. And if we just, I don't know if you can see these, all of these feature maps are slightly different, and they're all seeing different things. They're putting out different details from the original picture. And this is what's really good about convolutional neural networks, because maybe some features are easier for the network to learn than others. But by doing this, what we're doing is we're kind of decomposing the image into its constituent parts and giving those to the neural network. I particularly like, I think it's these 2, if I can find them. Yeah, these 2 here, which almost look like they're pictures taken from different angles because they're highlighting the different edges on the handbag. But that's how the convolutional filter actually works. And then what we're doing is we're going to take that convolutional, all of these, the products of the convolutional filters, and we're going to downsize them by using max pooling. So what we do here is we generate these ones here, which are the exact same pictures, but they're downsampled a little bit. So there's less data in them. They're a bit more pixelated, but we still maintain that important information the network needs to make its prediction. So when I trained this network, I basically had my 70,000 records. I split my data into training data and test data. You don't want to test your model with the same data you trained it with, because then you're just checking if it's memorized the data. You're not finding out if it actually has managed to learn anything. So I split my data into training and testing data, and I train my CNN with the training data. I show it all of the records. Every 256 records, I do my weights updating, so the network learns from the loss. And I do that 10 times. I go through the training data 10 times, so 10 epochs. And then finally, I test my CNN with the test data to see how well it's doing. And here you see the results. Yes, you can see that quite good on the screen. So this is the output of the neural network after testing. So we see it's pretty good results, really. And we see we even get the results per item of clothing, which is quite handy. Now, we're getting lots of different numbers here: precision, recall, F1 score, support, accuracy. Let's just try and explain what all of these mean. Now, precision is the amount of correct class identification. So for all of the items, or the pictures I said were T-shirts, how many of them are actually T-shirts? That's what precision is checking. Now, precision is important when the cost of false positives is high. So in other words, if precision would be important when doing spam email detection. When you're doing spam email detection, if you say, oh, that's spam, when it's not spam, and you send it to the spam box, then the user might not get to read it. So that's an example when precision is important. Recall is the percent of correctly identified class members. So for all of the T-shirts in my data set, my test set, how many did I find? And recall is important when the cost of false negatives is high. So in other words, cancer diagnosis. If you say to somebody, you don't have cancer, when they do have cancer, the cost is high. Now, a lot of people get confused about precision and recall. I do. So a lot of people just use the F1 score, which is the mean of precision and recall. And F1 score is it's a better metric than, say, accuracy. Accuracy is just the overall score. And what's important when you're measuring how well your network is doing, you need to look at your test data set to make sure that it's well balanced. And you don't really get that when you look at accuracy. Here's some examples of where my network failed. Let me see now. I can bring up some of those. Oh, now it doesn't want to work. No, let me go a bit closer to the computer, see if that helps. Here we go. This one here. Now, my network said this was a T-shirt, but it's a shirt. You can see the buttons on it. This one here, my network said this was a sandal because of the pattern on the side of it, which looks like a hole. And this one here, which is predicted to be a dress, but it's actually a shirt. So you see that often the problem is ambiguous data. And that's often the problem, especially with image processing. And the only really way to solve that is to get pictures with better quality, like higher resolution. So, to summarize, convolutional neural networks are spatially aware, and they're very good for image processing. And they use convolutional filters to identify and extract features from images. And those features will then be passed on to dense layers to map them to classes. And pooling is an optional step in convolutional networks to even further reduce the dimensionality of your data. And precision, recall, F1 score, and accuracy are all different metrics for measuring your model's performance. So we're done with convolutional networks now. Let me just check how I'm doing for time. I'm doing OK. So let's go on to recurrent neural networks. Now, recurrent neural networks is a slightly different beast, different architecture. And recurrent neural networks try and solve problems like this. Which way is the arrow moving? Well, it's moving from right to left. We can see that. But, like any animation, basically, when you're looking at animation, you're just looking at still pictures in a sequential order. And our brains, they can process that. They can tell us, OK, I remember where the arrow was a minute ago. I know where it is now, and I can see which way it's moving based on that. And that's because we have state. And the same with text. When you're processing text, you need to be able to take each word in the context of the words that came before and after it. So this is a problem with vanilla artificial neural networks like multi-layer perceptrons. They're not very good at handling sequential input because they don't have state. As simple as that. So we need another solution, and this is where recurrent neural networks come in. So recurrent neural networks are pretty much the same as vanilla neural networks, but they have a feedback loop, or they actually have states. They maintain hidden states. So what happens is, like, when you pass in a sentence into a recurrent neural network, each word in the sentence is sent through the rest of the network one at a time. But the network remembers the words that have come before. And that's how basically recurrent neural networks work. And then you get a final prediction from the output layer telling you, okay, what does the network predict based on the sequence that is seen? Another way of viewing recurrent neural networks is like by unrolling it. And if you unroll a neural network, a recurrent neural network, is basically you're enrolling it into multiple instances of the same neural network, which are all sharing weights and hidden states. So in this example here, you see that we have a sequence of 1 to 4. And when you go through each instance, it takes one sequence at a time, and it produces its own output for that particular input. But you also see the hidden state is maintained, as you see with these red lines going through the hidden layer. The problem with recurrent neural networks is that they're very forgetful, much like my daughter, in that what happens is, like, when you give them a long sentence, they'll actually forget the start of the sentence when you get to the end. And this is because recurrent neural networks have a problem called the vanishing gradient problem, which is actually commonly known in the neural network or in the artificial neural network world. And this means that recurrent neural networks aren't very good for long sequences because they have short-term memory, not long-term memory. So what we're going to do today is we're going to use a long short-term memory long short-term memory neural network, which is the same as a recurrent neural network, but it has something extra. It has long-term memory as well. So what you can think about is that a LSTM network has two conveyor belts going through the hidden layer. And one conveyor belt is like taking all of the short-term memory, and the other conveyor belt is taking the long-term memory. And then basically when you look at a LSTM node, you have these two conveyor belts, and you have these workers that are standing between the conveyor belt. And the worker that's working the forget gate, their job is to look at the working memory and say, okay, well, based on the working memory and based on what we've learned so far, is this information in long-term memory is it something we need to remember or not? Is that important for us to remember to achieve the network's goals? And then you have the input gate, which is saying, okay, I have all this working memory here. Is there anything that I should move over to the long-term memories? Is there anything important to remember? And the output gate is saying, okay, what are we actually going to push out of this node based on what's in the long-term memory and the short-term memory? So that's basically how an LSTM node works. And these gates are basically stacked activation functions, which is why I'm not going into the math, because especially after lunch, you would all fall asleep. So what I'm going to do is I'm going to use LSTM networks for solving the Internet Movie Database problem. We have a use case where we have like 50,000 Internet Movie Database reviews. And they are classified, they're labeled, it's labeled data. They're classified as either positive or negative. And we have all these reviews have been already encoded into a sequence of integers. So what's been done is someone's gone through all the words in the data set and they replaced them with integers, which are consistent across the data set. And the integer that each word has got represents how often that word pops up in the data set. So you can imagine words like the has a very low number because it pops up very often. And what I did is I trained a LSTM that could classify a movie review based on this training data. And this is the actual data, the data set that I have. If you look on the left-hand side, the encoded side, that's the actual data set that I started working with, which is just basically a list of integers. For each review, that's a single review. And then luckily, the data set contains a codex, so I can convert it back into text, which I did, and that's where you have the decoded on the other side. And you can see the most popular word in the whole data set is the start tag. And that's because the start tag comes at the start of every single review. I had to do some extra pre-processing of the data. First thing I had to do is I wanted to reduce the vocabulary in the data set to the most popular 10,000 words, because there's 26,000 words in the data set, and most of them aren't very commonly used. So I wanted to shrink down the data set to the most popular 10,000 words. And the other thing is all the reviews are different lengths. Some are 16 words, some are 1,000 words. And I wanted them all to be 500 words long. So I either padded them out or I truncated them down to 500 words. So all reviews are 500 words. Now, my neural network is using something called word embedding. Anybody heard of word embedding? Yeah, word embedding is really cool. And at its basic essence, word embedding is basically just mapping, because the goal of word embedding is to give meaning to words, help us to understand a word's semantic meaning. And what word embedding does, it plots the words in a multi-dimensional space. And the closer the words are together, the more they have in common. And the different dimensions capture the different linguistic relationships between words. Now, this picture here, which I've stolen from a guy called Shane Lin, it kind of shows how that works. So we have a two-dimensional word embedding here, and you can see like these ones tagged with blue, kitchen, table, vanity, sink, bathroom, they have a lot semantically in common. And especially these three here, finish, color, and paint. In English, finish is like either gloss or matte. So you can see that how these things have semantic relationships. So word embedding is very, very powerful, and it's mathematically based, because basically you're just updating the coordinates of words as you train the network to represent the words, the semantic similarities between words. There's lots of pre-trained models, but I'm not going to use a pre-trained model today. I'm going to just train it from start. And my LSTM implementation, again, is on my GitHub. So if you go to my GitHub later on, you just click a link. It opens up Google Colab, which is a Jupyter notebook. You press run, and it will just run it all using Google's GPU, not using your own GPU. So it runs pretty quickly. And it basically looks like this. This is the architecture of my LSTM, which is quite simple. Basically, what's happening is in my input layer, I'm taking in 500 words. Every review has been either truncated or expanded to be 500 words, right? And that goes into my input layer, which is then fed into the embedding layer. This is where the word embedding is happening. And the embedding layer is going to learn a word embedding, 32 dimensions of similarities for each word in my training set. So basically, it creates a table where each word has a row, and then along that row there's 32 values, each representing a dimension in the word embedding. I have a dropout layer to fight overfitting. If you remember that earlier on, I deactivate 25%. The dropout layer is a copy of the embedding layer, and at training time it will randomly deactivate 25% of nodes, giving the network brain damage so it learns different routes to the solution. And then I have my LSTM layer. My LSTM layer has 32 nodes in it. And what that's going to do, that's the one that actually looks at the order of the words. So the LSTM layer both takes in the meaning of every individual word, but also the order they come in to try and work out, is this a positive or negative review? Then I have another dropout layer, which is just a mirror of the LSTM layer with 25% of the nodes deactivated. And then finally, I have a single node in my final dense layer, which is saying negative or positive. Basically, if it's 0, negative, if it's 1, positive. So just to explain that word embedding layer, just one more time, it's a lookup table. The embedding layer is just a lookup table. You have each word has a row, and then 32 dimensions of values, which are modeling the similarities between the words. And those coordinates, those values in my lookup table are all weights that are updated during training and backpropagation. So those values will be optimized for the network to enable the network to solve the problem it's trying to solve. And then my LSTM layer is taking the order of the words and the dimensions, the word embedding, and putting those together to try and work out, is this a positive or a negative review? So training the LSTM is pretty simple. I trained it with my training data. I will have like 25,000 training examples. Half of those are negative and half are positive. And I update my records via backpropagation, update my weights via backpropagation every 256 records. I'll do this 3 times. And I test with my test data. And here is the results. So here I'm getting like 87%, overall 87% accuracy, which is pretty damn good. And again, if we look at precision, that's the percent of correct class identifications. Like for all of the records that I said were negative, how many were negative? Recall is for all the actual negative records, how many did I find? And then the F1 score is the harmonic between precision and recall. And then we have our accuracy. So good results from the LSTM network. Here's an example of an incorrectly classified review. And this was actually predicted to be negative, where it's actually positive. And if you kind of look a bit closer, you can see that there's a lot of negative language in here. The person was just disappointed that this show got taken off the air, or this film was cancelled, or whatever it was. But you see there's a lot of negative language in there, which could maybe drag the prediction towards negative. But there's another problem. And it's all the tags. Firstly, you have the tags from the process where they've actually turned the text into integers. They have some leftover tags from that process. And there's also some HTML tags in there. So imagine, like in my word embedding, if my word embedding starts looking at starts or unknown and saying, oh, this is negative words, it could drag my predictions in the wrong way, right? And the same with these HTML tags. So this is the danger when you work with NLP. You need to strip out all of the words that don't give meaning. And it's just like the convolutional neural networks where you try and identify the features that are most important. And there's a bit of an art to it, especially with natural language processing. So to summarize, recurrent neural networks and long short-term memory networks, RNNs, or recurrent neural networks, handle sequential data because they have states. But this is just a working memory, and this working memory has a bit of a problem with short-term memory loss. It's just one of those things due to the vanishing gradient problem. So instead of using RNNs, it's often better to use something like an LSTM because they take care of the long-term memory. Word embedding is a powerful technique for modeling semantic relationships between words. And often when you're doing neural networks that handle NLP, you'll have to consider some kind of word embedding. But you can actually, as I said, you can download other models that have been created before. I think Facebook has something called fast text, which is particularly good. So if you don't want to do it yourself, you can just use somebody else's. And pre-processing of NLP data is vital for securing good results. Okay, so if I went too fast, I hope I didn't go too fast, but I've written some blogs. When I actually wrote this talk, I wrote some blogs which back it up, which are all available there. And my implementations of the CNN and the RNN, you can just go to Google now, GitHub, sorry, and you can open those up and run them in your browser. Just one thing I have to apologize for is that they're implemented in TensorFlow 1. I haven't managed to convert them to TensorFlow 2 yet, but they still run, so it's completely okay. And what's good with those implementations, I've also done some visualization stuff that you can check out. And that's quite cool, especially with the convolutional neural networks and fashion MNIST. And there we're done. And I'd just like to say thank you all for coming. I hope you learned something. I hope it was interesting. And yeah, don't forget to rate all the talks in the jFocus app. Thank you very much. Get some drink.
Thank you. Thank you. Thank you for the nice introduction. My name is Maarten Mulders. I work at a Dutch company called InfoSupport. We do a lot of consultancy, and we do that by bringing in our own kind of awesomeness, which we call awesome sauce, hence the sticker on the Mac and on the screen. One kind of technology that I find particularly awesome, and that I've been valuing more and more over the last years, is called React. And in the coming 45 minutes, I want to share with you why I think React is so amazing, what you can actually do with this. And I'm going to do that using a lot of coding examples, so please bear with me. If it doesn't go correctly the first time, please bear with me, but I guess we'll do fine. Let's get started. What is React? React is described as a library that lets you declaratively build a user interface using JavaScript and optionally XML. Now, what's interesting here is the word declaratively, because we're using React, you can actually declare what your user interface looks like instead of writing it out imperatively. And the word user interfaces is very important. React is really targeted at building user interfaces, but it does not say what kind of user interfaces. In this talk, we'll be looking at web applications, but there's spin-offs and forks of React for a lot of user interface platforms like desktop applications, mobile applications, and there's even a spin-off that lets you generate PDF files. It's kind of a read-only user interface, I guess, because, well, interacting with a PDF file is a bit hard. And we use XML for that. This is 2020. If you thought everything is done using JSON nowadays, well, not so much. We still use XML, and we'll see how that works. How does React compare to other web application libraries that are out there? There's a few things that make React different. First of all, React uses one-way data binding and not two-way data binding. Two-way data binding has become very popular with kits like, for example, AngularJS back in the days, where you had a dynamic and automatic binding between your memory model on one hand and your document object model on the other hand. And AngularJS would keep those in sync, probably throwing too many digest cycle exception at you if it couldn't do so. React chooses another approach and says data just flows from top to bottom. It's one-way direction. There's no custom templating language in React. Everything is done using XML, and there's no post-processing of your views whatsoever. Thirdly, React focuses on building user interfaces, and this means that there's a lot that does not come out of the box for you. Again, if you look at, for example, AngularJS or later versions of Angular, you would find modules for doing REST calls. You would find modules for interacting with your cookie jar. You would find modules for whatever you can think of. This is all not there in React. It's just a user interface and nothing else than that. But as we can see later, browsers have a rich set of APIs nowadays that lets you do many common tasks. React applications are built using JavaScript, and just JavaScript. We can add XML. This is called JSX, and we'll see in a few minutes what that is and how it works. But you can do without. By the way, I've never seen anyone doing it without JSX because your code will get very verbose. You can add TypeScript if you wish, which gives you type checking at compile time or build time if you wish. Very powerful, and especially if you're building larger applications, it's definitely worth considering to use TypeScript on top of JavaScript. And finally, React uses its own mental model of what your document object model looks like. It's called the virtual DOM, and that's, if all goes well, it's in sync with the actual DOM. And we'll see later how that synchronization process works. Before we dive into that, I want to show you a few tricks and things that are very popular in the JavaScript world nowadays. Because if, like me, you have a Java background and you look at JavaScript, you'll at first be like, oh yeah, I know this. This is how we did it with jQuery back in the days. Well, the JavaScript world has changed, and there's a lot of powerful constructs in the language that are also very popular in React and in the front-end community. So let's run through them real quick. First of all, JavaScript now has classes, which wasn't the case like 5 or 10 years ago, maybe. Classes work basically like we expect them as Java developers. So we have a class that can have properties, and it can have methods. And if I create an instance of that class by saying, hey, I have a new instance of the amount class, 1,500 Swedish crowns. I can invoke the getCurrency method on that. And as I expect, I get the currency back, not the other part of the object. And I can create many instances of classes and have them populated with different fields. And those methods can be simple getter methods like this, but can also contain more complex business logic. Secondly, there's functions. Functions aren't that special, are they? I mean, we all know functions, and this is just a JavaScript function checking whether a number is even or not. There's nothing special. I can invoke it, and the outcome is as I expected. But what you see happening a lot in the React ecosystem is that they use different syntaxes as well. For instance, the arrow function is very popular. In the arrow function, I have an argument list down there, followed by the fat arrow, and then followed by curly braces that mark the function body. And inside the function body is just, as I expected, the same statements. And you can make it even shorter. You can make it even shorter by just removing the curly braces. If your function is really short, you don't need the return statement either. And you can just write it like this. You can like this, or you cannot like this. My personal preference is I like this. I find it very short and concise. But if you feel like writing function fit is more of your taste, you're perfectly good to go. It all works in a similar way at the end of the day. But just know that there's many ways in which functions are written. Next language construct is object decomposition. Imagine I have an object here, and I created it with a few properties. There's a name, there's an age, and there's an occupancy. I can actually deconstruct this object into the individual properties. So I can say, hey, just give me the name and the age. And at this point, I have two local variables in scope, name or age. But I don't have occupancy here because I did not decompose that one. So this is a very intuitive way to pull out a few properties from an object and leave the rest alone. Same can be done with arrays. So I can have an array and I can say, okay, decompose that for me into some of the individual elements inside that array. I can ask, for instance, for the first element of the array or the second one. Again, this mechanism is used, as we will see later today, for instance, in some of the React hooks, where the hook is trying to return more than one return value, which is not allowed in JavaScript. But hey, why not? We can just return an array with the two values and then let the user decompose that into individual variables. This would actually be the same as if we did numbers, first position, second position. But you're not coding the indices, you're saying, hey, I want to have this, this position. Then there's the object shorthand notation, which is basically doing the other way around. It's constructing new objects out of the individual properties. So I can say, I have a few local variables, name and age. Please construct me a simple object with just those two properties, and the values of those properties are equal to the variables that I currently have in scope. And if I would inspect what that looks like, I can stringify that as if using JSON, and it gives me an object with two properties and the values that I expected it to have. Then there's string interpolation. Very powerful, and I'm really hoping this someday will come to Java as well, because it is, in my experience, an easy way to construct strings altogether. Let's say that I have my amount class that I showed a few seconds ago, and I want to have a nice textual representation of that. I could say, okay, first take the currency property, put a space, and then the amount itself. And then this gets combined into one single string and then returned as the return value of the toString method. This backtick and the $curly braces syntax is there to tell JavaScript, hey, I'm going to construct a string using some variables that I have in scope in this case, they're in scope because I refer to them using this. So, this is all nice. It's not required to understand React. What we're going to tackle now is JSX. And JSX is, well, I would say highly recommended if you want to use React. As I said, you can do without, but it's just going to be a lot more typing from your side. And I don't know about you, but I'm a kind of a lazy developer, so I prefer less over more typing. So what is JSX actually? JSX is an extension to JavaScript, and it lets you use variables that are whose value are XML. That's not a string containing XML. That is XML itself, just a structure of text, of elements, with attributes, with child elements. You can embed expressions in it, as we will see later, and you can add attributes to those elements. And you can actually have child elements, so there's nesting support. React gives you an automatic prevention against XSS attacks. So if there's any place where you have a variable with, for example, script, alert, whatever, and then close script, React will not automatically embed that into your web application, but it will escape that for you and make sure that it doesn't get run into the user's web browser. Of course, there's a way to circumvent that, and the syntax for that is so bizarre, I don't recall it from heart, and there's no way that you're doing that by accident, because the syntax is so absurd. But it is there. JSX is a very interesting technology, but the thing is, there's no browser nowadays that runs it out of the box for you. So you need a step in between to turn this JSX into plain old JavaScript without XML. And this process is called transpilation, which is transformation and compilation. It's neither of both, so let's just combine the two and think of a new word for that. And in the case of React, it means that a JSX element gets translated into an invocation of React.createElement. We'll see later how that works. So let's look at some examples. I mentioned the word elements, and as I said, using JSX, we can have XML as a first-class citizen in our JavaScript code base. Here I'm declaring a variable called element, and what's inside the variable? Well, it's a div. It's a div, the same thing that we can have in an HTML file, and that will create a DOM element in our browser. I can start typing here, and we can see in the yellow box below that it gets updated automatically. So this element, this div, is actually being run in the browser, but it's not a string, it's not interpreted, it's not whatever, it's automatically converted into real document object model elements. Well, that's all nice and good. I have this element. The second thing I need to do is I need to invoke the React DOM render method. React DOM is actually the binding of React to the document object model. As I said, there's multiple bindings. There's bindings for native applications, for desktop applications, so on and so forth. This one is there to specifically work with the document object model in your browser. The render method needs two arguments. The first one is the thing that I'm going to render. In this case, it's an element. And the second thing is an actual element inside my existing DOM where the application is going to be mounted, so as to say. So I'm creating an application, but it needs a place to live somewhere in the web application, in the web page where my JavaScript has been loaded. And that's the second argument, document.getElement by ID. Now, as I said, JSX can have attributes. So for instance, I can just say, okay, my element has an identifier. You hardly ever do this in the React world, but you can do it if you want to. And you can specify more than just the ID attribute. But take care, because many attributes actually have a different name in JSX. For instance, if you have a div in your HTML file, you would say class is red text to apply a certain CSS rule. But that one won't work in JSX, because class is a reserved keyword in JavaScript, and this still is JavaScript after all. So it's named class name. camel cased. And if I start typing here, we can verify that indeed it gets translated into the regular DOM thing called a class, which binds the CSS style red text to the element and applies it to the text that we are seeing here. Another thing is that they sometimes behave differently than what you're used to in the HTML world. For instance, the style attribute is there to actually apply an inline style to your HTML file or to your HTML elements. In JavaScript, I can actually do this. In JSX, I can actually do this using an object instead of just a string. And in this case, I'm creating an object with two properties, color and font weight. Note that the font weight is also written differently than we're used to in CSS. In CSS, we would have written font-weight, and here we're writing font weight camel cased. Again, this is because font-weight would not be a valid JavaScript identifier for the property, so they needed a way to circumvent that. And if I start typing again, we will see that we have red text in a bold font. So the translation to how it's done in the browser is done for us by React. And we just need to know and need to remember that sometimes both classes, both attributes and their values behave a little different than we're used to. The React documentation has a very descriptive page about the actual differences between JSX and HTML. And if you start using React, it's worth checking that one out to see what other differences you may encounter. So, another difference that we need to be aware of is the fact that a JSX expression, or a variable with JSX in it, must have a single root node. Just as our HTML files have an HTML opening and closing tag as the root of the whole document, the same holds for JSX. So I cannot just say, well, let's do a div followed by another div. We get an error message from Babel. It's actually very descriptive. It says adjacent JSX elements must be wrapped in an enclosing tag. So the most simple approach to do that is, well, let's put an enclosing tag around it. Now it works. But some purists may say, hey, you're creating a div here that you actually don't need. And, well, you're more or less right. So we can replace that with react.fragment. Like so. And react.fragment creates, well, it makes sure that it's syntactically correct, so it can be rendered. But at runtime, the surrounding div will be gone. It's not there anymore. So it's a little bit closer to our intention. And if you are really feeling fancy, you can actually remove the name react.fragment altogether and have a JSX element with no name. This is not valid XML, and that's why they have react.fragment as well, because that is valid XML. But you can do it like this, and it's still valid in the JSX world. Now we've seen elements, and they are basically just DOM elements. That's not yet very powerful. This is not where the magic of React really happens. Where React shines is that you can build components. Think of components as actually a function that gives you a React element in return, and that you can pass a few arguments. Those arguments are somehow named props in the React world. I don't know why, but they decided that elements have props instead of arguments. It's that way. You can give the method any name, you can give the method argument any name, but props is by far the most used. What we see here is that we create a function. I'm using the arrow syntax. The function takes one argument called props, and it returns a sample snippet of JSX. One element here, it's a div again, because at the end of the day, it needs to be something that the browser is aware of. And it will just create this div with two child elements. The first one is hi, comma, space. And the second one is a new text element with the value of the name property of that props argument. So this props argument is just an object we're getting, And if there's a name in it, we'll use that one. How do we specify it? Well, using an attribute. So we're saying, render this greeter component for me. And here is the arguments that I want to give it. There's one, it's named name, and the value is jfocus. Instead of using this props and typing props.name, we could have used object decomposition as well. Note that in our arrow function, we got rid of the props. We just say we expect an object with a name property in it. And that means that our local variable is not named props anymore, but it's named name again. Effectively, it does the same thing as the previous example. It's just a little bit more verbose in what it actually expects. I prefer it this way because I'm really making clear with the function declaration already what kind of properties I expect from my component. So these are the basics of JSX, but JSX can do much more for us. As I've already shown you, you can have expressions in JSX, and this is a way to dynamically populate the document object model that will be outputted eventually. So here I have an example component. It's a function, it takes props, but if you don't have any props, you can actually leave the argument list empty. It's no matter, it's the same thing, but well, let's just put it there for conciseness, like so. It builds a div, and inside that div is a strong, and inside that strong is our curly braces. And this is a place where I can literally type anything as long as it is a valid JavaScript expression. So I could just say 40 plus 2, and it will say 42, of course. JavaScript is a very powerful calculator at the end of the day. It's so powerful, it can even add numbers if they're text. But you need to be aware of the fact that it's text. This is cool. You can also refer to variables that you have in scope. I have a variable answer to question of life. Let's look at that one. It's a valid JavaScript expression, so I can type it here. I can even do method invocations there. I put those braces, turning it into an invocation of the method named ask question of life. And of course, as we all know, the answer to that question is 42, and that outcome is then used as the value of the expression. And that's being used in my document object model that we see at the end of the page. If we can do expressions, we can also do control statements. Here, for instance, I can do a ternary operator. I have a very emotional component. I can give it a property called isHappy. And if that one's true, I want to clap my hands, and otherwise it's time to dry my tears. So what I'm doing, I'm looking at this property here. I'm checking if it's true. If it's true, I'm returning the clap hands component. Otherwise, I'm returning the dry tears component. This is a very easy way to make small decisions inside your JSX. Have little things like, am I logged in? Show a user profile, else show a login button, that kind of stuff. Not only can I do conditionals, I can also do iteration. So for instance, if I have an array of ticker symbols, those are all Dutch companies, ASML, Heineken, you must be familiar with that one, I guess, Royal Philips. I can create a list of ticker symbols, which basically takes the array of symbols that I'm passing and says for each element in that array, I want you to invoke a function. I'm passing that function as an argument to you. And the outcome of all those function calls is giving me a new array. And that new array is then the outcome of my component. So it looks at ASML, runs this function. It looks at HAIA, runs that function. Looks at PHIA, runs that function. And for each and every one of them, it will display the ticker component. And if I update that component, we see that all of them are actually being updated immediately. Very powerful. Now, if you're like me and you look at this, you may be thinking, that's all cool, but it feels a bit like magic. How does that work? I, for one, was very curious and decided to figure out what's happening under the hood, the stuff that we did not see. There's basically two things going on. The first thing is that at build time, some magic is happening already. We've written a few components in JavaScript files. We've wired them together using nesting, etc. But that's not all of it. When we build our application, we use Babel or the TypeScript compiler to actually strip the JSX away and replace that with invocations of React.createElement. So, for instance, if I have a component that's called greeter and I'm using that somewhere in my application, I'm passing it an argument called with the value jfocus, then at build time, this is getting replaced with an invocation of React.createElement. The first argument is the component itself. The second argument is all the properties together in one object. And the third argument, null in this case, is any child components that I may have included. But there are none in this case, and that's why it's null. So, as you may imagine, this will give us a very large object structure because, well, at the start of the day we have an application and that has a lot of child elements, and those have child elements and grandchild elements and grandchild elements, etc., etc. Very large tree of components, all represented as a kind of an object. Because React.createElement is a function that returns us an object that kind of like describes what the document object model should look like. But mind you, it's not the document object model thing itself. It's a description. Now at runtime, this large tree of DOM-like objects is looked at by React, and then React compares that with the actual DOM. It starts looking at the second argument of the React DOM.render method. That's where my app is going to be mounted, right? And it looks at this large object tree in one hand, it looks at the actual DOM in the other hand, sees that it's basically empty, and starts performing changes to the actual DOM based on what it sees in the object structure. And now the powerful thing is that React will only do the changes that are really necessary to perform. So if a part of this large object tree is a correct description of what the actual document object model looks like, it will not do anything. And this allows for a very high runtime performance. This process is called reconciliation. It's basically syncing this virtual document object model with the real document object model. And it works as long as you are aware of the two major assumptions that React does on your code base. The first assumption that React does is, hey, if you have two components, two elements with a different type, then whatever is under them, their subtree, will by definition be different. That's the first assumption. The second assumption is, if you have any child elements that are re-rendered in a list of similar type elements, then they do need a key prop that will help React identify the children. Let's look at this in more detail. First, there's the, hey, elements of a different type will return a different subtree. That's the first assumption. Say I have an application that takes two properties, a name and a language. And based on that language, it will include a greeter component that is aware of the language of the user. I'm passing SE, and my switch statement will return the Swedish greeter here, of course. This means that my document object model contains a div with a text element for the hey. Let's do it this way. A div, a hey, that's the first child element. Second child element is text with the name. And then there's a Unicode flag, which is a bit hard to see in the code, but you see it down there in the output there. Now, if I change my language to, for instance, Dutch, because I'm Dutch after all, React will decide, hey, this Swedish greeter just got replaced with the Dutch greeter. That means that by definition, this div, hey, name whatever flags, is now obsolete and can be removed from the document object model. And instead, there's a new div with hello and the name and the flag, and that needs to be added to the DOM. So based on this different type, React can decide what is to be removed from the document object model and what is to be added. But all the other parts of the document object model, as I said, remain untouched. And the second assumption is about this key prop. This is basically the same example that I showed you like a couple of seconds ago, where we looked at the ticker list. But now, let's imagine that at runtime, somehow, my array gets mutated, and the beer company gets removed. Goodbye, Heineken. Now, how would React know which of those tickers needs to be removed? There's no way for React to see, because they all have the same type. They're basically, as far as React is concerned, the same thing. There's just 3 of them. So what it will do, if I don't guide React in any way, it will just remove all 3 of them and then re-add 2. This is not very efficient, of course. For a small list with just 3 items, it doesn't really matter. But if your list contains a couple of hundreds of items maybe, then this may hurt. And that's why React asks you in such a situation to give an additional property which is named key. And the key is a special property. You don't need to implement it somewhere in your component. See, my ticker doesn't know about the key. But the key is just an identification of that element. And the rules for a key are simple. They need to be unique. So for each symbol in my input, I need to have a unique key. Well, in this case, given the nature of my application, the ticker symbol itself is already unique, but this may not always be the case. And the second thing is that it needs to be stable when re-rendering. So if this array changes, and I'm running my ticker list again with the symbols.map invocation, then this symbol, this key needs to have the same value for every element that appeared in the previous render as well. So there's no way that you can use, for instance, a random number or so. But if your objects have a unique identifier which comes from a database, or if they have a property, a value in this case that is by definition unique, then you're good to go and you can use that one. So this is all nice and good, and until now we have seen a lot of things that happen inside the browser. But typically applications don't live only in the browser. That's where the user gets to interact with them. But oftentimes, we want to do something with the environment as well. We want to store some data that the user types. We want to react to things that the user does, because it's user interfaces after all. We might want to fetch data from a remote API. Let's look at how that works. As I said, this is all stuff that does not ship with React itself. So we're basically looking quickly at standardized APIs that browsers nowadays have to do these kind of things. The first thing that we can do is, inside a component, we can store a little bit of state. React provides us with a mechanism to do that, by the way, so this is part of React. And it's basically saying, hey, I have my component, and my component uses a little bit of state. The initial value is 0. And remember when we discussed array decomposition? That's what I'm basically doing here. UseState gives us an array with 2 elements, and I want to have a name for the first and for the second element inside that array. The first element of the array is the actual value, the actual state right now. And the second one is a method that I can use to actually update that state. And in a few seconds, we will see how that works. And since I have a local variable with the counter in it, I can use that in an expression and display it to my user. But if we want to update the state, we need a way to react to events, because that state is not going to update itself in some way. Reacting to events in React, wow, that's a nice one. Reacting to events in React looks pretty much like you might be used to in the document object model, but it's subtly different again. First of all, event names are spelled a little bit different. Again, they're camel-cased instead of all lowercase, as you may have seen before. Second is we cannot have a function name as an event handler. We always need to provide the function itself. Third, an event handler is always bound to a component that takes care of handling the event. And unlike event handlers in the document object model, they cannot be global. Well, technically they could, but I would advise you not to do that. Keep your stuff isolated, you know. And finally, event handlers, when called, because an event fired, will receive a synthetic event. This synthetic event looks pretty much like a native browser event, except it works the same on all browsers, which is a major difference with event handling in the browser, because who hasn't seen these event handlers that are like, well, if the user agent is Internet Explorer, I need to look here, and else I need to look there. You don't need to do that if you're doing event handling in React. So how does that work? In this simple component, I have two buttons, and my buttons have an onClick property. The onClick property is a reference to the function, as I said. You don't pass the function name, you pass the function itself. So increase, there's a small typo there, increase is actually a function, and so is decrease. Well, the functions are empty at this moment. And I have the same line as I had a few seconds ago, where I say, hey, React, I want to use a little bit of state inside this component. There's the counter, its initial value is 0, and I have a function to increase, to update the counter. So if my increase event fires, I want the increase callback to be called, and I can say counter +1 or counter -1. And now if I would click my button, then the callback gets called, and it will in turn invoke the setCounter function, and the setCounter function will update the state, and then my component re-renders, and my state is updated to 1. And if I click it a couple of times, it still gets updated, and it also gets decreased if I click the minus button. So the state is managed by React, and React makes sure that if I update it, that the component will be re-rendered for me. And using the setCounter function, I have a mechanism to actually do that. And that setCounter is invoked from an event callback. I can do the same thing for input elements. For instance, I have an input of type text. There's an onChange callback, and it refers to the update name function. The update name function takes the event, the synthetic event, remember, looks at the target of that event, which is the input itself, and takes the value attribute of that, and uses that to call setName. SetName is an updater function for a piece of state that initially has an empty string as value. And then there's a button, just like we saw on the previous example. The onClick refers to a callback, and the callback will show an alert. And I can use string interpolation here to actually construct a nice message. Stockholm, almost there. And when I click the button, I'll zoom in a little bit. We see that we actually have a pop-up that refers to the name stored in the state of the component and used to construct this pop-up. This is all nice and good, but we still have data that only lives inside our application. What if we want to retrieve data from a remote API, for instance? That's a very common use case, isn't it? Well, again, there's no default component for that in React, but the good part is that every modern browser nowadays supports the fetch standard. So using fetch, we can actually do any kind of HTTP request that we want, retrieve the data, process it, and then the only thing we need to implement ourselves after that is a component that actually calls that API and uses the data to do something useful. So using the fetch API isn't that hard. Let's read it from bottom to top. It starts with invoking fetch itself. And in this case, I'm passing the URL as an argument. Fetch gives me a promise. And a promise is JavaScript's way to say, you know what? I promise that I give you a value, but I don't have it at my hands right now. So let me get back to that later. That promise can be either resolved or rejected. Resolved means, well, as I promised you, here's the data. And rejected means, well, I know I promised you, but I'm sorry, I'm not going to make it. Sorry to disappoint you here. Now the thing is, from a browser's perspective, a request is successful if you get any kind of data back. So even if you get a 401 unauthorized or a 404 no found, yeah, here's your data. So the first thing I do when I have a response is look at the response status. And if it's between 200 and 300, then I consider the request to be successful. Otherwise, I'm replacing the original promise with a rejected promise that just says, well, you did a request, but it failed. It failed with 401 or 500 or whatsoever. If that check succeeds, then I try to read the response and parse it as if it was JSON. Note that in this code, there's a lot of assumptions from my side on what the actual API will do. So I'm assuming it returns JSON. Well, I'm not assuming. I built it myself, so I know. Parsing it as JSON gives me an object structure. And then finally, I'm looking at that object structure. And I'm just interested in the joke property that's inside the response. The next thing I know I need to make is a component that actually uses this. And doing a request from a component is always involving state. Because initially, I'm sending out the request, I'm waiting for the response. This can be milliseconds, it can be seconds. So I have a little bit of state that just keeps track of the fact whether the request is still running or not. I'm using the state construct again, use state, and I'm giving it an object saying, well, loading is currently true. Then I'm saying react. This component has a side effect. When it renders, there's a side effect that you need to fire, but don't block on it for rendering. And the side effect is basically invoke the fetch random joke function, which is marked async. That lets us do an await on a function that actually returns a promise. And if that promise resolves, I have a local variable called joke, and I can say state. I'm not loading anymore because my response is there. And here's the actual data that I was looking for. And as you can see, my API actually returns some data, and the data is now included in my component and displayed. There's a lot of jokes in there. Let's not go through all of them. So if you want to store data persistently in your browser, you cannot store it inside a component, because as soon as you reload the page or you navigate away, it will be gone, because the component is gone. You can use local storage or session storage to circumvent that. Both of them conform to the Web Storage API. Again, this is a standard API in all modern browsers. And it basically lets you store string values, just that. This means that if you have objects or anything else, the best thing you can do is stringify them with json.stringify, and when you read them, do a json.parse, and then you have your object structure back. You can choose how long the data needs to be stored. If it's just for the browser session, you use session storage. If it needs to be there even when the browser crashes or restarts, or your computer actually restarts, you can use local storage instead. Now, this is all nice and good. This was all toy example, so as to say, run directly inside the browser. But what if you want to do serious application development, ship something to your customer? Well, I highly recommend that you install the React developer tools for either Firefox or Chrome. As far as I know, there's no extension for Edge or Internet Explorer. Don't know why. This gives you a lot of additional debugging possibilities when you build your React applications. And it basically looks like this. It lets you look at your application from a component point of view instead of what your browser would normally do. Well, it's just JavaScript. And it lets you debug even when you have source code minification on, and when you use TypeScript and you use JSX, then your browser would normally not understand that, but now it would. Testing your components can be done with just an enzyme, and it's basically a way to verify that your component has a specific behavior without running it in your browser itself. Let's look at that real quick. We have shallow testing, which just tests the component itself, but nothing from the subtree. I'm rendering my component. This gives me a wrapper, and I can invoke the text method on that to inspect the actual outcome of the component. And there's also a way to verify that event handling works correctly. I can do that by asking the wrapper to look for a specific DOM element inside. In this case, it's an A element, and simulate the click event. And when I have done that, I can do an expectation on my mock to see if it has actually been called. This all comes to you. You can combine all of this yourself, but I highly recommend to use the Create React app. This is a project also by Facebook, which is basically a combination of a lot of powerful tools that really make your life as a React developer easier. And it leverages existing tools like Webpack and Babel and ESLint and you know what all to actually give you as a developer a very good development experience. It even lets you reload the page automatically as soon as you update a source file. You install it using the npm I create react app, and then you invoke it one time using create react app, name of the application. If that all goes too fast, by the way, I'll share the slides afterwards, so don't worry. And there's basically 3 commands that you need to remember if you use Create React App. It's start when you start developing. It's build to create a production build with minimized source code, etc. And it's test to run your unit tests. Going one step further, you can even write your own hooks. We already saw a few hooks like use state and use effect. You can actually write your own hooks that are a combination of hooks that you take from React. So for instance, if we look at the component that lets us fetch random jokes from this remote API, I can have a custom hook. Its name must start with use, that's a convention. And it can use existing hooks like use state or use effect to basically combine behavior to create new behaviors. This is especially very powerful if you have remote APIs that your application works with on different places in your application. Then you can just create a hook and just use that hook whenever you need it. So, it's time to wrap it up altogether. If you start using React, then there's a few things that I would advise you to take home with you. Use Create React App because it saves you a lot of headaches when constructing your own build environment. Start thinking of your application as a composition of components and try to target towards small components with just one single responsibility, and think in a declarative way. If you're curious how that all works, here's a few useful links. Create React app, you can Google it or follow this link. And if you're interested where that really boring jokes came from, there's also a link to that API. I hope you enjoyed all this. Please rate the talk in the jfokus app and have a very good conference further on. Thank you.
Okay, please welcome everyone. Now we have a lightning talk with Johan Isaksson from Bryntum. And please start.
Okay, welcome. I'm glad everyone's here. I'm going to do a quick talk on JavaScript performance. And the title of this talk is so long I couldn't fit it on the slide. But I think it was performance lessons learned during component development. And since I'm already introduced, I'm going to skip that slide. So I'm here representing Bryntum. We create pretty advanced JavaScript components for scheduling, basically. And we have a new line of components for which we have focused a lot on performance. And that's why I'm here, not to talk about the components, but to talk about performance. And as almost everyone in web these days, we aim for fast rendering times and good scroll performance. We aim for 60 frames per second while scrolling. And 60 frames per second, that means that we have 16 milliseconds per frame to do whatever we need to do during scroll. It's not a lot of time. And there's a lot of stuff that needs to happen in this short time span. We need to run all our JavaScript. The browser needs to handle rendering, and it needs to paint the end result onto the screen. So a lot being done. And to achieve quick rendering times and fast scrolling, you need to be able to profile performance. And in case you haven't tried that, it's pretty easy in Chrome to record a performance profile. This is a tab from Chrome DevTools. Okay, weird sound. I have made a performance recording here. I will live demo this soon, but just this might be a bit overwhelming if you haven't seen it before. So at the top, in green, we have frames per second during this recording. Ideally, the bars would be really high everywhere, solid green block. They're not here. And they would be as high as the middle one there. On the next row, we have CPU usage. And the color codes are the same as I had on the previous slide. So the orange, that's the JavaScript part. The kind of purple one, that's the browser doing rendering. And the small green ones here, hardly visible, that is the painting. Okay. And then we have the frames of the recording down here. And this green bar shows time per frame. And remember from the earlier slide that we want to stay below 16 milliseconds per frame. So here I have 64, way too much. What we have here is a waterfall chart of the functions that it run during this frame. And at the bottom, we have a summary view of everything that's in view up here. Everything. So all of this is summarized at the bottom. And we can easily see what costs a lot and what we should focus on. So moving on to get to the live demo part. So we should investigate that. We can also see that it produces a lot of garbage. If I zoom this in really long, there are some narrow bars showing that the browser is collecting garbage. And that means that we are producing garbage in that function. We should try to avoid that, and this will go faster. Okay, and Chrome is super helpful with this. I can just select that function in the chart, and I can dive right into the code for it. And it shows me the timings for each step here. And it's pretty easy to see that this row is taking a lot of time, over 2 seconds in total. So let's analyze what it's doing and come up with a fix. Oh, I need to turn that thing off. Let's make this a bit bigger. So here it is. It's generating 100,000 records in chunks of 10 records at a time. If we see here, we have Linda and Steve, and they are repeating, Linda and Steve. The other data is random, but they are repeating. This was the row that cost a lot. It's concatenating arrays. And in JavaScript, this is something worth checking in your code, perhaps. In JavaScript, a lot of the array manipulations yield a new array, meaning that the old array is now garbage. And for 100,000 records at the end, that's a large array being trashed. So we want to do this some way that doesn't create a new array. I'm just going to comment that out and write a new line. So instead of concatenating arrays, I'm going to just push the items of one array onto the other using some fancy newish ECMAScript, the spread operator. If you're not allowed to use that in your code base, you can do this the good old apply style. Would be the same, even faster, but not as elegant. Keep that for reference. Okay, so with that change, hopefully I've reduced the garbage collection and I've sped this thing up. So remember that the initial rendering time was about 2 seconds. And now we're going to reload this page. So from 2 seconds, we went down to 40 milliseconds by changing that single row. So that's pretty good investment, recording that performance profile, tracking that down. So that was my first thing. Avoid array manipulation that creates new arrays in loops. And we learned that the hard way. We have a big data set demo for our scheduler that generates 4 different arrays this way. And for some reason it was slow, but now it's not. Okay, next problem. I promised a CSS fix for layouts. So I'm going to record a performance profile as I scroll. And that's enough. And that was very good results. Well, anyway, we can see in the summary view down here that most of the time as I scrolled, the browser spent on layout. And layout is something that we can affect indirectly from JavaScript, but we can also affect it directly using CSS. Let's say you have a third-party component. You can't change its source. It's layout trashing. That's what it's called when it lays out a lot. If we zoom in here, we see a lot of purple bars. Ideally, those should just appear after each frame. Let me draw where. So they should appear here at the end, not in the middle of a frame. We want to avoid that. We can't solve that with CSS, but we can make the layouts a lot cheaper. So if I hover one of those small bars, it highlights what it's laying out. So the entire page is laid out a lot of times here. And in CSS, there's an attribute called, or rule called contain, which by default is not enabled. If I enabled it for this component, I set it to strict, which means that it will contain layout, paint, and sizes, I think, or something like that. Easily checked on MDN. I'll reload the page, and I make another recording as I scroll. Now, the layout cost is no longer the most expensive thing going on. If we compare this to my previous recording, the one down here, well, it's a bit hard to tell, but there's less purple on the top one, which is the new one, than on this one. On the previous one, the layouts cost 48% of the processing. With the rule on, the cost for them is down to 17%. So nice improvement for a single line of CSS. Also, if I zoom in on one of those bars and hover it, you will see that it only laid out a really small portion of the page instead of the entire page. Okay, a couple of minutes left. One more thing. So I didn't actually fix the layout problem here. Let's track down what causes it. And since I already have a recording, I can just click one of those layouts and click the file, and Chrome will take me to the code that caused it to layout. Let me zoom that up a bit. And in this case, it's just reading an attribute from an element in DOM. So this will be one of the cells in this grid. It's reading the height of it. So it's not writing to DOM or changing it. It's just reading. Depending on what you have done previously in this frame, that might trigger the browser to re-layout everything on your page again. So we want to avoid that, just to see the difference. I'm just going to throw that code away. I have no time to do a proper fix. Reload the page. Record performance. Okay, so now layout cost is down to 12%. And if I zoom in, it's only doing layout at the end of the frame. And that's what I wanted. Okay, that was a super quick live demo in this quick talk about performance. And in case you didn't get all of that, oh, I need to just run this again. No. And there's some links in these slides. I have uploaded the slides. They will be available somehow on the jfokus site. If there are questions, you can come and find me at the Brinton booth. We're outside here. When you grab coffee or anything, feel free to ask stuff. I'm glad to discuss JavaScript performance. It's fun. And I think that was about 15 minutes. Thank you.
Okay. Welcome to this session in which we will discuss Java in containers. So first of all, I want to say that it's great to be back. So in fact, I was at jfokus in 2017, same room, same stage. And back then, so I did a presentation, and back then someone in the audience tweeted that it's not a real conference unless you read Oracle's safe harbor statement at least once. So here it is. Please enjoy. So my name is David Delabasset. Despite my French accent, I'm not French, but I'm from the French-speaking side of Belgium, where I work for Oracle. So I'm part of the Java platform group, so basically the group that is responsible for Java, the platform, and OpenJDK. I'm remote, so I live in Belgium, but I report to the organization in the States, in California. And if you have any questions, or if you want to do any follow-up, you can reach me on Twitter, or you can try to grab me during the next 2 days. Something else. Apple has recently launched a new MacBook with a new keyboard. Why I'm telling you that? Well, unfortunately, I have the old models with the broken keyboard. So today I'm going to do a few demos. If any of my demo fail, it's not my fault, it's the keyboard. Not only that, this is also a subtle message to my manager. Okay, before we talk about Java into containers, and first I have to mention, so first that talk was Java into containers, but then I turned that into JVM into containers, because at the end of the day, it's really about how to make sure that a Java virtual machine runs well and correctly within the containers. At the end of the day, a JVM only understands bytecode. Most of the time, that bytecode is coming from a JavaC compilers, but if it comes from another compiler, it will provide the exact same behavior. So it's really about making sure to run the JVM correctly within the containers. So containers, so who's using containers today, by show of hands? So yes, that's what I've guessed. So I wouldn't spend too much time on explaining what a containers is. As a recap, it's basically a way to package software and its dependency into a unit that we can easily move around. Very convenient for development, but also for deployment, for testing, and so on. There are multiple containers runtimes. At the end of the day, what I'm going to discuss today applies to Linux containers runtime that are based on cgroups and namespace. So containers are leveraging some of the Linux kernel facilities, such as cgroup, namespace, also union file systems, and so on. Whatever we're going to discuss today applies to any container runtime that is using cgroups and namespace. I'm going to use Docker for my demo, but it will also work with different runtimes. So we shouldn't confuse containers with virtual machines. Containers are using cgroups and namespace for the operating systems, but one drawback of containers is the isolation level that they provide. So we have some form of isolation, but clearly the isolation is not that great. Why? Because basically we are running and we are sharing the same host operating systems. So everything runs on the same host operating system. On the other hand, we have virtual machines that use technologies such as an hypervisor to provide a stronger isolation. And then we can have different operating systems within the VM that we have on the host itself. There is now what we call kata container, because one of the benefits of VM is basically the isolation that we have, but one of the drawbacks is the cost. Starting a VM is very expensive. Kata containers basically brings the benefit of the two. So we have almost the startup time that we can have with containers, but we have the isolation that we have with VMs. So basically it works with a lightweight VM, and then we have containers on top of that. So let's now switch gear and talk about Java. So obviously, containers are widely used in the Java space too, because of multiple reasons. The cloud is one of them. And if we look at the landscape of our toolings, well, you see that all the tools in the Java space are evolving to support containers. So we have multiple Maven plugins that we can use to easily create a container image. There's Jeep from Google that we can also use to create container image. Test container. IDE also those days support the ability to directly create containers out of the IDE itself. If you look in the microservices space, most of the frameworks support out-of-the-box containers. So look at Helidon, Quarkus, Gypsers, and so on. You basically build your artifact, and you can directly turn that into a containers. The serverless space is also heavily relying on containers. that's true for the Java space, but also the serverless space at large. So whatever we're going to discuss today apply to all that space at large. So what do we want from a JVM that runs within the containers? Basically, there are two things that we need to tackle. First, we want to make sure that the JVMs behaves correctly when it runs within the containers. And we'll see why it's important. Then there's the question about making sure that we have a good latency. By latency, I mean whenever we start a container, we want to make sure that the Java code that runs inside starts as quickly as we can. Because containers tend to be disposable. So containers are easy to build, they are easy to ship around. So we're going to tend to use a lot of containers. So obviously, we don't want to have to wait like for a VM minutes for that container to start. So that whole latency question is something that is very important within that space. So I'm going to first start with a very basic demo. So it's really the hello world of containers. So for that, I'm going to switch to a Unix VM, and procs that has 8 CPU. So I have, let's see. So this is a basic hello world application that basically look around at some of the system properties. So which version am I using, which Java vendor that JVM comes from, am I running within the containers, and so on and so on. Then we have a Docker file to containerize that. Yeah, it's, so let's, sorry, no. Sorry. And I'm going to use, for example, this one. So the Docker file is pretty basic. So I start from a base image, java-latest. I create a directory. I copy my source. I compile it, and I run it. So let's build that. So build -t. Let's call it RN. And this is our context. No, sorry, I'm not in the right directory, and my context will be too big. So yeah, that one is good. So Docker build, -t, and this is our context. Let's run that. So it's run. So hello world, here is what I see. So this is a quite old version of Java. It comes from Oracle. I'm indeed running inside the containers. I have 8 CPU. So the JVM sees 8 CPU, so it will configure accordingly 7 threads for the command for join pool, and it's going to use that much memory. So we can already see, if we do this, Docker IRN image. So the size for that very basic application is over 600 megabytes. This is already a big issue. This is a pretty basic code that basically just displays some information, and for that, we need to fetch an image that weighs over 600 megabytes. And why this is an issue? Well, each time we need to run that code, basically the container runtime will have to pull that from a registry. Obviously, ideally, the registry will be co-located on the network, on the same network, but still, to just display some information, the container runtime will have to fetch over 600 megabytes. So we're going to see how we can work around those issues a bit later. So back to the slides. So latency. Basically, there are 2 levels on which we can work when it comes to latency. First, there is the time it takes to start up the container, and then there's the time it takes to start the containerized code. So basically, the Java application, the JVM, and the Java application. So there are 2 levels on which we can work on. The container startup, well, as I alluded, we need to make sure that our container is as small as possible. Our container image should be as small as possible. So you know that container is basically a stack of images, and we need to make sure that basically each layer is as small as possible. When it comes to Java application, there are 3 types of layer. There is the Java top to bottom, there is the Java runtime layer that include the Java application and its code. Then there is the Java runtime, that's basically the Java virtual machine. And then below that, we have the operating system layer that will host our JVM. So we basically need to make sure that we shrink as much as we can those layers. So if we look at the Java application layers, basically the thing that we can, there's not much that we can do. I mean, we can give you advice and best practices. Typically, watch out the dependency that you are using. Don't bring any transitive dependency that are not needed, those kind of things. It's also a good idea to try to leverage some of the cache mechanism that we have in the containers. And that's why fat jar are maybe not a good idea. Try to basically have different layers when it's possible. And that way, you will leverage the cache, and only the layers that will be updated. So you don't have to pull all the layers again and again. But still, there are technology on the Java side that can also help us, like CDS, class data sharing, that we're going to discuss a bit later on. Now, at the Java runtime layer, there are things that we can do to reduce the size of that layers. And what we can do is use jailing that has been introduced in Java SE9. So part of the modularity, we have these jailing tools that give us the ability to create a custom runtime image that will only include the module that our code needs. So our application will have a runtime with just the capacity, the feature from Java that is needed by the code. To give you some sense of the benefit that we can get by using jailing, I started from a serverless Java function running on FN with OpenJDK 13. So first, we start from a whole JDK. A whole JDK 13 weight 316 megabytes. It's not a good idea to run Java application to run them on top of a JDK. Why? Because basically, you want, from a security point of view, to reduce the potential surface attack as much as possible. So it's kind of stupid to carry a JavaC compiler within your runtime image, because we know that at runtime we won't need a JavaC compiler, and so on and so on. So we need to use a GRE instead of a JDK. The thing is that since Java 8, there's no, since Java 9, there's no GRE anymore. So that's one thing. But on the other hand, we can use jailing to basically create our custom runtime image. That would be kind of a custom GRE. If we do that, so that's what I did next. So I basically created a custom runtime with all the modules. We go from 316 megabytes to 178 megabytes. So that's a huge win on one hand. On the other hand, it's very stupid to create a runtime image that includes all the modules, because there is no way your code can use all the modules from the platform. So what I did next, I used jailing as it was designed to be used. I basically created a runtime that only includes the modules that my serverless Java function needs. So for that, I've used JDEPS to get the dependency. And I went from 168 megabytes to 50 megabytes. So 50 megabytes, that's basically a complete Java runtime to run my serverless Java function. We can remove, using jailing, some information that is not needed, like header file, man page, and we can also strip out some debug information. If we do that, from 50 megabytes, we will go down to 44 megabytes. In jailing, we have two level of compression. If we do that, level 2 is basically zip deflate. We'll go from 44 megabytes to 34 megabytes. So basically, by using jailing, we can go from a whole JDK that weighs over 300 megabytes to a custom Java runtime that, in this case, only weighs 34 megabytes. Now, something to mention. We did that to basically reduce as much as we can the size of the Java runtime layers. If you look at the bottom of the tables, I'm using compression. If I'm compressing stuff, I will have to decompress them. Maybe the benefit that we will get by saving a few megabytes there is something that we will lose when we will have to decompress stuff. So we should maybe stop at 50 or 44 megabytes, and we're good with that. That's something that you would have basically to measure. So using jailing is something that we can use to shrink the Java runtime. Now, what about the operating system layer? Well, there are multiple things that we can do. The first obvious things to do is to use a Slim distro. And watch out, it's not because there is Slim in the distro name that it's Slim. So that's something that you need to look at. So using a Slim distro is one thing. We can also rely on distroless distro. So that's a Google effort. And The Java 11 distro from Google weighs 199 megabytes. That's a lot, but that's basically the operating system and Java 11. So that's everything built in. So that's one thing that we can do. Something else that we can do is use different tools that mimify our Docker image, such as Docker Slim. Now, I put their claim between quotes because so they're claiming that they can mimify the image up to 30 times. The thing is that I've tried and it doesn't work, at least on my machine. So they are supposed to come with a new version that should solve my issue. So until then, I don't know. So that's one thing that we can do on the operating system layer. Something else that we can do is we can leverage lighter operating systems, such as Alpine. So Alpine is a security-oriented Linux distribution that weighs between 5 and 6 megabytes. So basically, in those 5 to 6 megabytes, you will have a full-blown distribution that you can use to run your code. Obviously, you will not have all the bell and whistle that you have from a typical distro, such as grep, package dependency management, and so on and so on. But at the end of the day, it's good because, again, within the container space, we want to reduce as much as we can the potential surface attack of our containers. The issue with Alpine is that it uses muscles. And OpenJDK relies on libc, jlibc. So jlibc is basically the library that the C++ code of Hotspot, of the JVM, because Hotspot is written in C++. That's the library that it used to talk to the underlying operating system. So OpenJDK use libc, Alpine use a different one, which is muscles. So we can either use Alpine package glibc, which is an intermediate layer that will basically do the mediation between muscle call to, libc call to muscle calls. I'm not a big fan of that. Not only that, well, I find that solution a bit tricky, and also it had anyway weight to our image. So that's not, to me, that's not a good solution. Something else that we can use is Portola. So Project Portola is a project within the OpenJDK community whose goal is to build OpenJDK on top of muscles, so that you can run directly OpenJDK on top of muscles. Technically, so it works nice. The thing is that it's not, well, we don't do all the tests that we do with a typical OpenJDK distribution. So you can use it in distribution at your own, in production at your own risk, but ideally don't do that. That's why at this stage, so right now the current version of OpenJDK is 13, so we're giving the build for Portola on 14. And when 14 will be released, we will provide the build for Portola on 15, and so on and so on. Having said that, if you want to help us to port OpenJDK to muscles, contributions are welcome within the project Portola. So feel free to join and jump in and help us. So I will do a demo to illustrate that. And one of the comments that I had when I saw the result that I had when using Jailing with serverless function is that, well, it's good, but it's a serverless function. What I'm using is a server. So what benefit would I get? Well, and that's true. So for this demo, I took a server. And for that, I'm basically using the Minecraft server. At the end of the day, it's a server that runs on the network, so we're good with that. So let's see. Let's go. So what I have is a Docker file that will containerize my Minecraft server. So you see that I'm starting from OpenJDK 14. Everything happened here. So here I'm using Jailing to compress level 2, and basically I'm creating a custom Java runtime with all the modules and just the modules that Minecraft server needs. So here I specify by using the add module flags which modules are needed by the Minecraft server. So that's the first step. That's a multi-build multi-stage build. So this is the first stage. Then I start from a base image, an Alpine base image. I create a directory. I copy all the files that the Minecraft server needs, like the license, the properties file, and the jar. And then I copy my runtime, my custom runtime from the first stage, and I'm done. So let's build that. So build, I said, -t. That's the keyboard. I told you. Also, I'm going over my mobile phone, so that's why it might be a bit slow. OK. So I have this mine image. Now, we can already look at the size of that image. It weighs 100 megabytes. So in 100 megabytes, I have an operating system, I have a Java runtime, and I have my server application. We can have a look at exactly what we have inside. So for that, I'm going to use Dive. OK, so on the left side, you have the layers, and on the right side, you have the content of the layers. So the first layer, the 5.5, is Alpine. So that's the operating system. That's the Linux operating system needed to run that code. Then we have 181 bytes. If we look there, that's basically the license. Next layer, property files, and next layer, the jar. It would have been a good idea to put those 3 files in a single layer, but. And then we have this 58 megabyte layers, which is my custom runtime. So it's basically my Java runtime with the 12 modules that are needed by my Minecraft server. And at the end of the day, I indeed have a complete Docker image that only weighs 100 megabytes. So whenever that container will have to be invoked, the container runtime will just have to fetch that 100 megabyte through the network. So Minecraft server, OpenJDK 13, 12 modules, 88 megabytes. If you strip debug, so if you strip the debug and the native debugs and the Java debugs attributes from that image, you will save 14 megabytes. If you use compress1, you will save from the 88 megabyte, you will save 18 megabytes. If you use compress2, from the 88 megabyte, you will save 31 megabytes. And if you remove the header file and the main page, you will not save anything because they are not included by default. So this is on using the OpenJDK latest. So OpenJDK latest Docker Hub image is based on OpenJDK, so the Oracle OpenJDK build that runs on Oracle Enterprise Linux. But if you are using other Linux distribution and other OpenJDK distribution, you might have different results, such as this one. So OpenJDK 13, a custom runtime image with 1 module weight 48 megabytes. So you will not be able to go lower than that. 48 megabytes. Debian Buster with the Debian OpenJDK 13 distribution, a custom runtime with that same Java-based modules, almost 500 megabytes. And there's no typo there. Why? Because the Debian OpenJDK builds include the native debugs information. Luckily for us, we have these new jailing flags in JDK 14 that we can use to strip out the native debug information. If you do that, you will have a custom Java runtime with the Java-based module that weight 51 megabytes. So you are not reaching the 48 megabytes that we have with Oracle OpenJDK build, but we are almost on parity. So if you are using such distribution, and if you are getting funky numbers, well, look at the native debug information. So we've talked about what we can do at the container level to reduce the startup time. Now let's look at the Java level. What can we do to improve the startup time? This slide shows the startup time of a simple Hello World application between Java 8 and 9. And clearly, smaller is better. So that clearly means that between 8 and 9, we had a big regression. And there is an easy trick to solve that regression. Basically, if you use the latest and greatest, there is an ongoing effort going around the startup time. And you see that between 8 and 14, well, the startup time for that same code is basically more than twice as fast. So that's an advice. If you can, and if the startup time is important to you, try to use the latest version of the platform. This is basically the same slides, but so we have a Hello World application. We have a Hello World application that is using Lambda, and a Hello World application that is using concat strings. And basically, you see again and again that with each release, there is an ongoing effort to reduce the startup time. If you want to have more information about the startup time and Java performance in general, there is the blogs from Class, who works at Oracle in Stockholm, and is basically putting a lot of useful information about Java performance and startup time there. So I encourage you to check that one out. OK, something else that we can work to reduce the startup time of Java application is CDS. We can use class data sharing. Anybody is using CDS today? Anybody knows what CDS is? OK, 1-2%. It's a bit scary because CDS is in the platform since Java 5. So 15, 16, 17 years ago. So the basic idea of CDS is basically the following. When you start a Java application, so you have a bunch of class on disk, the JVM will have to load that and turn that into something that it can use to basically run your code. So you have a class with bytecode, and that bytecode will have to be scanned and parsed and checked and so on to basically be turned into something that the JVM can exploit. And the thing is that obviously with your Java application, you don't have one class, you have a bunch of classes. So that means that each time you start your application, you basically have to go through all those steps again and again. The idea with CDS is that it will only happen once. So you will start the JVM, and the JVM will basically do an in-memory snapshot of all the representation of your code in memory. It will dump that to disk. And the next time your Java application is started, it will bring directly that into memory, so that the JVM doesn't have to go through all those expensive operations on all the classes. So that's the basic idea with CDS. We have that in the platform since Java SC5. It was pretty limited back then. It was only for the serial GC. It was only for the run. Back then, it was only for the runtime classes, so the rt.jar of Java SC5. But CDS has been evolving since then. So let's have a quick demo of CDS in action to see what we can get. So let's see. Yes. So I have this Hello World application, same code. So this is my application. In this case, it doesn't run within the containers. So I'm going to compile that. And I'm going to use that. I'm going to invoke that application multiple times without and with CDS so that we can see what we get in terms of. So for that, I'm going to use perf42, which is basically just an alias that is invoking perf 42 times. Why 42? Because 42. So perf 42 Java. So hello world. So the first time I'm going to avoid CDS. So 42 times my application is invoked. And on average, it takes like 205 milliseconds. So let's do the same exercise, but with CDS this time. And to use CDS, it's pretty easy. We just have to use the default behavior. So 205, we can already see that it scrolls faster. So this is good. So from 205, we went to 135 milliseconds to invoke that Java application. So basically, oops, 35, whoops. We are like at 65% of the time with CDS than we are without CDS. So this is a huge benefit because it comes for free. That's something that the platform provides. So I told you that at the beginning, CDS was limited to the runtime classes, but now not anymore. That's something that we can also use for our own classes. So that's my CDS demo. Obviously, my application is pretty basic, so that's why I have a huge win. So don't take my words about the benefit of application CDS. So application CDS is basically for the class of the application itself. This is a quote from Gunnar from Red Hat, and on Quarkus, they are seeing a reduced startup time of 30% with app CDS. Another quote from Charles Nutter, who runs the JRuby project, and JRuby in itself is a huge project. That's the benefit that they are seeing with CDS. So just look at the bottom. So they go from 853 milliseconds to start up JRuby to 717 milliseconds with app CDS on a Java 13. So this is something that you should leverage. And that's something that we should also leverage when Java runs within containers, obviously. So I mentioned that CDS is not new, introduced in Java SE5, but it has been evolving since then. So at the beginning, it was quite limited. So CRLGC, only the system classes. Later on, in Java 9, we have introduced application CDS and support for additional GC. But back then, it was a commercial features of the Oracle JDK. So you basically had to pay to use it. Good news is that application CDS was open source in Java 10. So that's something that since Java 10, that's a feature that is part of the platform. In Java 12, we have introduced default CDS archive. So you don't have to create the archive, the runtime archive, if you will. In Java 13, we have introduced dynamic CDS archives. So before to create the archive, so basically the dump of your classes, you had to go through multiple steps. In Java 13, there is a flag. You just launch your application, and you will have the archive of your own classes created directly. So it's more convenient. And we are keeping improving CDS with all the release. So something else that we can also leverage to reduce the startup time of our Java code is to use GraalVM. GraalVM, it's an high-performance polyglot virtual machine developed by Oracle Labs. It provides many capabilities. On the Java side, two well-known capabilities is the JIT compiler. So it's basically a JIT compiler that can replace C2. One of the unique things of that JIT compiler is that it's written in Java, and you can plug it directly into a hotspot. They also have an AOT compiler in the form of a tool called native image. So the goal of the native image tool is basically you feed it with some Java application, and at the end of the day, the artifact that you will get out is an executable for a given target. So multiple reasons to do that. Reduce the startup time. So it's not a Java bytecode running on top of a Java virtual machine, but it's really a native executable. Improve footprint. So technically, your code running in that executable will consume less memory because it doesn't have the overhead of, for example, a JIT, those kind of things. And the side effect is also the reduced image size. So that's something that we're going to see. So let's see. For that, I'm going to go back to my Mac. Let's first see which Java version I have. So 13, let's switch to Graal. So one of the perks of working within version GN version. Shell. So yeah, one of the perks to work in the GPG group is that you need to deal with a lot of versions of Java on your machine. So I want the shell to use 11. OK, this is indeed, you can see that it's a Graal VM. So let's see. So I still have this Hello World Java application that I'm going to compile. And then I'm going to pass it to native image. So I'm going to pass the class to native image. Hello world class. So what's wrong? Found defunct image build server. That's a bit scary. Hello world class. Sorry? Oh, oui. Thank you. That's the keyboard. OK, so what it does, so wait, I think I have a slide. So. OK, so what I've done here, so I've passed my Java application. In this case, it was a simple classes to the native image. That's not the keyboard, that's the Mac. OK, so I've passed that to the native image tool that will basically look at all the reachable code path, and it will, at the end, compile that code into a native code. And what I will get at the end is a native executable. And if I go back here, so I should have a hello world. So if I look at that file, hello world, that's a Mac OS executable that I can obviously launch. So what it sees is a Java 11.05 version. And to prove you, so I'm going to switch back to, let's say, 14. Yeah. So my current Java JVM running on my Mac is Java 14. But if I do that, you'll see that it still sees the basically substrate VM, so the lightweight VM that has been embedded in that native executable. Something to mention is the size of that guy. So 8 megabytes. So in 8 megabytes, you have basically everything. So that's, well, there's no Java runtime because it's directly embedded within that executable, and your Java code itself. We can time the invocation, so 10 milliseconds, and we can compare that to the same code running on hotspot, so hello world. Sorry, you're right. Well, it won't be a lot. You see, 3 milliseconds. Yeah, we can compare that to, so let's see, Java. We can compare that to the same code, but this time running on top of hotspot. And, well, it's a bit slower. So let's see, 13 milliseconds and 151 milliseconds. So not only we have a smaller executable, but it starts way faster. Having said that, there are a few limitations with Graal. So right now, Graal only supports Java 8 and Java 11. There is this mostly supported branch that basically means that reflection, dynamic proxy, GNI, and so on works, but you have to do some configuration works to make it work, right? And then there are a few things that are not supported, such as invoke dynamics, dynamic class loading, unloading, and so on and so on. Now, the thing that you have to keep in mind is that with Graal VM, native image, what you will have at the end of the day is a native executable. So you will not be able to use the typical tool that, like GMC, that you are using to, for example, observe your JVM. You will not be able to use the Java debugging tools that you are used to use, and so on and so on. And also, portability is kind of lost because if you want to deploy your code on multiple platform, you will have to compile for those different platforms. So there are a lot of benefits of using a native image, but there are also a few drawbacks. Something also that you don't have in a native image is you have a pretty basic GC, like a serial GC. So if you have long-running code, maybe you are better to leverage the hotspot GC, such as ZGC, and so on. So that's something that you need to keep in mind when you're using GraalVM. There are pros and cons, like hotspot, pros and cons, right? OK, let's switch to the last point that I want to address today, is about the fact that the JVM should behave correctly when it runs within a containers. So I'm not going to go into details about that slide, but basically this slide shows that we're making the right investment in OpenJDK to make sure that hotspot runs correctly when it runs within a JVM, when it runs within a containers. It's something that we have started since Java 8, and since then we have continued to do improvements. If you look at the bottom of the slide, there is an enhancement that has been merged 2 weeks ago. That's support for cgroups v2. If you are using Fedora 31, for example, that's something that you will need. And that's something that will land in JDK 15. So why it's important that the JVM behaves correctly and understand that it runs within a containers? Because of the JVM ergonomics. So since Java 8, we have this notion of ergonomics that basically, it's the ability that the JVM has to auto-tune itself. So the JVM will look at a few metrics, basically the memory that it has access to, and the number of CPU that it has access to. And based on those two metrics, it will configure the JVM so that you have a good default out-of-the-box behavior. So it will pick a GC that is appropriate, it will set the heap size, and the JIT compiler to use based on those criteria. So let's have a look at why this is important. Let's see. No, sorry, I was on the... So for that, I'm going to use the image that I started with. OK, so this is the image, the Hello World application that we did at the beginning of the presentation. So this one sees that it has 8 CPUs. So the JVM configured the command for join pool to use 8 threads. The runtime max memory is also configured based on the available memory and the max RAM percentage flags that is 25% by default. So let's see. So this VM has 8 CPU. So that's why the JVM sees 8 CPU, and hence we have 7 threads. So now what I'm going to do, I'm going to basically say that my JVM, my container can only use 6 CPU out of the 8 that my VM has. And what we can see is that, well, the JVM still sees 8 CPU, and hence it's configured to use 7 threads. And I could go down up to 1 CPU, and it still sees 8 CPU. Why? Because, well, I'm using, in that particular case, I'm using a very old Java version that is not container aware. So that's something that you want to avoid. And I'm going to show you that. Let's see. So I'm going to use this one. Let's see. So this command runs OpenJDK. So by default, it's 13. Within OpenJDK with the Java command, we print all the flags, and I explicitly disable container support, because container support is enabled by default. And let's see. So you see that in this case, I have a JVM OpenJDK 13, 1 CPU, and the default GC that is configured is G1 GC. Clearly, that's not going to work. Why? Why? Because this JVM is not container aware. Now, if I if I take the default behavior, you will see that now, so my JVM has 64 megabytes of memory and 1 CPU, and you see that G1GC is not used anymore. So now it will behave correctly. So with 1 CPU, it's better to use serial GC instead of G1GC. So that's the kind of trick that JVM does. But for doing that, we need to make sure that it can seize the right metrics. That's why we need to make sure that we are using a JVM that is container aware. So this is true for the GC that is used, the memory, and basically everything that is based on those metrics. So for example, this container has only access to 64 megabytes of memory. If I disable the container support, or if I'm using an old version of Java, the JVM will basically seize the memory of the host, like 32 gigabytes. And clearly, it will very quickly overconsume memory, and it will basically be killed by the container runtime. So let's see. Yes, it's time to wrap up. So JVM containers, that's what we have discussed today. We have discussed about techniques that we can use to reduce the latency, so basically improving the startup time of the container itself, shrinking the layers at different levels, using J-Link, for example, using Alpine. And then we also discussed some of the techniques that we can use on the Java side to improve the startup time of the JVM and the Java code. And clearly, those techniques can also be used outside of containers. We've then discussed about why it's important that the JVM behaves correctly when it runs within containers. We saw that it's important to give the right metrics to the JVM ergonomics to make sure that it's not killed by the container runtime itself. So please use the latest Java version, and please never use Java latest as I did at the beginning. That image is very old. It's not container aware. That's an image that you can only use when you're on stage and you are doing a demo in front of a bunch of people. Don't use that in production. I also use container support flag. You don't have to, because if you are using a recent version of Java, it's enabled by default. That's a flag that you will only use to explicitly disable the container support. And I'm not sure that you want to do that unless you want to do demo like I do. If you cannot use the latest Java version, at least rely on an actively supported Java version to make sure that it is container aware. And don't use a JDK to run your Java code within a container, but please use a JRE or a Java runtime. And we saw that using J-Link, we can create custom runtime images that basically fit our needs. And for the rest, it's really container as usual. So you can use all the tools in the container space, and so on and so on. So I'm going to conclude with this. The top 10 most popular Docker containers contain at least 30 vulnerabilities. The good news, Java is not there. The bad news is that we are not immune. This was back in May, where Debian basically shipped an OpenJDK build GA before it was even GA on the OpenJDK community. I mean, it's easy. Everything is open source, so the source is there. So someone took the source, built it, and tagged as GA. So watch out. Something else that I saw last week. There's no OpenJDK 11 Alpine build for Alpine. But someone on the internet said that, OK, that build is pretty close to what it should have been as if it would have been GA. So you can consider it as the OpenJDK 11 Alpine GA release. There's no such a thing. The problem is that many people now rely on that pseudo GA release. And then when you deep dive, and if you look at the Docker file, you realize that basically it gets over HTTP from a university in Austria, a build. The good news is that they are checking the checksum. The bad news is that they are checking the checksum from that same host. So basically, you get a random build that a lot of people are using, and it's clearly not an OpenJDK 11 build for Alpine. It's something that will work, but we don't know what's inside. So please choose your base image wisely. Also choose your OpenJDK distribution wisely, and secure it. And don't trust someone else to secure your base image. Don't trust someone else to choose your OpenJDK build. And don't trust what you read on the internet. With that, I'd like to... Yeah, there is one which is very secure. You see? Don't trust someone else to secure it. That one is very secure. You see? So, thank you.
Well, hi, welcome to my talk on the essential characteristics of the microservice architecture. We're just going to define the motivations for using the microservice architecture, talk about what it is, and then discuss some of the design issues that you'll face when using microservices. And the talk is structured as a series of visual metaphors, so various shapes, triangles, hexagons, and cylinders, and so on. But before I talk about that, let me introduce myself. I want to start by saying I really appreciate the theme of the conference, because when I saw the first Star Wars movie, when I was a kid, I think that was one of the inspirations that ultimately led to me being the nerd I am today. So over the years, done a number of things. I've worked on Lisp systems in the late 80s, early 90s. I wrote the book Pojos in Action, which came out 14 years ago now. I started tinkering with Amazon EC2 back in the early days of cloud computing, and ultimately created the original Cloud Foundry, which was a PaaS for deploying Java applications on EC2. And then pretty much for the past 7 years now, I've been focused on the microservice architecture. So I travel the world doing consulting and training, helping organizations use the microservice architecture successfully. I have a startup that's creating a platform to simplify the development of business applications. My book, Microservices Patterns, came out November 2018. You can get it with that discount code. And I also have the website microservices.io, which is a popular resource for learning about the microservice architecture, patterns, articles, example code, and there's also an assessment tool as well. So anyway, that's me. I just do microservices. So as I said, I'm going to introduce the microservice architecture using a series of visual metaphors. The first one I want to talk about is the success triangle. So this slide really sums up the main motivation for the growing adoption of microservices. So there are two themes driving the adoption. The first is, as Mark Andreessen said in 2011, software is eating the world. In other words, it doesn't matter what industry you're in, the products and services that you deliver and how you engage with your customer is increasingly being done by software. So in other words, every company needs to master software development. And then at the same time, the marketplace within which companies operate is becoming increasingly sort of more dynamic, more volatile, uncertain, complex, and so on, which then leads companies to forces companies to innovate at a much faster rate. And because their products and services are based on software, what that means for us in IT is that we need to deliver software much more rapidly, frequently, and reliably. And you can quantify that with these 4 metrics. The first 2 concern velocity of development. There's lead time, which is the time from a developer committing a change to that change going into production. You want to minimize that. There's also deployment frequency, which is how often an organization is pushing changes into production. And interestingly, the ideal is at least once per developer per day. And then at the same time, there are the reliability metrics. Change failure rate, how quickly can you recover from an outage? And then also, the change failure rate, which is the percentage of deployments which cause an outage. And then there's mean time to recover, which is how quickly can you detect, diagnose, and then recover from a production problem. And then there's another trend, which is the applications that we build today tend to live for a very long time. It's quite common to have applications that are absolutely mission critical that are 10 or 20 or even 30 years old. And of course, over that long time frame, technology changes. And we need to be able to modernize applications so that they remain current. Today, there are just far too many applications that are just built using absolutely ancient technologies from companies that no longer exist. So in my view, in order to deliver software rapidly and frequently and reliably over a long period of time, you need what I call the success triangle. In other words, you need three things. You need to have the right process, the right organizational structure, and you need to have the right software architecture. What that translates into today is that you need to use Lean and DevOps, which embraces continuous delivery and deployment as your development process. From an organizational perspective, you need to structure your engineering or your IT organization into a team of teams, these small 5 to 9 person cross-functional autonomous teams. And then you need to have the right architecture, which, as you could imagine, is often the microservice architecture. But let's look at why microservices are important. So the next visual metaphor I'm going to talk about is the scale cube, which is sort of one of the ideas that motivated me to look into the microservice architecture. So, in order to do DevOps plus continuous delivery and all of that, and have autonomous teams and have long-lived applications, you need an architecture that has particular architectural qualities or so-called ilities. So in particular, to do DevOps, you need an architecture that's highly testable, highly deployable, and highly maintainable. To support autonomous teams, you need a modular, loosely coupled architecture. That's basically an application of Conway's law, which says that the architecture and the organization that created it are mirrors of one another. So if you want to have loosely coupled teams, you actually need to have a loosely coupled architecture. And then to have long-lived applications, you need to have an architecture that's modular and evolvable, where you want to be able to easily upgrade it to adopt new technologies. So if we look at the standard architecture that most of the many applications we build, it's a monolithic architecture. So internally, it's actually somewhat modular. It's comprised of layers: presentation layer, business logic layer, and then there are various modules that implement different chunks of functionality. And it talks to a database, of course. So despite having a sort of logically modular architecture, what then happens is all of those modules get packaged up into a single deployable unit or executable, depending on which language you're using. In the case of Java, that would be a WAR file or an executable jar file. So you just build the application, and that's what gets deployed into production. So that's the monolithic architecture. It's important to remember, however, that it is not an anti-pattern. For a large number of applications, it is an entirely suitable architecture, because you can have a monolithic application that is highly testable, highly deployable, maintainable, so on and so forth. It's not always a problem. The problem occurs, however, is that successful applications have a habit of growing. So you might start off with a small team of people building a relatively small application, but over time, the application is getting bigger and bigger and bigger. And then if you're making money, you hire more developers, so the team is growing, and so the rate of change of your application is also increasing as well. And you might try and split up into multiple development teams, multiple Scrum teams, but ultimately all contributing to the same increasingly large code base. And then not only that, once applications get rather large, they don't fit in the heads of the developers anymore. They're much more difficult to understand, and I think that can lead to a breakdown in modularity as well. So you end up ultimately, you're not necessarily with a big ball of mud. And then at the same time, the technology stack that you're using is becoming increasingly out of date. Because you've got such a large code base, it's actually quite difficult to upgrade to new versions of frameworks, or to switch frameworks, or to switch languages, or so on. So you tend to be locked into the technology choices that you made at the start of the project. So it ends up looking like this. Over time, the size and the complexity and also the value of the application is continuing to increase. But at the same time, all of the desirabilities are declining, and so development just gets slower and slower and slower. And this can end up being an existential threat to the business, because where you need to be in terms of agility, so to speak, is actually delivering software faster and faster, not slower and slower. So you end up with this, what I call this sort of gap between the two, where there's a risk of disruption. So that can happen if you're not taking care of these illities. And for me, that then leads you to the microservice architecture. So I was sort of first introduced to this way of thinking when I read this book known as The Art of Scalability, which was written by some folks at eBay. And if you remember back 10 plus years ago, eBay were a thought leader in web application architectures. And in the book, they introduced a three-dimensional model of scalability, the scale cube. So you have x-axis scaling, which is horizontal duplication, where you're running multiple copies of the application behind a load balancer. You have z-axis scaling, where you're running multiple copies of your monolith behind a load balancer, but the load balancer is using an attribute of the request, like the customer ID, to route requests to a particular destination. So some customers go to one destination, other customers go to a different destination. At the database level, this would be called sharding, where the primary key of the row determines which server that row resides upon. But then there's y-axis scaling. That's different. Rather than having a monolith, you actually functionally decompose the architecture into a set of services. So each one of them is a sort of mini application, so to speak, that implements a particular business function. And that, to me, sort of is the essential definition or the key motivation behind the microservice architecture. It's functional decomposition, breaking things apart by function. So a more complete definition of the microservice architecture is this. So it's an architectural style that structures the application as a set of services. And each service, and I don't really like the term microservice, because that implies that it's tiny. 100 lines of code, 2 weeks worth of work, and so some of those metrics that have been used in the past. But in reality, a service should be highly maintainable and testable. It should be loosely coupled. If you remember, one of the key requirements here is that you have a loosely coupled modular architecture. It should be independently deployable, so you can push into production changes to one service without having to deploy any other services. Each service typically implements a business capability, and I think this is a really key point, it is owned by a small team. Once again, these teams are like 5 to 9, and they're cross-functional. So if you have a service that requires a much bigger team, then that service is actually too large. And that's sort of the upper bound on service size. Because once again, we want to have these highly productive small teams. Then not only that, I would actually recommend quite a coarse-grained microservice architecture where you actually start off with just one service per team, and only introduce more services for a given team if it actually solves a real problem. Like if splitting a service into two actually enables each part to be tested independently and hence much faster. And that's quite a change from a lot of the sort of the microservice architectures that you see publicly, or I've encountered when I visited clients, where I've seen like one service per developer is a very common pattern. And then there are extreme examples like Monzo Bank in the UK, where they appear to have 10 services for each developer, which in my opinion is an excessively fine-grained, excessively complex architecture. So start off simple, one service for each team. So if we look at the the example application, as a microservice architecture, it consists of a set of services. Each service implements a business function like order management, delivery management, and so on. Each service has its own database because that's important to ensure loose coupling. And I'm going to talk more about that later. I'm also going to describe how asynchronous communication between services is actually incredibly useful and quite common. So your architecture is very likely to include a message broker. And you can apply functional decomposition to a server-side web application that's generating HTML and have web applications for each functional area of the UI, because that will also benefit from functional decomposition. If you're exposing an API to the outside world, which is either literally outside of the firewall or just to other parts of the large organization, you have an API gateway. That basically functions as a facade that implements the public interface and then routes requests appropriately to the actual services. So in this example, I've got JavaScript running in the browser, and I have a mobile application that are both making REST calls to the API gateway. So as you can see, there's many more boxes and arrows. There's a lot more complexity here, which is actually one of the downsides of this architecture. But there are quite a few benefits. It can enhance maintainability. If you're a developer working on a service, the amount of code that you have to deal with is significantly smaller. You don't have to deal with a much larger application. So your code base is much easier to understand and change. The modularity is enforced with this architecture because every service has a well-defined remote API that cannot be bypassed. It's also evolvable. You can incrementally replace or upgrade the technology stack of your application one service at a time. You don't have to upgrade the entire code base in one go. So that lets you make quite radical changes to your technology stack. You could try a new language or switch frameworks a lot more easily than you can with some massive code base. And that's really, really important for these long-lived applications. Testability is a lot easier as well because each service is small, which makes it easier and faster to test. And obviously, each service is independently deployable as well by definition. So that all, between testability and deployability, that makes it possible to do DevOps of large, complex applications. And there are also some other technical benefits as well, like enhanced scalability. A service could be written using some much more scalable, though perhaps less convenient framework in order to meet its unique requirements. And also a failure with inside one service is likely to have a much smaller blast radius than, say, a memory leak inside the whole monolith. And this slide actually sums up the relationship between the benefits of the microservice architecture and DevOps and the small teams. You got the testability and deployability that you need to do DevOps. You've got the modularity that's required for small teams. So that's huge, really key. At the same time, there are some drawbacks. This architecture, as you could tell from the diagram I had a few slides ago, is much more complex. There are many more moving parts. You're building a distributed system, so you have to deal with inter-process communication and all of its complexities, including partial failure. Also, because each service has its own database, you've got all of the complexities of distributed data management, which I covered in my tutorial yesterday. Testing to make sure that services actually can communicate poses some interesting challenges, and you have to learn new techniques like consumer-driven contract testing. And then also from a deployment perspective, there are many more moving parts in production. You've got tens or hundreds of services, each one of which is basically its own small application. And there are multiple instances of it at runtime, and they all need to be managed, orchestrated, monitored, and so on. So there's a bunch of challenges. This is not an architecture that you should choose lightly. And then also, identifying service boundaries is actually quite challenging. It requires thought, and then sadly, there's no mechanical process that you can follow to come up with an ideal architecture. And if you get it wrong, you could build a distributed monolith, which is essentially the worst of both worlds. And then also another challenge is actually migrating an existing monolith to a microservice architecture. That's a process that can take years. For instance, Airbnb have been working on refactoring their architecture to services for about the past three or 4 years. But if you're building a large, complex application and you need to deliver changes much more rapidly, much more frequently, and much more reliably, then this is usually a good choice. Conversely, if you're building a small application with a small team, probably the monolith is a much better choice. It's one of those things where it really depends on context and requirements. Neither pattern is a silver bullet. Okay, so that's the microservice architecture. I kind of now want to just talk a little bit about the structure of an individual service. And for that, I'm going to talk about the hexagonal architecture, yet another shape. So when we draw pictures of our software, we often like to use layers, right? And in particular, there's this whole 3-layer, 3-tier architecture where you've got a presentation layer handling requests from the outside world. You've got the business logic, that's where your entities live. And then you've got a persistence layer. And we kind of draw it like this. But arguably, this doesn't really reflect reality. Really, does your business logic depend upon the persistence layer in quite that way? Is there only really one presentation layer? Also, is there only really one persistence layer as well? It's sort of, even though it's really common to think in these terms, it's not entirely accurate. So for that reason, I like to use the hexagonal architecture, because not only is it sort of more accurate, but it also it's it's a good visual as well. So with the hexagonal architecture, it puts the business logic at the core of the application. So the yellow hexagon is actually the core of the service, and then around it is other stuff. The business logic has various ports. And you can think of that as Java interfaces. So there are two types of ports. There are inbound ports that enable stuff outside of the business logic to invoke the business logic. And then there are outbound ports that enable the business logic to, say, access a database. But those are basically interfaces. And then you have adapters, and a good example of that would be a controller class that handles HTTP requests. That actually, so an inbound adapter would then invoke the business logic using an inbound port. There are also outbound adapters, like a database access object, and that actually would implement the port interface, and that's how the business logic would invoke the database access logic. But you can see that the database access logic depends upon that port interface, and so it's actually decoupled from the business logic. And there are other adapters as well, like an inbound adapter for processing messages, and say an outbound adapter that's making REST calls to some other service. So that's kind of a nice model for thinking about the architecture of an individual service and also structuring your code base as well. So then if we look at the structure of a service, it's something like this. I mean, the whole reason for a service to exist, and in fact, the whole reason for a team to exist, is to expose an API. The API consists of two parts. There are operations, which can be invoked by the service's clients. And there are actually two types of operations. There are commands that change data. So if this was the order service, it would create, there would be commands for creating, revising, and canceling orders. And then there are queries which retrieve data without modifying it. So there would be, for example, find order history, so on and so forth. These operations you might think as always being invoked using a synchronous protocol like REST, or if you're feeling adventurous, gRPC. But it turns out that a lot of the time, particularly with inter-service communication, especially when you're invoking commands, it's often much better to use asynchronous messaging. So send commands over a message broker, because that, as I'm going to describe, actually improves or reduces the coupling between components. So that's one part of the API, its operations. The other part is that it's quite common for services to emit events. So in domain-driven design terms, these would be domain events. So when the state of a business object changes, the business object emits an event, which actually then gets published by the service. So that's the key part of the service, is its API. That's its whole reason to exist. Then, of course, the service might actually have dependencies. It might invoke the operations of other services, and it might also subscribe to the events of other services as well. So that's kind of sort of the black box view of the structure of a service. It's got roles, responsibilities, it has an API, it emits events, and it has dependencies. So I now want to talk a little bit about coupling. And for that, I'm going to use this iceberg metaphor, which I know is not a shape, but it kind of looks like a triangle. So this is a really useful metaphor. So services, as I just described, collaborate. That's quite common. So for example, the order service, in order to create an order, has to invoke the customer service in order to ensure that there's sufficient credit for that customer available, right? Sufficient available credit. So that means that there are dependencies between services, there are collaboration, but you want to make sure that any coupling is loose. And it turns out there's actually at least two types of coupling. There's runtime coupling, which is where one service, if it's coupled at runtime to another one, can't work unless that other service is also working. And I'm going to talk about that next. And then the other type of coupling, which I'm going to talk about now, is design time coupling. And that's where changes to the API of a service can require changing its clients. So if we look at design time coupling, that's particularly problematic if it's constantly occurring, because it forces teams to coordinate their work. Right? So imagine the customer service kept on changing its API. That would then require the order service to keep being updated so that they can continue to work, right? So you got to schedule meetings to discuss the work. You got to find the meeting room for the meeting, and there's never enough meeting rooms, right? And in general, all of this cross-team collaboration, communication and collaboration slows down development. Studies have shown that decision-making within a team is 10 times faster than decision-making between teams. So it's really important to minimize design time coupling. So you want to have well-designed, stable APIs that encapsulate the implementation, and you have to be very careful about using any kinds of shared libraries. I like to think of a service as looking like an iceberg. The saying goes that the visible part of an iceberg is tiny compared to what's below the waterline. And I think that's a great metaphor. And a service should have a relatively small API that encapsulates a much larger implementation, because that means that you can change the implementation without impacting the API. And there's some great examples of that. You could imagine like a credit card processing company, like where you just have an API which is sort of like charge this credit card number, this amount, and credit this merchant, right? One operation, 3 parameters, but behind it is an awful lot of complexity. You know, that would be Stripe. The other one would be Twilio for sending an SMS. It's like, here's the destination number, here's the from number, here's the body. But you know, incredibly simple API, but behind that is like a multi-billion-dollar company, right? And presumably there's a lot of complexity of delivering SMSs globally. So that's, you want to think of that, you know, that's what your services should be like. The anti-pattern are services like, which are just wrappers around the database. And you know, there are some well-known tools and well-known frameworks that let you generate a REST API from your database schema. You know, those are basically anti-pattern generators. You know, there's no encapsulation. You've got, you know, basically no implementation really, and it's just this large unstable API. And then at the same time, you have to, you want to avoid sharing database tables as well, because that inhibits change. That's another form of design time coupling. So imagine that the order service could look up the available credit by querying the customer table. Super simple. But when it's time for the customer service team to change the structure of their table, guess what? They have to go coordinate that work with the order team. Meetings, finding a meeting room slows things down. And in the worst case, it can completely inhibit change. I think in a lot of enterprises, you can't change database schemas because you do not know who's accessing your database. And then there's also runtime coupling as well, where 2 services that are sharing the same database are actually competing for the same resources. Not only can one claim a lock that interferes with the other, but one service can basically steal all of the memory and CPU resources of the database server and basically block the other service, which might actually be more important, from doing its work. So you've got both runtime and design time coupling simply by sharing tables. So it's best not to do that. Only go through service APIs, and ideally have separate database servers for each service. Though I know with Oracle licensing is kind of expensive and so on. But open source running on the cloud, much better. Anyway, so that's design time coupling. I now want to talk about runtime coupling, and for that I'm using this metaphor of the cylinder, which is actually a visual representation of a message channel. So, you know, one of the challenges with runtime coupling, right, is that it reduces availability. So let's look at, you know, a really simple example where you've got the order service, post request comes into it to create an order. It then turns around and does a put request to the customer service to reserve credit, sitting there waiting for a response to come back, and then it can return a response to its caller. Super simple, right? Except that what this means is that the availability of the create order operation is the product of the availabilities of the 2 services, which is like less available. You know, and I've seen examples where, you know, a company will have a key API and its implementation requires 10 other services to collaborate. So that's actually the availability of one service to the power 10, which, you know, if you do the math, takes you from probably 4 nines to 3 nines, something like that. So suddenly, you know, your key operations, because of the synchronous coupling between the services that implement them, are not as available as they should be. And this is sort of an example of this sort of distribution is free anti-pattern, where developers just sort of use the same communication patterns that exist in the monolith, except that method calls are super fast, whereas inter-process communication is orders of magnitude slower, and you have all of this latency. Plus, if you're using synchronous communication, you have this tight runtime coupling and reduced availability. So you want to be very, very careful about one service synchronously calling another. And I think another really key concept is of a self-contained service. So that's a service that can handle a synchronous request without waiting for a response from any other service. And one way that you can achieve this is to use asynchronous messaging. A great book on asynchronous messaging is the Enterprise Integration Patterns book by Gregor Holpe. I mean, that's really a classic. It's basically a very comprehensive pattern language for message-based applications. Fundamental idea is that a sender sends a message which consists of headers and a payload over a message channel to a recipient. You know, that's the essence of messaging. These message channels are basically an abstract representation of whatever capabilities the underlying message broker provides. And even there's actually brokerless messaging implementations as well. So, you know, it could be Kafka topics if you're fashionable, or it could be JMS queues and topics. And there's two types of channels. Point-to-point and publish-subscribe. So point-to-point is sending a message to just one recipient, whereas obviously publish-subscribe delivers the message to all of the participants. So one way that you could use messaging to make the order service self-contained is as follows. You can use what's known as a saga, which is one of these patterns from distributed data management. Which is a whole, well, I did a 3-hour tutorial on that. But basically the way it would work is as follows. Post request creates the order. The order service returns immediately, basically saying, I've created the order and I'm working on validating it. And in the meantime, it publishes an event saying, I've created an order. One of the consumers of that event is the customer service, which can then reserve credit. It's got a message handler, an event handler, and then it will publish its own event saying, yes, I've reserved credit, or credit limit was exceeded. That then gets consumed by the order service, which would then approve the order or reject it. So there's a bunch of messages being exchanged in the background. And this is an example of a choreography-based saga. And there's another type, which is orchestration. But what's nice about this is that the post API, or the post endpoint to be precise, is only dependent upon the availability of the order service, because the communication with the customer service is essentially happening in the background. So you have much better availability. Downside, however, is, well, you've got all of the complexity of sagas. And there's a whole bunch of subtle issues around design. It's an eventually consistent model, for example. And then another complexity or issue is that the initial response that comes back from the post doesn't actually tell the client whether the order was accepted or rejected. The client actually has to check back later, which in practice is not a huge burden, but it does make things slightly more complicated. But anyway, that's one way of using asynchronous messaging in order to make a service self-contained. Another option is to use CQRS, Command Query Responsibility Segregation, which is a really fancy way of saying replicate the data. So with this version, the customer service publishes events when customers are created or their credit limit is changed. The order service subscribes to those events. That enables it to maintain a replica of the customer and its credit limit, which then enables the order service to actually be responsible for maintaining the customer's available credit. So in other words, the responsibility of knowing the credit is actually still owned by the customer service, but it's replicated, but the order service is now responsible for managing the available credit. The nice thing about this is that, once again, the order service doesn't need to synchronously interact with the customer service. What's even better, the response can actually tell the client, yes, the order was accepted or the order was rejected. So it's sort of back to the original API, but now you've got the cost and complexity of this replication mechanism. Plus, there's also the possibility that the order service would make decisions based on stale data, right? But on the other hand, you could say that the credit limit is a relatively static value, so this is an acceptable trade-off for this particular scenario. And obviously, you know, whether this is efficient or cost-effective depends on how many rows of data you have to replicate as well. I mean, I like to joke, I guess Sweden's a relatively small country, so how many rows could you have in your customer table, right? I made the joke in Australia, and I think they only have 20 million people, right? So that's sort of laptop-sized database, right? Yeah, but you know, you're operating at Amazon scale or you know, Facebook scale, you know, many orders of magnitude more rows that might need to be replicated, and it might be too expensive. But even LinkedIn actually make use of this pattern. Okay, so that's sort of the cylinder, the messaging, loose runtime couplings through asynchronous messaging. Now, I want to talk about the final topic is that I want to talk about the success pyramid. And it turns out that there's a really interesting relationship between testing and using the microservice architecture. So, you know, the whole goal of using microservices is basically to enable DevOps, plus loosely coupled teams and so on. DevOps actually requires automated testing, right? I mean, there's just no place for significant role for manual testing if you're trying to deliver software rapidly, frequently, and reliably. And then at the same time, the actual complexity of the microservice architecture demands that you have good automated testing as well. It's not really, you know, if you've got a relatively much more complex architecture, you really should not rely on manual testing. So in a sense, then adopting microservices without using automated testing is sort of self-defeating and very, very risky. The problem you have is that automated testing appears not to have caught on in the developer community. I mean, it's really funny, right? Like JUnit has been around for 1 million years, like I think probably 20 years roughly, right? Yet, you know, when you survey organizations, most organizations are not relying extensively on automated testing. So there's a mismatch between, you know, modern development techniques and the state of automated testing. We need to do better as a community. But so when you do embrace testing, you know, one key idea is this notion of a testing pyramid, which is a little controversial in this, but the big idea is that it shows the relative proportions of the types of tests that you need to write. Tests at the bottom of the pyramid, like unit tests, are much more reliable, much faster because they're entirely in memory and they're much cheaper to write. Whereas if you move up the stack, the tests get increasingly brittle, slower, and costly. And the worst example is doing end-to-end tests of a large, complex system where just due to its size, something's guaranteed to not start up right. So you want to push the tests as far down the pyramid as possible. You know, like if you've got a banking application and you'll recalculate and you've got a calculator for the repayment schedule for a loan, please test that using unit tests. You don't want to test that using complex end-to-end tests because it will just be too slow. The other key idea, of course, is that you have an automated deployment pipeline. That's how code gets from a developer laptop into production, is through this automated pipeline that's a series of sort of functional and non-functional tests. And then ideally what comes out the other end is automatically deployed into production. And you know, how this relates to services is that each service should have its own automated deployment pipeline. So these teams are working independently on their services. They commit a change. The change goes through that services deployment pipeline, pushed into production. And I'll touch on this in a minute. You might want to do an end-to-end test, but I would encourage you to avoid that and just do testing at the service level. So one key thing you have to deal with in a microservice architecture is API management. Teams are constantly changing their services, right? And it's really important that they never introduce breaking changes into their APIs, because if they go deploy that new version of a service into production, that will break all of their clients and cause an outage. So you could do that with end-to-end testing, but there's this really useful technique known as consumer-driven contract testing, where you actually test the client and its services independently, but in a way that guarantees that they can communicate. So the example I have is like the API gateway invokes the order service through using an order service proxy that makes a get to the order controller. And the way you test it is by writing a contract or writing several contracts. These contracts are written by the API gateway team. They're written by the client team. And they're basically saying, this is how we expect the API to behave. So this is like API definition by example. So you have a set of contracts that define the expected behavior. Those are then used to test the order service proxy class in isolation against, in this example, I'm using WireMock, which is basically Mockito for HTTP APIs that basically simulates the order service using those contracts. When it gets a request that matches a request in the contract, it sends back the matching contract's response. So it's simulating the API. So that's good, but then how do you know that these contracts match the actual behavior? Well, you use those contracts on the other side as well to test the controller. It's a little bit more involved, and I don't have time to go over all of the details, but basically what you're doing is with these same contracts, and I should say this example is with Spring Cloud Contract. There are other consumer-driven contract testing frameworks. So basically, you're with the same contract documents, you're testing both the consumer and the provider, so therefore, fingers crossed, they can actually communicate. And this actually enables them to be tested independently while giving you a high degree of confidence that they agree on what that API is. And this is really important because you really want to avoid running end-to-end tests. Because basically, not only are they brittle, slow, and costly, they actually end up being a bottleneck, right? Imagine that you've got these complex end-to-end tests that take a long time to run, fail randomly. That's going to make it really slow to get changes into production, which is going to really be painful if you've got a production outage and you want to push a bug fix into production. You have to go through these end-to-end tests because that's your company policy. So you want to minimize or eliminate end-to-end tests whenever possible, which requires a sort of mind shift with how kind of QA, I think, sort of views system behavior. And then there's this. Which is, I mean, it's not entirely serious, but this notion that testing doesn't actually stop sort of in your test environment, it actually continues into production. Because the really serious issue here is that any testing environment that you have is a simulation of production, and when things get into production, things will be different, and you will have bugs. And so you need a mechanism for dealing with bugs that occur in production, because they are inevitable. But there are ways to do it that give you a high degree of reliability. And one of those key patterns is canary deployment, where you've got version 1 running in production. You have this intelligent traffic router. You actually deploy version 2 alongside it, So version 1 is getting all of the production traffic. Version 2 is actually not getting traffic. You can test it in production. You can route some test traffic to it, perhaps from internal users. And then you can incrementally route more and more production traffic to version 2 and less to version 1. At the same time, you're monitoring behavior, looking at latency, looking at error rates. And if you ever notice a problem, you quickly roll back. Whereas if everything's good, you just keep routing more and more traffic to version 2 until all of the traffic is going to version 2 and none to version 1. So that's essentially doing testing or validation that your release is a good one in your production environment. And then ultimately you can undeploy version 1. And running on the cloud for sure makes this possible because you can temporarily use additional resources. And if failing that, Kubernetes or something equivalent on your in-house data center with hopefully enough capacity will work as well. So yeah, this is one technique that's just sort of this notion that testing continues into production. And there's a lot to be said about that, but I appear to have got to the end of my talk, or the designated slot, and I know there's beer waiting for you. So in summary, right, I mean, the goal is rapid, reliable, and frequent delivery of software, and you achieve that using the success triangle, right? You know, the microservice architecture has the abilities or the architectural quality attributes you need to deliver a large, complex application, rapidly, frequently, and reliably. The hexagonal architecture is a good way of thinking about the structure of an individual services. To ensure loose design time coupling, you want to think of the iceberg metaphor. And to ensure loose runtime coupling, you want to look to using asynchronous messaging rather than synchronous communication between your services. And last but not least, don't forget to do automated testing, because if you don't, it will not go well. So that's my talk. Thanks for listening, and I hope that you found it useful. And you can find the slides at the bit.ly link. So thank you. And down for questions if you have them.